In 1907, Albert Einstein sat at his desk in a Swiss patent office and imagined a man falling from a roof, a simple thought experiment that would occupy the next 8 years of his life, pulling him through mathematical labyrinths, sleepless nights, and moments of profound doubt before emerging as something that would reshape humanity's understanding of space, time, and gravity itself. This is a story of patient struggle, of equations scrawled and abandoned, of a mind reaching toward something just beyond its grasp, and finally, in November of 1915, finding it. If these quiet journeys through history bring a kind of stillness to restless evenings, the subscribe button is there whenever it feels right. The year is 1905. And a young physicist has just published 4 papers that will change everything, though the deepest revolution still lies ahead, waiting to be discovered. Let us begin there. In the year 1905, a young man of 26 years, working as a technical expert third class at the Swiss Federal Patent Office in the city of Bern, submitted a paper to the German physics journal Annalen der Physik. The paper bore the rather unassuming title On the Electrodynamics of Moving Bodies, and it arrived at the journal's offices in late June of that year, during what would later be called Albert Einstein's miracle year, his annus mirabilis, when he published 4 papers that would each, in their own way, reshape the foundations of physics. This particular paper, the one concerning the electrodynamics of moving bodies, would come to be known as the foundation of the special theory of relativity, though Einstein himself did not use that precise phrase in its pages. The paper ran to some 30 pages in its published form, and it contained no references to other scientific literature, no footnotes acknowledging previous work, which was unusual for a scientific publication even then, and which reflected something of Einstein's isolation from the academic mainstream, working as he was in a patent office rather than a university. The patent office itself was located at number 49 Speichergasse in Bern, a handsome building where Einstein spent his days examining patent applications, many of them concerning electrical devices and the synchronization of clocks, which was a matter of considerable practical importance in that era of expanding railway networks and telegraph systems. The work was not unpleasant, and Einstein later recalled that it left him with sufficient mental energy to pursue his own investigations into the fundamental nature of physics during his spare hours. His position there had been secured with the help of the father of his friend Marcel Grossmann, who had intervened on Einstein's behalf after a period of some difficulty in which the young physicist had struggled to find academic employment. The patent office provided a steady income, modest but sufficient, and it afforded Einstein a certain freedom from the pressures and politics of academic life, a freedom he would look back upon with some fondness in later years. The paper on the electrodynamics of moving bodies began not with complex mathematics but with a simple observation about asymmetries in the existing theories of electricity and magnetism. Einstein noted that when a magnet moves relative to a conducting wire, the current induced in the wire depends, according to the theories of the time, on which object is considered to be in motion, the magnet or the conductor, even though the observable phenomenon, the current itself, depends only on the relative motion between them. This asymmetry troubled Einstein, for it suggested that the existing theories contained unnecessary distinctions that had no counterpart in the physical phenomena they were meant to describe. From this modest beginning, examining a simple case of electromagnetic induction, Einstein proceeded to construct an entirely new framework for understanding space, time, and motion. The framework rested upon 2 postulates: two fundamental assumptions that Einstein took as starting points, and from which the rest of the theory followed through careful reasoning. The first postulate, which Einstein called the principle of relativity, stated that the laws of physics take the same form in all inertial reference frames. An inertial reference frame, to explain the term gently, is a frame of reference that is not accelerating, one that moves at a constant velocity or remains at rest, and in such a frame an observer who conducts experiments will find that the fundamental laws governing those experiments are identical to the laws found by any other observer in any other inertial frame. There is no experiment, no measurement, no physical observation of any kind that can distinguish one inertial frame from another in an absolute sense. You cannot determine, by any means whatsoever, whether you are truly at rest or moving at a constant velocity through space, because the distinction itself has no physical meaning. This principle was not entirely new, for it echoed ideas that could be traced back to Galileo Galilei, who had noted centuries earlier that a person below decks on a smoothly sailing ship cannot tell from the motion of objects in the cabin whether the ship is moving or at anchor. What Einstein did was to elevate this observation to the status of a fundamental principle and to insist upon its universal validity. The second postulate concerned the speed of light, and it was here that Einstein departed most dramatically from the intuitions of everyday experience and from the physics of Newton. This second postulate stated that the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the motion of the observer. This is a deeply strange claim if one pauses to consider it carefully. In our ordinary experience, velocities add together in straightforward ways. If you are walking at a certain pace along the corridor of a moving train, your speed relative to the ground is the sum of your walking speed and the speed of the train. But light does not behave this way. If a lamp emits light while moving toward you at tremendous speed, the light itself does not arrive any faster. It travels at precisely the same velocity as light emitted from a lamp at rest, approximately 300,000 kilometers per second in a vacuum. This constancy of the speed of light had been suggested by the famous experiments of Albert Michelson and Edward Morley, conducted in 1887, which had failed to detect any variation in the speed of light due to the Earth's motion through space, though Einstein later indicated that he was not strongly influenced by those experiments in formulating his theory, and scholars continue to discuss exactly which considerations weighed most heavily in his thinking. From these two postulates, the constancy of light speed and the principle of relativity for inertial frames, Einstein derived a series of remarkable consequences. He showed that simultaneity is relative, meaning that two events which appear simultaneous to one observer may appear to occur at different times to another observer in relative motion. He showed that moving clocks run slow, a phenomenon called time dilation, and that moving objects contract along the direction of their motion, a phenomenon called length contraction. He showed that mass and energy are related, a conclusion he explored in a subsequent short paper that same year, though the famous equation expressing this relationship in its most compact form came slightly later. All of these conclusions followed logically and inevitably from the two postulates, through reasoning that, while requiring careful attention, did not demand any mathematics beyond algebra and the most elementary calculus. The special theory of relativity, as it came to be called, was a triumph of physical insight and logical clarity. And yet, even as Einstein's 1905 paper began to circulate among physicists and to attract attention and discussion, Einstein himself was aware that the theory was incomplete. The special theory was a theory of inertial frames, of observers and objects moving at constant velocities, and it said nothing about what happened when objects accelerated or when gravitational forces were present. Acceleration and gravity were beyond its scope, beyond its reach, and this limitation troubled Einstein almost immediately. By 1907, just 2 years after the publication of the original paper, Einstein was already thinking deeply about how to extend the theory, how to generalize it to include accelerated motion and gravitational phenomena. He would later describe this period as the beginning of a long struggle, a struggle that would occupy him for the next 8 years and that would eventually lead to the general theory of relativity. During these years in Bern, Einstein was not entirely alone in his intellectual pursuits, despite his position outside the academic world. He had formed a small informal discussion group with 2 friends, Konrad Habicht and Maurice Solovine, a gathering they called, with gentle self-mockery, the Academy Olympia, or the Olympia Academy. The name was a playful reference to the grand academies of science, the learned societies where distinguished professors gathered to present their findings, and by adopting such a grandiose title for their modest trio, the young men were gently poking fun at academic pretension while also affirming their own serious intellectual ambitions. They would meet in the evenings, often at Einstein's apartment, to read and discuss works of philosophy and science, books by Ernst Mach, David Hume, Baruch Spinoza, Henri Poincaré, and many others. They would talk for hours, sometimes late into the night, about the nature of knowledge, the foundations of physics, the meaning of space and time. The discussions were informal and wide-ranging, marked by genuine curiosity and the pleasure of intellectual companionship. Konrad Habicht was a mathematician, a friend from Einstein's student days at the Polytechnic in Zurich, and Maurice Solovine was a Romanian student of philosophy who had come to Bern and who had first met Einstein by responding to an advertisement Einstein had placed, offering his services as a tutor in physics. The 3 men became close friends, and although the Academy Olympia disbanded around 1905, as its members moved to different cities and took up different positions, the spirit of those discussions stayed with Einstein and influenced his thinking in ways that are difficult to measure but should not be underestimated. The reading and conversation helped Einstein to clarify his ideas, to question his assumptions, and to situate his work within a broader philosophical context. Mach's critique of Newtonian mechanics, with its emphasis on the relativity of motion and its skepticism toward absolute space, was particularly influential, though Einstein would later distance himself from some aspects of Mach's philosophy. In 1907, Einstein was asked to write a review article on the special theory of relativity for a scientific yearbook, and in the course of preparing this article, he confronted directly the question of how gravity might fit into the new framework. He later recalled that during this period, while still working at the patent office in Bern, he had what he described as the happiest thought of his life. The thought was this: if a person falls freely, as from the roof of a house, they do not feel their own weight. During the fall, in the immediate vicinity of the falling person, gravity seems to disappear. This simple observation, which Einstein would later develop into the principle of equivalence, suggested a deep connection between acceleration and gravity, a connection that pointed the way toward a more general theory. But the path from this initial insight to the completed general theory would prove to be long and arduous, filled with false starts, mathematical difficulties, and conceptual puzzles that would take years to resolve. The special theory, for all its elegance, was limited to a very particular class of situations, situations in which observers move at constant velocities relative to one another and in which gravitational effects can be neglected. In the everyday world, such situations are approximations at best. Objects accelerate. Gravitational fields are everywhere present. The Earth pulls us downward, the Sun holds the planets in their orbits, and these gravitational influences shape the motion of all matter in the universe. A theory that could not encompass gravity was, in a fundamental sense, incomplete, and Einstein knew this. The extension of the theory to include gravity would require new concepts, new mathematics, and a willingness to abandon some of the assumptions that had served so well in the special case. Meanwhile, others were also thinking about the implications of special relativity, and in 1908, a former mathematics professor of Einstein's at the Polytechnic in Zurich, Hermann Minkowski, delivered a lecture at the University of Göttingen that would have a profound influence on the subsequent development of the theory. Minkowski had taught Einstein mathematics during his student days, and he had not been particularly impressed by the young Einstein as a student, once describing him as a lazy dog. But Minkowski recognized the importance of the 1905 paper, and he saw that its physical content could be expressed in a beautiful and powerful mathematical form, a form that Einstein himself had not fully appreciated. In his lecture, Minkowski introduced the concept of spacetime, a four-dimensional continuum in which the three dimensions of space and the one dimension of time are united into a single geometric structure. In this formulation, events are represented as points in the four-dimensional spacetime, and the relationships between events, the intervals separating them, are described by a geometry that differs in certain crucial respects from the ordinary Euclidean geometry of everyday experience. Minkowski opened his lecture with words that have become famous in the history of physics. He said that henceforth space by itself, and time by itself, are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. This was a striking way of expressing the deep insight that the special theory of relativity had revealed, the insight that space and time are not separate and absolute entities but are intertwined aspects of a single underlying structure. The spacetime formulation provided a geometric language in which the laws of special relativity could be expressed with great elegance and clarity, and it would prove to be indispensable for the later development of the general theory. Einstein, however, was not initially impressed. When he first encountered Minkowski's four-dimensional spacetime formulation, he dismissed it rather curtly, describing it as superfluous learnedness. To Einstein, the mathematics seemed like an unnecessary complication, an elaborate formal apparatus that added nothing essential to the physical understanding he had already achieved. He had derived the special theory using relatively simple mathematics, and he did not immediately see the need for the more sophisticated geometric framework that Minkowski had constructed. This dismissal was, in retrospect, a mistake, and it was a mistake that Einstein would later come to regret deeply. In the years that followed, as he struggled to extend special relativity to include gravity and acceleration, he would find that the geometric approach, the approach pioneered by Minkowski, was not merely a formal convenience but an essential tool, a way of thinking about spacetime that opened doors he could not have opened otherwise. The geometry of spacetime, as Minkowski had formulated it, treated time as a dimension on a similar footing to the three dimensions of space, though not quite identical. The key feature of the geometry was the spacetime interval, a quantity that combines spatial and temporal separations in a specific way and that remains unchanged under the transformations between different inertial reference frames. This invariance of the spacetime interval is the geometric expression of the constancy of the speed of light, and it provides a unified framework for understanding all the relativistic effects, time dilation, length contraction, the relativity of simultaneity, as manifestations of a single underlying geometric structure. Objects moving through spacetime trace out paths called world lines, and the geometry determines which paths are possible and how different observers perceive the same events from their different perspectives. By 1908, then, the special theory of relativity existed in two forms: the original physical formulation that Einstein had presented in 1905 and the geometric formulation that Minkowski had developed. The two formulations were mathematically equivalent, containing the same physical content, but they suggested different ways of thinking about the theory and different approaches to its extension. Einstein would eventually come to embrace the geometric perspective, to see spacetime not merely as a mathematical convenience but as a physical reality, a stage on which events unfold and whose geometry is shaped by the presence of matter and energy. But this realization lay some years in the future, and in the meantime Einstein continued to think about gravity and acceleration, searching for the path that would lead from the special theory to something more general, more comprehensive, more complete. The limitation of the special theory, its restriction to inertial frames, was not a minor technical matter but a fundamental constraint that left large portions of physical reality outside its scope. The planets do not move in straight lines at constant velocities. They follow curved orbits, accelerating continuously as they circle the Sun. A ball thrown into the air accelerates downward under the influence of gravity. A person standing on the surface of the Earth feels a force pressing upward against their feet, and this force, the familiar sensation of weight, is intimately connected to the gravitational field of the Earth. None of these phenomena, so basic and so pervasive, could be accommodated within the framework of special relativity as Einstein had originally formulated it. A new theory was needed, a theory that could handle accelerated motion and gravitational fields, a theory that would generalize the special theory to encompass these broader cases. Einstein's recognition of this need, his dissatisfaction with the limitations of his own creation, set him on the path toward general relativity. The journey would take nearly a decade, from 1907, when he first began to think seriously about gravity and acceleration, to 1915, when he finally completed the field equations of the general theory. Along the way, he would move from the patent office in Bern to academic positions in Zurich, Prague, and Berlin. He would wrestle with mathematical formalisms far more complex than anything he had encountered before. He would make mistakes, pursue false leads, and experience periods of frustration and doubt. But he would also receive help from friends and colleagues like Marcel Grossmann, who would introduce him to the tensor calculus and differential geometry that would prove essential to the final theory. And always, guiding his efforts, would be physical intuition, the same intuition that had led him to the special theory, the intuition that the laws of nature should be simple, beautiful, and universal in their application. The story of that decade-long journey is a story of persistence, of intellectual courage, and of the gradual construction of one of the most profound theories in the history of physics. But it begins here, with the special theory and its limitations, with the recognition that something more was needed, with a young man at a patent office in Bern, looking up from his desk and thinking about falling bodies and the curious disappearance of weight in free fall. In the quiet autumn of 1907, in the small and orderly city of Bern, nestled among the gentle curves of the Aire River and the distant white peaks of the Bernese Alps, Albert Einstein sat at his desk in the Swiss Federal Patent Office, engaged in the methodical work of examining technical applications and assessing the merits of various inventions. He was 28 years old, still unknown to the wider world despite having published several papers of extraordinary importance just 2 years earlier, and his days followed a pleasant and predictable rhythm that suited his contemplative nature. The patent office occupied a handsome building on a quiet street, and Einstein's position as a technical expert third class afforded him both a modest income and, more importantly, sufficient mental space to continue his private investigations into the fundamental nature of the physical world. It was during one of these seemingly ordinary November days, while seated in his wooden chair and perhaps gazing out the window at the grey Swiss sky, that a thought came to him which he would later describe as the happiest thought of his life, a thought so simple and yet so profound that it would eventually lead him to reshape humanity's understanding of gravity, space, and time itself. The thought that visited Einstein on that November day was not complicated in its initial form, and indeed its power lay precisely in its elegant simplicity. He imagined a person falling freely, perhaps from the roof of a building, and he considered what that falling person would experience during their descent. Setting aside for a moment the rather unfortunate circumstances that might lead to such a fall, Einstein focused his attention on the physical sensations that the falling person would feel, or rather, would not feel. A person in free fall, Einstein realized, would not feel their own weight. They would experience no sensation of being pulled downward, no pressure against their feet, no strain in their muscles working against the force of gravity. For the brief duration of their fall, before the inevitable and unpleasant encounter with the ground, the falling person would feel exactly as though they were floating freely in empty space, far from any gravitating body, weightless and unburdened by any force whatsoever. This observation, which might seem obvious once stated, struck Einstein with tremendous force, for he recognized in it a deep and previously unappreciated connection between gravity and the most fundamental aspects of motion. To understand why this thought brought Einstein such intellectual joy, we must consider what it revealed about the relationship between two quantities that physicists had long treated as distinct, namely gravitational mass and inertial mass. Gravitational mass is the property of matter that determines how strongly an object is attracted by a gravitational field, how much pull it feels from the Earth or the Sun or any other massive body. Inertial mass, on the other hand, is the property that determines how much an object resists being accelerated, how much force is required to change its state of motion. There is no obvious reason why these two properties should be related at all, for they describe quite different aspects of how matter behaves. And yet, as Galileo had demonstrated centuries earlier and as countless experiments had confirmed with ever-increasing precision, all objects fall at exactly the same rate regardless of their composition or their mass. A heavy stone and a light feather, in the absence of air resistance, will fall side by side and strike the ground at precisely the same moment. This remarkable fact, which we observe so regularly that we scarcely pause to wonder at it, implies that gravitational mass and inertial mass are not merely related but are in fact identical, that the very same property that makes an object harder to accelerate also makes it more strongly attracted by gravity, and these two effects cancel exactly to produce the universal rate of free fall. Einstein's falling person thought experiment illuminated this equivalence in a new and powerful way, for it showed that the effects of gravity could be made to vanish entirely simply by adopting the right frame of reference. A person standing on the surface of the Earth feels the downward pull of gravity as a constant and inescapable fact of their existence, but a person falling freely alongside them experiences no such pull, and indeed has no way of detecting, through any local experiment, that gravity exists at all. This suggested to Einstein that gravity was not quite like other forces, not a real force in the usual sense, but rather something more subtle, something that could be transformed away by a suitable change in perspective. The falling person and the person floating in distant empty space are, from the point of view of physics, in equivalent situations, and this equivalence hinted at a profound unity between gravitational phenomena and the geometry of motion itself. Einstein developed these ideas further through a thought experiment that has since become famous, involving an enclosed chamber such as a lift or an elevator, and considering what an occupant of such a chamber would experience under various circumstances. Imagine first a lift at rest on the surface of the Earth, with its occupant standing on the floor and feeling the familiar downward pull of terrestrial gravity. The occupant can perform various experiments within the lift, dropping objects and watching them fall, placing a ball on the floor and noting that it stays put, and all these experiments will confirm the presence of a downward gravitational field. Now imagine a second lift, this one located in the depths of empty space far from any gravitating body, but accelerating upward at precisely the rate of 9.8 meters per second squared, the same rate at which objects fall on Earth. The occupant of this accelerating lift will also feel pressed against the floor, will also observe dropped objects falling downward relative to the lift, and will obtain exactly the same results from every local experiment they might devise. Einstein's great insight was that these two situations are not merely similar but are fundamentally indistinguishable, that no experiment conducted entirely within the lift, without looking outside, could ever determine whether the lift is at rest in a gravitational field or accelerating in empty space. This principle, which Einstein called the equivalence principle, asserts that gravitational effects and the effects of acceleration are locally identical, that gravity and acceleration are, in some deep sense, two aspects of the same phenomenon. The word locally is important here, for over large distances or long times, genuine gravitational fields can be distinguished from pure acceleration by the presence of tidal effects, the slight variations in gravitational strength from place to place that cause the field to converge toward the attracting body. But in a sufficiently small region of space and over a sufficiently short interval of time, the equivalence is exact, and this exactness pointed Einstein toward a revolutionary new conception of what gravity actually is. Rather than a force acting between massive objects across the intervening space, gravity might be understood as a manifestation of the curvature of space and time themselves, with massive bodies warping the geometry of the spacetime around them and freely falling objects simply following the straightest possible paths through this curved geometry. Einstein first published these ideas in a review article that appeared in 1907 in the Yearbook of Radioactivity and Electronics, known in German as the Jahrbuch der Radioaktivität und Elektronik. The editor of this journal, Johannes Stark, had invited Einstein to write a comprehensive review of the principle of relativity, and Einstein obliged with an article that summarized and extended his special theory of relativity from 1905. In the final section of this review, Einstein turned his attention to the question of gravity, and it is here that the equivalence principle made its first appearance in the scientific literature. Einstein was cautious in his presentation, acknowledging that he was venturing into speculative territory, but he was also clearly excited by the possibilities that the equivalence principle opened up. He recognized that if gravity and acceleration were truly equivalent, then the special theory of relativity, which dealt only with uniform motion in the absence of gravity, would need to be extended and generalized to encompass accelerated motion and gravitational fields. This extension would require mathematical tools that Einstein did not yet possess, and nearly a decade would pass before he completed the task, but the foundation was laid in that 1907 review article. Among the predictions that Einstein drew from the equivalence principle, two stand out for their boldness and their eventual experimental confirmation. The first concerns the behavior of clocks in a gravitational field. Einstein argued that clocks located at different heights in a gravitational field would run at different rates, with clocks deeper in the field, closer to the gravitating body, running more slowly than clocks higher up. This gravitational time dilation, as it is now called, follows directly from the equivalence principle when combined with the effects of time dilation in accelerating reference frames. A clock at the bottom of an accelerating rocket, for instance, will run more slowly than a clock at the top, and by the equivalence principle, the same must be true for clocks at different heights in a gravitational field. Einstein expressed this effect mathematically and noted that while it would be extremely small under ordinary circumstances, it would have observable consequences for the frequencies of light emitted by atoms on the surface of massive bodies like the Sun. Light climbing out of a gravitational field would be shifted toward lower frequencies, toward the red end of the spectrum, an effect now known as gravitational redshift. The second prediction concerned the bending of light in a gravitational field. If an accelerating lift is equivalent to a lift at rest in a gravitational field, then a beam of light passing horizontally through the accelerating lift would appear to curve downward as the lift accelerates upward to meet it. By the equivalence principle, a beam of light passing through a gravitational field should therefore also be deflected, bending toward the massive body that produces the field. Einstein calculated the magnitude of this deflection for light passing close to the surface of the Sun and obtained a value of approximately 0.87 arc-seconds, a tiny angle but one that might be measurable during a total solar eclipse when the Sun's light is blocked and stars near the solar limb become visible. This prediction was remarkable and exciting, but Einstein did not yet know that his calculation was incomplete. The value of 0.87 arc-seconds accounts only for the equivalence principle effect, the bending that would be predicted by treating gravity as equivalent to acceleration in flat spacetime. The full theory of general relativity, which Einstein would not complete until 1915, would predict an additional contribution from the curvature of space itself, doubling the deflection angle to 1.75 arc-seconds. Einstein's 1907 prediction was thus only half the correct value, a fact that would have important consequences for the eventual experimental tests of his theory. The city of Bern in 1907 was a quiet and cultured place, the capital of the Swiss Confederation and home to a modest university and various intellectual societies. The old town, with its covered arcades and its medieval clock tower and its bears kept in a pit by the river, had a timeless quality that invited contemplation and unhurried thought. Einstein had lived in Bern since 1902, first as a provisional employee of the Patent Office and then as a permanent staff member, and he had grown fond of the city's orderly streets and its beautiful natural setting. The Air River, green with glacial melt from the distant mountains, curved in a great loop around the old town, and Einstein often walked along its banks in the evenings, thinking about physics and occasionally stopping to watch the swift current flowing past. These walks were an important part of his intellectual life, for it was often during solitary strolls, away from the distractions of daily work and domestic concerns, that his most productive thinking took place. The steady rhythm of walking seemed to free his mind for abstract contemplation, and the beauty of the river and the mountains provided a backdrop of tranquility that nurtured his deepest insights. Einstein's position at the patent office, though not prestigious in academic terms, had certain advantages that he appreciated. The work was interesting enough to engage his technical abilities without being so demanding that it exhausted his mental energies, and it left him free in the evenings and on weekends to pursue his theoretical investigations. He later spoke warmly of his years at the patent office, describing it as a kind of worldly cloister where he could hatch his most beautiful ideas. The examination of patent applications also gave him useful practice in analyzing physical systems and identifying the essential features of technical problems, skills that served him well in his theoretical work. And the regular salary, though modest, provided a security that allowed him to take intellectual risks without worrying about his career prospects. Einstein had tried and failed to obtain an academic position after completing his doctorate, and for the time being he was content to remain a patent clerk who did physics on the side, unknown to the wider world but quietly confident in the importance of what he was discovering. The Bern of those days had a small but active community of intellectuals and freethinkers, and Einstein had gathered around him a circle of friends who shared his passion for ideas. The most important of these friendships had been formed a few years earlier, when Einstein and two companions, Maurice Solovine and Konrad Habicht, had established a reading group that they jokingly called the Olympia Academy. The three friends met regularly to discuss philosophy and science, reading works by Hume and Mach and Poincare and debating the fundamental questions of epistemology and physics. By 1907 the Olympia Academy had dissolved, as Solovine and Habicht had both moved away from Bern, but the intellectual habits that Einstein had developed during those intense discussions remained with him. He continued to think deeply about the foundations of physics, questioning assumptions that others took for granted and seeking the simplest and most general principles from which the laws of nature might be derived. The 1907 Review article marked the beginning of Einstein's long struggle with gravity, a struggle that would occupy him for the next 8 years and bring him to the verge of despair before finally yielding the complete theory of general relativity. In that article, Einstein laid out the basic idea of the equivalence principle and drew its most immediate consequences, but he recognized that a full theory of gravity consistent with his principle would require a radically new mathematical framework. The special theory of relativity described physics in flat spacetime, where the geometry was Euclidean and the paths of light and matter were straight lines in the absence of external forces. But if gravity was to be understood as a manifestation of spacetime geometry rather than as a force acting within a pre-existing geometric background, then the geometry itself would need to become dynamical, curving and bending in response to the distribution of matter and energy. Einstein did not yet know how to formulate such a theory, and indeed the mathematics he needed had barely been developed by pure mathematicians and was entirely unfamiliar to physicists. As Einstein walked along the air in the fading light of those November evenings, watching the cold green water flowing past and perhaps thinking of his happiest thought, he could not have known how long and difficult the road ahead would be. The equivalence principle was a beginning, a glimpse of a profound truth, but the full theory would require years of effort, many false starts, and collaboration with mathematicians who could teach him the geometric tools he needed. There would be moments of doubt and frustration, periods when the goal seemed unreachable and the effort seemed futile. But there would also be moments of sudden insight, when pieces of the puzzle clicked into place and the outlines of the finished theory became visible through the fog. And at the end, in November of 1915, exactly 8 years after the happiest thought first came to him, Einstein would present the completed field equations of general relativity to the Prussian Academy of Sciences, and the new theory of gravity would be born. But that triumphant conclusion lay far in the future, hidden beyond years of toil and uncertainty, and for now the young patent clerk walked beside the river, turning his beautiful thought over in his mind, feeling the quiet joy of a great discovery taking shape, and not yet knowing where it would lead him. In the spring of 1911, Albert Einstein received an appointment that would mark a significant transition in his professional standing, though the city to which he traveled would prove to be a place of decidedly mixed experience, both intellectually stimulating and personally difficult in ways that would leave their mark upon his family life. The position was that of full professor of theoretical physics at the German division of Karl Ferdinand University in Prague, which was then part of the Austro-Hungarian Empire, a sprawling and ancient political entity that encompassed a great variety of peoples and languages and administrative peculiarities. This appointment represented Einstein's first full professorship, a position of genuine academic prestige that placed him among the established figures of European physics rather than among the promising younger scholars still making their way upward through the ranks of the academic hierarchy. He was 32 years old, no longer the patent clerk who had astonished the scientific world with his papers of 1905, but now a recognized theoretical physicist whose ideas about space and time and light had begun to reshape the understanding of the physical universe, even as many of his colleagues remained uncertain about the full implications of what he had proposed. The bureaucratic requirements for accepting this position in the Austro-Hungarian Empire included certain formalities that reflected the administrative character of that aging institution with its centuries of accumulated tradition and its careful attention to matters of official record-keeping. Among these requirements was the expectation that any person accepting a state position would declare a religious affiliation, as the empire maintained official connections between the state and various recognized religious bodies, and the paperwork of appointment needed to place each individual within one of these recognized categories. Einstein had for many years held no conventional religious beliefs and had formally left the Jewish religious community during his youth in Germany, a departure that reflected his early and thorough embrace of scientific materialism and his rejection of the religious observances in which he had been raised. Nevertheless, when faced with this administrative requirement, he wrote down the word mosaic, an older and somewhat formal term referring to the religion of Moses, which is to say the Jewish faith, thereby acknowledging his cultural and ethnic heritage even while maintaining no active religious practice or belief in any traditional theological sense. This was a practical accommodation to bureaucratic necessity rather than any return to religious observance, and Einstein approached it with the somewhat bemused tolerance of a man who understood that institutions have their requirements and that one must sometimes complete forms in order to get on with more important work. The university provided Einstein with an office in a building that overlooked a parkland of considerable natural beauty, with trees and pathways and the kind of peaceful greenery that might have seemed conducive to quiet contemplation of the deepest questions concerning the nature of space and time and gravitation. However, this particular park was attached to an institution for the care of individuals suffering from mental illness, what was then called an insane asylum, and the patients of this institution could sometimes be observed walking in the grounds below Einstein's window as he sat working on his theoretical problems. Einstein, who possessed a sense of humor that tended toward the dry and the gently ironic, was known to remark to visitors that those were the madmen who did not think about quantum theory, a comment that reflected his ongoing struggle with the strange and counterintuitive features of quantum physics, which he had himself helped to establish through his work on the photoelectric effect and which continued to trouble him with its apparent departures from the kind of deterministic physical reality he found most intellectually satisfying. The joke captured something of the genuine intellectual difficulty that quantum theory presented, the sense that dwelling too deeply on its implications might threaten one's comfortable assumptions about how the world fundamentally operates, while also displaying the characteristic Einstein wit that made him such an engaging presence in scientific and social gatherings despite his reputation for abstraction and his obvious preference for solitary thought. It was during this Prague period that Einstein published a paper of considerable importance for the development of his gravitational theory, a work that appeared in 1911 and that made specific predictions about phenomena that could, at least in principle, be observed and measured by astronomers equipped with appropriate instruments and favorable circumstances. In this paper, Einstein predicted that light passing near a massive body such as the Sun would be deflected from its straight path by the gravitational influence of that body, bent slightly toward the mass in a way that would alter the apparent positions of stars whose light passed close to the solar limb during its journey to Earth. He calculated the magnitude of this deflection for starlight grazing the edge of the Sun and arrived at a figure of approximately 0.83 arcseconds, which is a very small angle indeed, less than 1 second of arc, which is itself 1/60th of 1 minute of arc, which is in turn 1/60th of 1 degree. To visualize how small this is, one might consider that the full moon as seen from Earth spans roughly half a degree, or about 1800 arcseconds, so that the deflection Einstein predicted was smaller than this apparent lunar diameter by a factor of more than 2000. Nevertheless, this deflection was within the range of what careful astronomical observation might detect, particularly during a total solar eclipse when the moon blocks the brilliant light of the solar disk and allows the much fainter light of background stars to be photographed and their positions measured with precision. Einstein also predicted in this same paper the phenomenon now known as gravitational redshift, which describes how light climbing out of a gravitational field will lose energy and thereby shift toward longer wavelengths, toward the red end of the spectrum in the case of visible light. This effect arises from the relationship between gravitational potential energy and the energy of electromagnetic radiation, and it means that light emitted from the surface of a massive star will appear slightly redder when observed from a greater distance than it would appear if measured at the point of emission. This prediction, like the prediction of light deflection, offered a potential point of contact between theoretical speculation and observational astronomy, a way of testing whether Einstein's developing ideas about gravitation corresponded to the actual behavior of the physical universe or whether they represented merely an elegant mathematical construction without genuine physical content. The Prague paper thus marked an important moment in the transformation of Einstein's gravitational theory from pure theoretical speculation into a scientific proposal that made specific claims about what observers should find when they examined the universe with sufficient care and precision. The prediction of light deflection attracted the attention of a young German astronomer named Erwin Freundlich, who was working at the Royal Observatory in Berlin and who became genuinely enthusiastic about the possibility of testing Einstein's theoretical predictions through astronomical observation. Freundlich was drawn to the intellectual excitement of Einstein's work and saw in the prediction of light bending an opportunity for observational astronomy to contribute to fundamental physics in a most dramatic fashion. He began corresponding with Einstein about the practical challenges involved in detecting such a small deflection, discussing the technical requirements for photographing stars near the Sun during an eclipse and comparing their positions with photographs of the same star field taken when the Sun was elsewhere in the sky. This correspondence marked the beginning of a collaboration and friendship that would continue for years, with Freundlich becoming one of the most dedicated advocates for organizing expeditions to test Einstein's predictions during favorable solar eclipses. Einstein was grateful for this interest from the astronomical community, as he understood that his theoretical work would remain merely speculative until it could be confronted with observational evidence, and Freundlich's enthusiasm provided hope that such confrontation might eventually be arranged. The intellectual life of Prague during Einstein's residence there included a number of figures who would achieve lasting distinction in their various fields, and Einstein found himself drawn into a circle of thinkers and writers whose conversations ranged across physics and philosophy and literature and the great questions of human existence. Among the physicists in this circle was Philipp Frank, a younger scholar who would later become Einstein's biographer and who shared Einstein's interest in the philosophical foundations of physical theory, the deep questions about what scientific theories actually tell us about reality and how we ought to interpret the mathematical structures that prove so useful in describing natural phenomena. Frank was associated with the emerging movement of logical positivism, which sought to clarify the meaning of scientific statements and to eliminate metaphysical confusion from scientific discourse, and his conversations with Einstein touched on these methodological concerns even as Einstein pursued his own quite different philosophical intuitions about the nature of physical reality. The literary dimension of Prague's intellectual life was represented in part by the writer Max Brod, who would later become famous as the friend and literary executor of Franz Kafka and who was at this time an active participant in the cultural conversations of the city. Brod was interested in ideas of all kinds and enjoyed the company of scientists and philosophers as well as his fellow writers, finding in their different ways of approaching fundamental questions a stimulation for his own creative work. The gatherings that brought together such diverse figures as Einstein and Brod and Frank reflected the particular character of Prague in this period, a city where German-speaking and Czech-speaking communities maintained their separate institutions while sharing the same streets and coffee houses, a place of ancient architecture and modern intellectual ferment existing side by side. For Einstein, these social and intellectual connections provided a welcome counterbalance to the isolation that could accompany deep theoretical work, though his primary energies remained focused on the gravitational problem that increasingly occupied his thoughts. While Einstein found intellectual stimulation in Prague and made significant progress on his theoretical work, the city proved far less congenial to his wife Mileva, who experienced considerable unhappiness during their residence there and whose dissatisfaction contributed to the growing strain in their marriage that would eventually lead to separation and divorce. Mileva had herself trained as a physicist, having studied alongside Einstein at the Zurich Polytechnic, and she had once shared his intellectual passions and participated in discussions of the scientific questions that absorbed him. However, the years of marriage and child-rearing had drawn her away from active scientific work, and she now found herself in a foreign city where she struggled to establish social connections or to find the kind of meaningful engagement that might have made the move worthwhile from her own perspective. Prague's social divisions and the particular challenges of life in a city where she was neither fully at home in the German-speaking academic community nor connected to the Czech-speaking majority left her feeling isolated and unhappy, emotions that she did not conceal from her husband and that cast a shadow over their domestic life. The marriage between Albert and Mileva had already shown signs of difficulty before the move to Prague, But the unhappiness of the Prague years intensified these problems and marked a significant stage in the gradual dissolution of what had once been a partnership of genuine intellectual companionship as well as personal affection. The precise nature of their difficulties was complex and involved factors that neither party fully understood or articulated at the time, including the changing dynamics of their relationship as Einstein's fame grew and as Maleeva's own aspirations remained unfulfilled, the challenges of raising young children while one partner was absorbed in demanding intellectual work, and the ordinary disappointments and resentments that accumulate in any long marriage when circumstances prevent the full flourishing of both partners. Einstein himself was not always attentive to his wife's emotional needs, being prone to absorption in his theoretical work to the exclusion of domestic concerns, and Maleeva's increasingly bitter unhappiness created an atmosphere in their home that was far from the peaceful domestic haven that might have supported Einstein's intellectual labors. The Prague years thus represent a period of personal difficulty running parallel to professional achievement, a reminder that the life of even the most brilliant scientist remains embedded in the ordinary human circumstances of family and relationship and emotional need. The theoretical work that Einstein accomplished during the Prague period, particularly the 1911 paper with its predictions of gravitational redshift and light deflection, represented an important stage in the development of his thinking about gravitation, though the theory he had at this point remained incomplete in crucial respects. The value he calculated for light deflection, 0.83 arc-seconds for starlight grazing the Sun, was based on his current understanding of how gravity affects light, but this understanding was itself provisional and would be substantially revised as he continued to develop his ideas. In particular, Einstein had not yet incorporated into his theory the full geometric description of gravitation that would become the hallmark of general relativity as finally completed in 1915, and his calculations at this stage relied on a simpler framework that captured some but not all of the effects that a complete theory would describe. The prediction of light bending was correct in its qualitative claim that gravity would deflect light, but the quantitative magnitude Einstein calculated in Prague would turn out to be exactly half of the final value that general relativity would predict, a discrepancy that reflected the incompleteness of his theoretical framework at this intermediate stage of development. This circumstance would later prove fortunate for Einstein's reputation, though at the time he could not have known that his early prediction contained this error. Expeditions organized to test the light deflection prediction during solar eclipses in the years immediately following the Prague paper were prevented by various circumstances, including unfavorable weather and the outbreak of war in 1914, from obtaining definitive results. Had these early expeditions succeeded in making precise measurements, they might have found deflections inconsistent with Einstein's 1911 prediction, which could have cast doubt on his entire theoretical approach and complicated the reception of the completed theory when it finally emerged. Instead, the delays meant that the first successful measurements came only after Einstein had completed general relativity and revised his prediction to the correct value of approximately 1.75 arc-seconds, double his earlier estimate. The observations made during the eclipse of 1919 confirmed this larger value, providing dramatic support for the completed theory and making Einstein famous throughout the world. Einstein's time in Prague lasted only about 16 months, from April of 1911 until the summer of 1912, when he accepted a position at his alma mater, the Zurich Polytechnic, returning to the Swiss city where he had been a student and where he and Maleeva had first met. The decision to leave Prague reflected several factors, including the opportunity to return to a more congenial environment, the chance to work more closely with his mathematician friend Marcel Grossmann, who was now a professor at the Polytechnic, and perhaps also the hope that a change of location might improve the domestic situation that had become so difficult in Prague. The Prague Interlude thus represents a relatively brief but significant chapter in Einstein's life, a period of professional advancement and theoretical progress combined with personal strain and domestic unhappiness, a time when he moved closer to the great theoretical achievement that still lay 3 years in the future, while also moving further from the marriage that had once seemed to promise a lifetime of shared intellectual adventure. The city of Prague, with its medieval spires and its modern intellectual life, with its park of wandering asylum patients visible from his office window and its coffee houses where physicists and philosophers and writers gathered to discuss the great questions, had provided Einstein with an environment that stimulated his thinking even as it failed to satisfy his wife or to offer a permanent professional home. The work he accomplished there, particularly the paper predicting observable gravitational effects, helped to transform his theoretical speculations into scientific proposals that could be tested against the behavior of the actual universe, setting the stage for the eventual triumph of general relativity and the confirmation that would make Einstein the most famous scientist in the world. And the conversations he had there, with young astronomers eager to test his predictions and with philosophers interested in the foundations of physical knowledge and with writers curious about the nature of creativity and discovery, enriched his understanding of the broader significance of scientific work even as he remained focused on the specific technical problems that his gravitational theory still needed to solve. And so we come now to the question of mathematics, to the tools and techniques that would eventually allow Einstein to express his physical intuitions in precise and workable form, and this is a part of the story that unfolds with a certain quietness, a tale of collaboration and of one man recognizing the limits of his own expertise and reaching out to an old friend for help, which is perhaps one of the more humanizing aspects of this entire decade of work. Einstein was, by training and by temperament, a physicist rather than a mathematician, and this distinction, which might seem rather fine to those outside these fields, carried with it real consequences for the kind of work he could accomplish on his own, for the mathematics that would prove necessary to describe curved spacetime was of a sophistication and abstraction that lay well beyond what Einstein had learned in his student days, and indeed beyond what most physicists of that era would have encountered in their ordinary work, and so there came a point, sometime around 1912, when Einstein found himself in possession of profound physical insights but lacking the mathematical language to give them proper expression, rather like a poet who senses the shape of what he wishes to say but finds that the words of his native tongue are simply insufficient to capture the meaning. It is worth pausing here to understand something of Einstein's relationship with mathematics up to this point in his career, for he had not been, as a student, particularly devoted to the mathematical side of physics, preferring instead to focus on the physical concepts and to use mathematics only insofar as it served to express those concepts, and his mathematics professors at the ETH Zurich, the Swiss Federal Polytechnic, had not been especially impressed with his diligence in their courses, with Hermann Minkowski, who would later contribute so importantly to the mathematical formulation of special relativity, reportedly calling the young Einstein a lazy dog, though this was said with some affection, and Einstein himself later acknowledged that he had not fully appreciated the importance of mathematics in his student years, a circumstance he would come to regard with some regret as his work progressed into more demanding territory. The Special Theory of Relativity, published in 1905, had required mathematics that was relatively accessible, involving algebra and calculus of the sort that any well-trained physicist would know, and even the four-dimensional spacetime formulation that Minkowski contributed in 1908 used mathematical structures that, while elegant and somewhat unfamiliar, were not fundamentally beyond the reach of a physicist willing to learn them, but the general theory, the theory that would encompass gravity and acceleration and the curvature of spacetime itself, this demanded something far more sophisticated, something that Einstein did not possess and could not easily acquire through self-study alone. And so we arrive at the year 1912, when Einstein returned to Zurich to take up a professorship at his alma mater, the ETH, and found himself once again in the company of Marcel Grossmann, who had been a close friend during their student days and who was now a professor of mathematics at the same institution, and this reunion would prove to be of considerable importance to the development of general relativity, for Grossmann possessed precisely the mathematical knowledge that Einstein lacked, and more than that, he possessed a willingness to help his old friend navigate the difficult terrain that lay ahead. Marcel Grossmann had been a diligent and organized student, in contrast to Einstein's more irregular approach, and during their student years Grossmann had shared his careful lecture notes with Einstein, allowing Einstein to pass his examinations despite his somewhat spotty attendance, and so there was already between them a history of intellectual generosity, a pattern of Grossmann providing Einstein with the tools he needed to succeed, and this pattern would now repeat itself on a much grander scale, with Grossmann introducing Einstein to an entire branch of mathematics that would prove essential to the general theory. The conversation between them, or rather the series of conversations that took place in 1912, began with Einstein explaining his physical problem, explaining that he needed a way to describe how the geometry of space and time could vary from place to place, how it could curve and bend in response to the presence of matter, and Grossmann, listening to this description, recognized that what Einstein was describing had connections to mathematical work that had been done decades earlier, work on the geometry of curved spaces that had begun with the German mathematician Bernhard Riemann and had been developed further by Italian mathematicians in the years since, and Grossmann reportedly responded to Einstein's plea for help by saying that he would look into it, that he would search through the mathematical literature to see what might be of use. There is a phrase attributed to Einstein from this period, addressed to Grossmann, in which Einstein said, "In essence, you must help me or I will go crazy," and while we cannot know the precise words that were used, the sentiment is clear enough, that Einstein was struggling with a problem that seemed to require mathematics beyond his reach, and that he was turning to his friend with something approaching desperation. And this moment of reaching out, of acknowledging the need for help, is rather touching in its way, showing us that even the most celebrated minds have their limitations and that great work often emerges from collaboration rather than solitary genius. And so Grossmann went to the library, as mathematicians do, and began to search through the accumulated knowledge of his field, and what he found there, and brought back to Einstein, was a body of work that had its origins in a lecture delivered in 1854 in the German university town of Göttingen, a lecture that had been delivered by a young mathematician named Bernhard Riemann and that had, in the decades since, grown into a substantial branch of mathematics, though one that was still known mainly to specialists and had not yet found significant application in physics. Bernhard Riemann's lecture of 1854, delivered as part of his qualification for a university position, bore the title On the Hypotheses Which Lie at the Foundations of Geometry, and it represented a profound departure from the geometry that had been handed down from the ancient Greeks, the geometry of Euclid that had seemed for centuries to be the only possible way of describing space. And in this lecture Riemann proposed that one could imagine spaces of any number of dimensions, with geometrical properties that varied from point to point, spaces that might be curved in ways that were impossible to visualize but that could be described precisely through mathematical formulas, and this was, in a sense, Exactly what Einstein needed: a mathematical framework for talking about spaces whose geometry was not fixed and uniform but could change and curve in response to physical circumstances. Riemann had been a student of Carl Friedrich Gauss, who had himself done important work on the geometry of curved surfaces, showing how to describe the intrinsic curvature of a surface without reference to any higher dimensional space in which it might be embedded, and Riemann extended this work to spaces of higher dimensions, developing the concept of what we now call a Riemannian manifold, a space equipped with a way of measuring distances and angles that could vary smoothly from point to point. And while Riemann himself died young, at the age of 39, the mathematical tradition he founded continued to develop in the hands of others. Among those others were the Italian mathematicians Gregorio Ricci-Curbastro and his student Tullio Levi-Civita, who worked at the University of Padua in the closing years of the 19th century and the opening years of the 20th, and who developed what they called the absolute differential calculus, a systematic method for doing calculations in the curved spaces that Riemann had described, and this method, which we now call tensor calculus, provided a way of writing equations that would take the same form regardless of what coordinate system one used to describe the space, a property that would prove essential for Einstein's purposes, since he wanted physical laws that would hold true for all observers regardless of their state of motion or the coordinates they used. The word tensor, which may be unfamiliar, refers to a mathematical object that generalizes the concepts of scalars and vectors, and while a complete explanation of tensors would take us rather far afield, it is enough for our purposes to say that tensors provide a way of describing quantities that have both magnitude and direction in multiple dimensions simultaneously, and that they transform in specific predictable ways when one changes coordinate systems, and that this property of predictable transformation is what makes them so useful for describing physical laws in a way that does not depend on the arbitrary choice of coordinates. Grossman introduced Einstein to this entire body of work, to Riemann's geometry and to the tensor calculus of Ricci-Curbastro and Levi-Civita, and while the learning was difficult, Einstein began to see that here at last was the mathematical language he needed, a way of describing curved spacetime and the physical processes occurring within it, and the collaboration between the physicist and the mathematician began in earnest, with Einstein providing the physical insight and Grossman providing the mathematical technique, each contributing what the other lacked. One of the key mathematical objects that Grossman brought to Einstein's attention was what we now call the Christoffel symbols, named after the German mathematician Elwin Bruno Christoffel, who had introduced them in 1869, and these symbols, which are not tensors themselves but which appear in the formulas for how tensors change from point to point, play an essential role in describing how to do calculus in curved spaces, how to take derivatives of quantities that live in a space whose geometry varies from place to place, and understanding these symbols and how to work with them was one of the mathematical challenges that Einstein had to overcome. Another crucial object was the Ricci tensor, developed by Ricci-Curbastro as a way of capturing certain aspects of the curvature of a space, and this tensor, which is derived from the more complete Riemann curvature tensor by a mathematical process called contraction, would eventually appear in the final form of Einstein's field equations, though the path to that final form was neither straight nor easy, and there were many false turns and abandoned approaches along the way. The year 1913 saw the publication of a joint paper by Einstein and Grossman, often referred to as the Entwurf paper, the word Entwurf meaning outline or draft in German, and this paper represented their first attempt to put together a complete theory of gravity based on the new mathematical framework, and while the theory presented in this paper was not quite correct, it was an important step along the way. showing that the general approach was promising even if the specific equations needed further refinement. The Entwurf theory, as it came to be known, used the metric tensor to describe the geometry of spacetime, and it proposed equations relating this geometry to the distribution of matter and energy, but the equations were not quite right, in the sense that they did not possess the full generality that Einstein was seeking. They were not fully covariant, meaning they did not take the same form in all coordinate systems, and this troubled Einstein, though for a time he convinced himself that the restriction was acceptable, that physical considerations required the equations to hold only in certain special coordinate systems. This period of Einstein's work, from 1912 through 1915, is documented in remarkable detail by a set of notebooks that Einstein kept, in which he recorded his calculations and his various attempts at finding the correct equations, and these notebooks, which were not widely known until they were carefully studied by scholars in the 1980s, reveal the difficulty of the mathematical work that Einstein was attempting, showing page after page of calculations, many of them crossed out or abandoned, as Einstein struggled to find his way through the thicket of indices and symbols and transformation rules. The Zurich notebook, as one of these documents is known, contains calculations from 1912 and 1913, and it shows that Einstein actually considered and then rejected the correct field equations at one point, writing them down and then discarding them for reasons that are not entirely clear, perhaps because he believed they did not correctly reduce to Newtonian gravity in the appropriate limit, or perhaps because he made errors in his calculations. And this is a poignant reminder that the path of discovery is rarely smooth, that even the greatest scientists can come close to the truth and then turn away from it, only to return later by a different route. The mathematical difficulties that Einstein faced were genuine and substantial, and it is worth appreciating that the tensor calculus, while systematic, is also remarkably complex in its details, with quantities that carry multiple indices and that must be manipulated according to precise rules, and a single error in these manipulations can lead to conclusions that are entirely wrong, and Einstein made many such errors in the course of his work, as the notebooks clearly show, and had to go back and correct them, sometimes recognizing his mistakes only after considerable time had passed. Marcel Grossmann's contribution to this work should not be underestimated, for while Einstein provided the physical vision, it was Grossmann who provided the mathematical foundation, who taught Einstein the techniques he needed and who helped him navigate the literature on differential geometry, and the collaboration between them was genuinely complementary, each man contributing what the other could not easily have provided alone. And while Grossmann's name is not as widely remembered as Einstein's, his role in the development of general relativity was essential. The Entwurf paper of 1913 was followed by several years of further work, during which Einstein both defended the Entwurf theory and gradually came to recognize its shortcomings, and these years were filled with mathematical labor of the most demanding kind, as Einstein sought to understand the full implications of the equations he and Grossmann had proposed and to compare them with what physical intuition suggested the correct theory should predict. And it was through this long process of calculation and comparison that Einstein eventually found his way to the final form of the field equations, which he presented in November of 1915. But we are getting ahead of ourselves, and it is enough for now to appreciate the mathematical turning point that occurred in 1912, when Einstein recognized that he needed help and reached out to his old friend, and when Grossmann responded by introducing Einstein to a mathematical tradition that had been developing for more than half a century, waiting, as it were, for a physical application worthy of its sophistication. And this meeting of physical intuition and mathematical technique, of Einstein's vision and Grossman's knowledge, was essential to the development of general relativity. The mathematics of curved spaces, of tensors and differential geometry, is not easy, and Einstein's struggles with it were real, and the notebooks from this period show us a man working at the very edge of his abilities, making errors and correcting them, trying one approach and then another, gradually building up the mathematical skill that would eventually allow him to complete his theory, and there is something reassuring in this, something that reminds us that great achievements often require great effort, that even the most brilliant minds must work hard to master difficult material, and that the final elegant result often emerges only after years of labor. The tools that Riemann and Christoffel and Ricky Kurbastro and Levi Civita had developed, each working on problems that seemed at the time to be purely mathematical, problems of curved surfaces and abstract spaces and generalized coordinates, these tools found in Einstein's hands a physical application that none of their creators had foreseen, and this is one of the curious features of the relationship between mathematics and physics, that mathematical structures developed for their own sake sometimes turn out, years or decades later, to be exactly what is needed to describe some aspect of the physical world. And so Einstein, with Grossman's help, learned to think in terms of tensors, learned to work with the metric tensor that encodes the geometry of spacetime, learned to manipulate Christoffel symbols and Ricci tensors, learned to write equations that would hold in any coordinate system, and this mathematical education, difficult as it was, gave him the tools he needed to complete his theory, though the final steps, as we shall see, required several more years of work and a return to the correct equations that he had once considered and rejected. For now, it is enough to rest with this image of collaboration and of learning, of two old friends working together at the ETH Zurich, one a physicist with a revolutionary vision and the other a mathematician with the knowledge to help realize that vision, and between them creating the mathematical foundations for a new understanding of space and time and gravity, an understanding that would change how we think about the universe and our place within it. In the summer of 1912, Albert Einstein returned to the city of Zurich, a place that held for him many memories of his student days, his early struggles, and the friendships that had sustained him through years of uncertainty and intellectual wandering. He came back not as the young man who had once sat in lecture halls wondering about the nature of light and motion, but as a professor of theoretical physics at the very institution that had trained him, the Eidgenössische Technische Hochschule, which we may simply call the ETH or the Polytechnic, and which now welcomed him to its faculty with a position of considerable prestige. The appointment began officially in July of that year, and Einstein settled into his new role with a mixture of satisfaction and restless determination, for he carried with him an unfinished project that had consumed his thoughts for several years and would continue to occupy the deepest regions of his mind for some time yet to come. The problem of gravity remained stubbornly unresolved in his thinking, and the months spent in Prague had shown him both the promise and the difficulty of extending the principle of relativity to accelerated frames of reference and to the phenomenon of gravitation itself. He had made progress, certainly, discovering that gravity must bend light and affect the passage of time, but the mathematical framework needed to describe these effects in their full generality continued to elude him, slipping away whenever he thought he had grasped it firmly. The equations he had developed in Prague were limited in their applicability, working only for special cases where the gravitational field was weak and static, and Einstein understood with growing clarity that something far more sophisticated would be required if he hoped to capture the true nature of gravitational phenomena in all their complexity and variety. It was at this juncture that he turned to an old friend from his student days, a mathematician named Marcel Grossmann, who had helped Einstein in practical ways during their youth and who now held a professorship in mathematics at the ETH. Grossmann was a careful and methodical scholar, gifted in precisely the areas where Einstein felt his own training had been insufficient, and the two men had maintained a warm friendship despite the different paths their careers had taken. When Einstein explained the physical requirements his theory needed to satisfy, describing how he wanted equations that would remain valid regardless of the coordinate system used to describe them, Grossmann recognized that his friend had wandered into territory that belonged to a branch of mathematics known as differential geometry, and in particular to the work of 19th-century mathematicians who had developed tools for describing curved surfaces and curved spaces of higher dimensions. The collaboration between Einstein and Grossmann began in earnest during the autumn of 1912 and continued through the winter and into the following year, with the two friends meeting regularly to discuss the mathematical structures that might serve as the foundation for a new theory of gravity. Grossmann introduced Einstein to the tensor calculus that had been developed by the Italian mathematicians Gregorio Ricci-Curbastro and Tullio Levi-Civita, a formalism that allowed one to write equations in a way that made their transformation properties under changes of coordinates immediately apparent. This was precisely what Einstein needed, for he sought equations that would look the same in every coordinate system, embodying the principle that the laws of physics should not depend on the particular way an observer chooses to label points in space and time. The tensor calculus was not easy to learn, and Einstein struggled with its unfamiliar notation and the abstract reasoning it required, but Grossmann was a patient teacher, and together they made steady progress in translating Einstein's physical intuitions into the language of differential geometry. They discovered that the curvature of space-time, which Einstein had come to believe was the proper way to represent the effects of gravity, could be described mathematically using objects called the Riemann curvature tensor and its various contractions, and they explored how these mathematical constructs might be connected to the distribution of matter and energy that produced gravitational effects. The work was demanding and often frustrating, with many false starts and abandoned approaches, but the collaboration was productive in ways that neither man could have achieved alone. By the spring of 1913, Einstein and Grossmann had produced a draft of their theory, which they prepared for publication under the title that translates roughly as Outline of a Generalized Theory of Relativity and of a Theory of Gravitation. This paper, which has come to be known as the Entwurf theory from the German word for outline or draft, appeared in the summer of 1913 and represented the most ambitious attempt yet to extend the principle of relativity to include gravity and acceleration. The paper was divided into two parts, with Einstein writing the physical sections that explained the motivation and interpretation of the theory, while Grossmann contributed the mathematical portions that laid out the tensor formalism and derived the relevant equations. It was a substantial work, running to many pages, and it attracted considerable attention from physicists and mathematicians who were following Einstein's efforts with interest and curiosity. Yet the Entwurf theory, for all its sophistication and ambition, was flawed in a fundamental way that would take Einstein nearly 3 more years to understand and correct. The central problem was that the field equations of the Entwurf theory were not generally covariant, which is to say that they did not maintain their form under arbitrary transformations of the coordinate system. This might seem like a technical issue of interest only to mathematicians, but it struck at the heart of what Einstein had been trying to achieve, for he had wanted a theory in which the laws of gravity would be expressed in a way that was completely independent of the particular coordinate system an observer might choose to use. If the equations changed their form when one switched from one set of coordinates to another, then there was a sense in which the theory was not truly general, not truly freed from the arbitrary choices that went into labeling the points of spacetime. Einstein was aware of this limitation from the beginning, and it troubled him, but he convinced himself through a line of reasoning that came to be known as the whole argument, or in German the Log-Betrachtung, that general covariance was not merely difficult to achieve but was in fact impossible, at least for any theory that hoped to describe the real physical world. The whole argument went something like this, though we need not concern ourselves overmuch with its technical details at this restful hour. Einstein imagined a region of spacetime, which he called a whole, in which there was no matter present, and he considered what would happen if one applied a general coordinate transformation that was the identity outside this region but different inside it. He reasoned that if the field equations were generally covariant, then the transformed solution would also be a valid solution, but the two solutions would assign different physical properties to the same points of spacetime, which seemed to Einstein to be an unacceptable ambiguity in the theory. How could the laws of physics allow such freedom, permitting different physical situations to correspond to what should be the same underlying reality? This argument, which Einstein found thoroughly convincing for several years, led him to accept the restricted covariance of the Entwurf theory as not merely a defect but as a necessary feature of any physically meaningful theory of gravity. He believed he had discovered a deep truth about the nature of spacetime and the limits of what coordinate transformations could mean physically, and this belief allowed him to continue developing the Entwurf theory without being paralyzed by its failure to achieve the full generality he had originally sought. In retrospect, the whole argument was based on a subtle confusion about the meaning of coordinates and the identity of points in spacetime, a confusion that Einstein would eventually resolve, but for now it served as a kind of intellectual scaffolding that allowed him to make progress even as it constrained his thinking in important ways. During these years in Zurich, Einstein lectured to students at the ETH on various topics in physics, including the developing ideas of his work on gravitation, and he found that teaching helped him to clarify his own understanding even as it consumed time and energy that might otherwise have gone into research. His lectures were not always polished or well organized, for Einstein tended to think aloud and to pursue interesting tangents as they occurred to him, but students who were willing to follow his unconventional approach found his courses stimulating and memorable. He spoke with a quiet intensity about the problems that occupied his mind, sketching equations on the blackboard and pausing frequently to consider whether he had expressed his ideas correctly, and those who attended his lectures came away with a sense that they were witnessing the creative process of a remarkable mind at work on fundamental questions. Einstein's reputation had grown substantially since his miraculous year of 1905, and by the time he returned to Zurich, he was recognized as one of the leading theoretical physicists of his generation, someone whose ideas were worth taking seriously even when they seemed strange or difficult to accept. Visitors came to Zurich to meet him and to discuss physics, and among these was Paul Ehrenfest, an Austrian physicist of great warmth and intellectual energy who would become one of Einstein's closest friends and most valued correspondents. Ehrenfest had a gift for penetrating to the heart of a physical problem and for expressing complex ideas with clarity and directness, and his conversations with Einstein were marked by a lively exchange of ideas and a mutual respect that deepened over the years into genuine affection. The two men would remain close for the rest of Ehrenfest's life, supporting each other through professional challenges and personal difficulties with a loyalty that was rare and precious. Other physicists visited as well, drawn by Einstein's growing fame and by the importance of the problems he was working on, and the apartment in Zurich became a place where scientific ideas were discussed and debated with passion and rigor. Einstein enjoyed these visits, for he thrived on intellectual exchange and found that conversation often helped him to see his own ideas more clearly, and he was generous with his time and attention even when the demands of work and family left him exhausted. He corresponded extensively with colleagues throughout Europe, exchanging letters that ranged from technical discussions of specific calculations to broader reflections on the meaning and direction of physics, and these letters provide a window into his thinking during this crucial period of his intellectual development. Yet not all was well in Einstein's life, for his marriage to Mileva had become increasingly strained, and the domestic atmosphere in their home was often tense and unhappy. The reasons for this estrangement were complex and perhaps not fully understood even by the two people most directly involved, but it is clear that the demands of Einstein's work and the intensity of his intellectual focus left little room for the emotional connection that Mileva needed, while Mileva's own disappointments and difficulties created a climate of resentment and withdrawal that Einstein found oppressive. They had two sons, Hans Albert, who had been born in 1904, and Eduard, who had arrived in 1910, and the boys were caught in the middle of their parents' unhappiness, loved by both but unable to bridge the growing distance between them. Einstein was not an attentive father in the conventional sense, for his mind was often elsewhere, absorbed in calculations and concepts that had nothing to do with the daily life of a family, but he cared for his sons in his own way and took pleasure in their company when he could bring himself to be present with them. Hans Albert was old enough to sense that something was wrong between his parents, and the tension in the household affected him in ways that would shape his relationship with his father for years to come. Eduard was younger and perhaps less aware of the difficulties, but he too would come to bear the marks of a childhood spent in a home where love had curdled into something more complicated and painful. The details of the Einstein's domestic troubles need not detain us further at this peaceful hour, but it is worth noting that the great intellectual achievements of this period were accomplished against a background of personal unhappiness that must have added to the burden Einstein carried. In the summer of 1913, Einstein received a visit that would change the course of his career and eventually lead him away from Zurich to a new chapter in his life. Max Planck and Walther Nernst, two of the most eminent scientists in Germany, traveled to Zurich with a proposal that was designed to be irresistible. They came as representatives of the Prussian Academy of Sciences and the University of Berlin, and they brought with them an offer of a position that was unprecedented in its generosity and its recognition of Einstein's unique gifts. The position would make Einstein a member of the Prussian Academy, with a substantial salary and complete freedom to pursue his research without any obligation to teach or to fulfill administrative duties. He would also be offered a professorship at the University of Berlin, but attendance at lectures would be entirely at his discretion, and he could devote himself wholly to the theoretical work that was his true calling. Planck was the elder statesman of German physics, the man who had introduced the quantum hypothesis that had revolutionized the understanding of thermal radiation and had set Einstein's own career in motion with the light quantum paper of 1905. Nernst was a distinguished physical chemist who had made important contributions to thermodynamics and who recognized in Einstein a mind of the first rank. Together they represented the pinnacle of the German scientific establishment, and their journey to Zurich was a mark of the extraordinary esteem in which Einstein was held. They wanted him in Berlin, at the center of European physics, where his presence would add luster to an already distinguished community of scholars and where he would have every resource he needed to complete the work on gravitation that occupied his thoughts. Einstein considered the offer carefully, for it was not a decision to be made lightly. There were advantages to remaining in Zurich, where he had friends and colleagues and the comfortable familiarity of a city he had known since his student days, and there was something troubling about the prospect of moving to Prussia, a country whose militarism and nationalism Einstein found distasteful. But the terms of the Berlin offer were extraordinarily attractive, promising him the freedom from teaching that would allow him to focus entirely on his research, and the scientific environment in Berlin was unmatched anywhere in the world. Planck and Nernst waited for his answer, having arranged to take a walk in the nearby mountains while Einstein deliberated, and it is said that Einstein indicated his decision by the color of the rose he carried when they returned, though whether this charming detail is strictly accurate matters little for our purposes. He accepted the offer, and arrangements were made for his move to Berlin, which would take place in the spring of 1914. The months that followed were filled with preparations for this transition, with continuing work on the Entwurf theory, and with the ongoing difficulties of his personal life, but Einstein faced the future with a mixture of anticipation and determination that carried him through the challenges of this period. He did not know, could not have known, what awaited him in Berlin or how the events of the next few years would transform both his theory and the world around him, but he moved forward with the quiet confidence of a man who understood his own abilities and who trusted in the value of the work he had set himself to do. The Entwurf theory, despite its limitations, represented a significant advance in the understanding of gravity, and Einstein continued to develop and defend it even as he prepared to leave Zurich. He believed he was on the right track, that the basic physical ideas were correct even if the mathematical formulation needed further refinement, and he was not yet ready to abandon the work he and Grossman had done together. The whole argument still seemed to him a compelling reason to accept the restricted covariance of his equations, and he would not recognize its fallacy until circumstances forced him to reconsider his approach from the ground up. For now, he rested in the confidence that he had made important progress, and he looked forward to the opportunities that Berlin would provide for completing the theory that had occupied so many years of his life. And so the Zurich period drew toward its close, with Einstein poised between the world he was leaving and the world he was about to enter, between a marriage that had lost its warmth and a professional opportunity that promised unlimited scope for his ambitions. The Entwurf theory stood as a monument to what he and Grossman had achieved together, flawed but substantial, a stepping stone toward something greater that still lay hidden in the mathematics of curved spacetime. In the gentle rhythm of days and seasons, in the quiet accumulation of understanding through patient effort and persistent questioning, the work continued, as it always does, moving toward clarity through confusion, toward light through darkness, toward the simple and beautiful truths that wait to be discovered by those who have the patience and the courage to seek them. And now we come to a rather lovely thought experiment, one involving a simple rotating disk, the kind you might imagine as a great flat turntable spinning steadily in empty space. This humble mental picture, so easy to conjure in the mind's eye, would prove to be one of the most important stepping stones on Einstein's long path toward general relativity. It helped him understand something quite profound, namely that gravity and curved geometry are deeply, inextricably connected, and that the familiar flat geometry of Euclid, which we learn in school and which seems so obviously true, cannot be the whole story when gravity and acceleration enter the picture. Let us begin by setting the scene as it unfolded in the years following Einstein's special theory of relativity in 1905. That earlier theory had transformed our understanding of space and time for observers moving at constant velocities relative to one another, but it said nothing about acceleration, nothing about gravity, and nothing about rotating reference frames. These were gaps that Einstein knew he would eventually need to fill, and the rotating disk would become his gentle guide into unfamiliar territory. The story really begins with a paradox, a puzzle that troubled physicists in the years immediately following special relativity. In 1909, the Dutch physicist Paul Ehrenfest, who was a thoughtful and deeply inquisitive man, published a short paper describing what seemed like a genuine contradiction involving rotating rigid bodies. Ehrenfest asked a deceptively simple question about what happens when you try to set a disk spinning according to the rules of special relativity. His paradox, which came to be known as Ehrenfest's paradox, went something like this. Imagine a perfectly rigid disk at rest. Now imagine gradually spinning it up, faster and faster, until it reaches some constant angular velocity. According to special relativity, objects moving relative to an observer undergo length contraction along the direction of their motion. For a spinning disk, the outer rim is moving quite fast, tracing out a circular path, and so the circumference of the disk, being oriented along the direction of motion, should contract. But here is the puzzle. The radius of the disk points from the center outward, perpendicular to the rim's motion, and lengths perpendicular to the direction of motion do not contract according to special relativity. So the radius should remain unchanged. But this creates an impossible situation for a rigid body. If the circumference contracts while the radius stays the same, the disk cannot hold together in its original shape. It would have to buckle or tear or somehow reconfigure itself in ways that seem to violate the very notion of rigidity. Ehrenfest's paradox showed that the concept of a perfectly rigid body, so useful in classical physics, simply cannot exist in special relativity. The very act of spinning up a disk forces it to change shape in complicated ways that depend on how the material responds to stress. There is no such thing as a relativistic rigid disk that can be set into rotation from rest. This puzzle attracted the attention of several physicists, including Max Born, who was working at Göttingen during this period. Born was a careful and mathematically sophisticated thinker who would later make fundamental contributions to quantum mechanics, but in these earlier years he devoted considerable effort to understanding relativistic mechanics. In 1909 and the years that followed, Born developed a rigorous definition of what it might mean for a body to move rigidly in special relativity, and he showed that the conditions for rigid motion are extremely restrictive. A disk at rest cannot be rigidly accelerated into rotation, and Born's work helped clarify the mathematical landscape surrounding these problems. His analysis of relativistic rigid bodies became part of the intellectual background that Einstein drew upon as he thought about rotating reference frames. Einstein corresponded about these matters with Arnold Sommerfeld, the great Munich physicist who was both a friend and a respected colleague. Sommerfeld had a remarkable gift for training young physicists and for engaging with the most difficult problems in theoretical physics, and he and Einstein exchanged letters discussing the rotating disk and related puzzles. In their correspondence, Einstein worked through his thinking about what the rotating disk really implied for geometry and for the nature of space itself. These letters reveal Einstein grappling with ideas that were still fuzzy and unformed, trying to articulate insights that he could feel but not yet express with full mathematical clarity. Now let us turn to Einstein's own version of the rotating disk thought experiment, the Gedanken experiment that would prove so illuminating. Einstein asked us to imagine the disk already spinning at a constant rate, and to consider observers living on that disk, making measurements with their own rulers and clocks. He was not concerned with how the disk got spinning, which was Ehrenfest's puzzle, but rather with what geometry those rotating observers would discover when they tried to measure the disk's dimensions. Consider first an observer sitting at the very center of the disk, at the axis of rotation. This observer is not moving at all, or at least not in any way that matters for our purposes, and so for this central observer, the geometry of the disk should appear perfectly normal and Euclidean. If this observer reaches out with a ruler to measure radii extending from the center toward the rim, those measurements should be straightforward and unaffected by the rotation. But now consider an observer stationed out near the rim of the disk, riding along as it spins. This observer is moving quite fast, tracing out a circle with each revolution, and for this observer special relativity tells us that clocks run slow and rulers contract along the direction of motion. The direction of motion for the rim observer is tangential, around the circle, and so any ruler laid along the circumference of the disk will be length contracted from the perspective of a non-rotating observer watching from outside. Here is where the Gedanken experiment becomes revealing. Imagine the rim observer tries to measure the circumference of the disk by laying down small rulers end to end all around the circle. Each small ruler, being aligned with the direction of motion, is contracted. To cover the same physical distance around the rim requires more of these contracted rulers than it would require for rulers at rest. When the rim observer counts how many rulers fit around the circumference and multiplies by the length each ruler is supposed to be, the result will be a circumference that appears larger than expected. Now imagine the same observer measures the diameter of the disk, laying rulers from one edge through the center to the opposite edge. The radii point outward, perpendicular to the direction of motion, and so these rulers do not contract. The measured diameter remains the same as it would be for a non-rotating disk. And here we arrive at the crux of the matter. For ordinary Euclidean geometry, the one we all learned in school, the circumference of a circle is always pi times the diameter, where pi is that familiar constant approximately equal to 3 14/100. But for observers on the rotating disk, the circumference comes out to be greater than pi times the diameter. The ratio of circumference to diameter is no longer the constant pi. The geometry of the rotating disk, as experienced by observers living on it, is non-Euclidean. This was a profound realization for Einstein. The rotating disk is an accelerating reference frame, not an inertial one, and yet the equivalence principle told him that there should be no way to distinguish locally between acceleration and gravity. If observers on a rotating disk experience a kind of pseudogravity, an outward centrifugal effect that feels like a gravitational pull toward the rim, and if these same observers discover that their geometry is non-Euclidean, then perhaps real gravity is also associated with non-Euclidean geometry. Perhaps the presence of mass and energy curves space itself, or more accurately curves space-time, and this curvature is what we experience as gravity. The rotating disk was not a perfect analogy for gravity, and Einstein knew this. The pseudo-gravitational field on a rotating disk points outward, not inward like the gravity of a massive body, and the disk has rotational symmetry that real gravitational fields need not possess. But the thought experiment was a conceptual bridge, a way of seeing that the familiar flat geometry of Euclid might not apply in situations involving gravity and acceleration. It suggested that the mathematical tools needed to describe gravity would have to include non-Euclidean geometry, the curved geometries developed by mathematicians like Gauss and Riemann in the 19th century. Einstein later recalled how important the rotating disk was for his thinking. It convinced him that he could not simply modify Newtonian gravity within the framework of special relativity and flat spacetime. Something more radical was needed. Spacetime itself would have to become a dynamical entity, capable of curving and bending in response to the presence of matter and energy. The geometry of spacetime would no longer be a fixed stage on which physics plays out, but an active participant in the drama, shaped by and shaping the motion of everything within it. As Einstein worked through these ideas in the years between 1907 and 1912, he encountered deep conceptual difficulties about what coordinates really mean in a theory where geometry is not fixed in advance. In ordinary physics, and in special relativity, coordinates are labels we attach to points in space and time. We can imagine a grid of rulers and clocks filling all of space, and the coordinates of an event are simply the readings on the nearest rulers and clocks. This works beautifully when spacetime is flat and Euclidean, when geometry is the same everywhere, but it becomes deeply problematic when spacetime is curved. On a curved surface, like the surface of a sphere, there is no way to lay down a flat grid of coordinates that works everywhere without distortion. Any coordinate system on a curved surface will have peculiarities, places where the coordinates behave strangely or where the relationship between coordinate differences and actual distances becomes complicated. Einstein realized that in a generally covariant theory, a theory that treats all coordinate systems on equal footing, the coordinates themselves lose their direct physical meaning. They become mere labels, arbitrary tags attached to events, and the physics must be expressed in a way that does not depend on which labels you choose. This was a difficult pill to swallow. It meant that statements like the position of this event is x equals 5 and t equals 3 would become almost meaningless on their own. Only relationships between events, described by geometric quantities that do not depend on the choice of coordinates, would have physical content. Einstein struggled with this for years, sometimes thinking he understood it and then realizing he had slipped back into treating coordinates as if they were physical things. His correspondence and notebooks from this period show him circling around these ideas, making progress and then backtracking, until he finally achieved the necessary level of abstraction. The rotating disk helped clarify some of this because it provided a concrete example where naive coordinate thinking goes wrong. If you try to describe the rotating disk using the coordinates of an inertial observer watching from outside, the geometry looks flat, but the physics on the disk involves strange pseudoforces. If you try to use coordinates fixed to the rotating disk itself, the physics looks simpler in some ways, with the pseudogravity appearing naturally, but the geometry is non-Euclidean. Neither coordinate system is wrong, but they describe the same physical situation in very different languages. The physics must be independent of which language you choose, and finding the right mathematical framework to express this independence was part of Einstein's great challenge. By around 1912, Einstein had become convinced that he needed to learn differential geometry, the mathematics of curved spaces developed by Riemann and others. This was not a subject he knew well, and he would need help from his mathematician friend Marcel Grossmann to find his way through the formalism. But the conceptual insight from the rotating disk, that gravity and curved geometry are connected, remained his guiding light. The disk showed him that spacetime geometry could vary from place to place, that the familiar flat geometry of special relativity was only an approximation valid far from gravitating masses and in non-accelerating reference frames, and that a new kind of theory would be needed to describe the full picture. The rotating disk thought experiment is a gentle one, easy to picture and requiring no advanced mathematics to grasp its basic message. A spinning disk, observers with rulers, and a circumference that comes out larger than pi times the diameter. From this simple image, Einstein glimpsed the curved geometry of spacetime that would eventually become the foundation of general relativity. The path from this insight to the final field equations of November 1915 was still long and difficult, filled with wrong turns and abandoned approaches, but the disk had pointed the way. It showed that Euclid's geometry, for all its elegance and apparent certainty, was not the last word on the structure of space and time. In the presence of gravity, space curves, time bends, and the geometry of the universe is richer and stranger than any flat grid could capture. And so the rotating disk takes its place among the great Gedanken experiments of physics, alongside falling elevators and chasing light beams, as one of the simple mental pictures that helped Einstein reshape our understanding of the cosmos. It is a quiet thought experiment, requiring no dramatic collisions or exotic particles, just a disk spinning steadily in space and observers carefully measuring circumferences and diameters. From this humble beginning, the curved spacetime of general relativity would eventually emerge, a theory in which gravity is geometry and the universe itself is a dynamic, curving manifold that we are still exploring today. In the spring of 1914, Albert Einstein made the journey from Zurich to Berlin, a move that would place him at the very center of German scientific life, and one that carried with it both tremendous professional opportunity and profound personal consequence. He arrived in April of that year, settling into a city that was, at that moment, still at peace, though the summer months would bring changes that no one could yet fully imagine. Berlin in those final months before the Great War was a metropolis of considerable energy and ambition, a place where science and industry and imperial confidence all mingled together in the broad avenues and imposing institutional buildings that characterized the Prussian capital. For Einstein, then 35 years old, the move represented a kind of homecoming to German soil, though his feelings about Germany and German culture had always been complicated, marked by an ambivalence that would deepen considerably in the years ahead. The positions that awaited him in Berlin were, by any measure, extraordinary, and they reflected the high regard in which his work was already held by the leading figures of German physics. He was to become a professor at the University of Berlin, which was among the most prestigious academic institutions in the world at that time, a place where generations of distinguished scholars had taught and conducted research. But the professorship was only one part of the arrangement that had been crafted to bring him to the city, for he was also made a member of the Prussian Academy of Sciences, that venerable body which had counted among its members some of the greatest minds in the history of German learning. Membership in the Academy carried with it not only considerable prestige but also a salary, which meant that Einstein would have financial security without the burden of extensive teaching duties. This was a matter of some importance to him, for he had always found that teaching, while not without its rewards, consumed time and energy that he would rather devote to his research, and the Berlin arrangement was designed with this preference in mind. Additionally, he was named as the director of a planned Kaiser Wilhelm Institute for Physics, though this institute existed more in intention than in physical reality during those early years, and the actual building and staffing of the facility would be delayed by the war that was soon to come. The Kaiser Wilhelm Institutes were a relatively new development in the organization of German science, conceived as research centers where scholars could pursue their investigations free from the teaching obligations that typically accompanied university positions. Fritz Haber had already established himself at the Kaiser Wilhelm Institute for Chemistry, and other institutes were being planned or were already in operation, creating a network of specialized research facilities that represented a new model for the conduct of scientific inquiry. Einstein's directorship of the Physics Institute was, in practical terms, something of an honorary position during its early years, but it nonetheless added to the remarkable collection of titles and responsibilities that had been assembled to entice him to Berlin. The men who had worked to bring Einstein to the city were themselves figures of considerable stature in the world of physics. Max Planck, whose work on blackbody radiation had introduced the quantum of action into physics and had thereby opened new avenues of inquiry that Einstein himself had explored in his early papers, was a professor at the University of Berlin and a dominant figure in German scientific circles. Planck was a man of great personal dignity and conservative temperament, deeply committed to both scientific rigor and German cultural traditions, and he had recognized in Einstein a physicist of exceptional ability whose presence would enhance the reputation of Berlin as a center of theoretical physics. Walther Nernst, who had made fundamental contributions to thermodynamics and would later receive recognition for his heat theorem, was another of the Berlin scientists who had been instrumental in recruiting Einstein. Nernst was a more worldly figure than Planck, a man with interests in both pure science and practical applications, and he too saw the value of having Einstein among their number. The scientific environment of Berlin was, in many respects, ideally suited to Einstein's needs and interests. Here were concentrated some of the finest physicists in the world, men with whom he could discuss the problems that occupied his thoughts and from whom he could receive the kind of informed criticism that was so valuable in refining theoretical ideas. The seminars and colloquia of the university and the academy provided regular occasions for the exchange of ideas, and the presence of so many distinguished researchers meant that Einstein would have access to a community of peers who could appreciate the subtleties of his work. Fritz Haber, whose Institute for Chemistry was already operational, was a figure of considerable importance in Berlin scientific society, a man whose work on the synthesis of ammonia from atmospheric nitrogen would have enormous practical consequences for both agriculture and, as it happened, for the conduct of the coming war. Haber and Einstein would develop a friendship, though their views on many matters, particularly those touching on German nationalism and the proper relationship between science and military application, would prove to be quite different. The personal dimensions of Einstein's move to Berlin were, however, considerably more troubled than the professional ones. His marriage to Mileva Marek had been deteriorating for some years, and the move to Berlin brought matters to a kind of crisis. Mileva had accompanied him to the city initially, but she found the atmosphere uncongenial and her position within it uncomfortable. The relationship between husband and wife had grown cold, marked by distance and resentment, and Einstein had already begun to develop feelings for his cousin Elsa Lowenthal, who lived in Berlin and who represented a kind of domestic comfort and uncomplicated affection that his marriage no longer provided. Elsa was a divorced woman with 2 daughters, and she and Einstein had been corresponding for some time before his move to the city, their letters suggesting an emotional intimacy that had developed despite the geographical distance and despite the fact that Einstein was still married to Mileva. In July of 1914, only a few months after the move to Berlin, Mileva returned to Zurich with their 2 sons, Hans Albert and Eduard. This departure marked the effective end of the marriage, though the formal divorce would not come until some years later. The separation was painful, particularly in its effects on the children, and Einstein's relationship with his sons would remain complicated and often strained throughout his life. Hans Albert, the elder boy, was approaching his 10th birthday at the time of the separation, old enough to have some understanding of what was happening, and his feelings toward his father would long be colored by the circumstances of those years. Eduard, the younger son, was only 4 years old, and his life would later be marked by serious mental illness that would bring its own sorrows and difficulties. Before Milieva's departure, in those tense final weeks of their cohabitation in Berlin, Einstein drafted a document that set forth the conditions under which she might remain in the household. This document, which has survived and been studied by biographers, reveals something of the emotional state of the marriage and of Einstein's own complicated character. The conditions he specified were harsh and clinical, treating the arrangement more as a business matter than as anything resembling a partnership between two people who had once loved each other. He stipulated that she would be responsible for bringing meals to his room, that she would handle his laundry and keep his study and bedroom in order. He made clear that she should expect no intimacy from him, that she should not reproach him or speak to him except when social conventions required it, and that she should leave his room or study immediately upon his request. The tone of the document is cold, almost bureaucratic, setting forth the terms of what would essentially be a domestic service arrangement rather than a marriage. Reading such conditions today, one cannot help but recognize the depth of the estrangement that had developed between them, and the document stands as a reminder that great intellectual achievement does not necessarily coincide with wisdom or kindness in personal matters. Milieva did not accept these terms, and her return to Zurich with the children brought an end to their life under the same roof. She would struggle financially in the years that followed, and Einstein's support for her and the children would be a matter of ongoing negotiation and occasional conflict. When he later received the Nobel Prize, the monetary award went to Milieva and the boys, an arrangement that had been agreed upon as part of their divorce settlement and that reflected both his sense of obligation and the practical necessities of their situation. The relationship with Elsa Lowenthal continued to develop during these years, and she would eventually become his second wife, though that marriage would not take place until 1919, after the war had ended and after his divorce from Milieva was finalized. Elsa was in many ways quite different from Milieva. Where Milieva had been a fellow student of physics, intellectually engaged with the subjects that Einstein cared about most deeply, Elsa had no particular scientific training or interest. She was warm and maternal, capable of creating the kind of comfortable domestic environment that Einstein found agreeable, and she was content to manage the practical details of daily life in a way that allowed him to focus on his work. Whether this represented a complementary partnership or merely a more conventional arrangement in which the wife subordinated her own interests to those of her husband is a matter that different observers have assessed differently. The summer of 1914 brought changes far greater than those in Einstein's personal life, for the assassination of Archduke Franz Ferdinand in Sarajevo at the end of June set in motion a chain of events that would lead, within weeks, to the outbreak of war across Europe. The great powers mobilized their armies, ultimatums were issued and rejected, and by early August the conflict had begun. Germany found itself at war with France and Russia and Britain, and the enthusiasm with which many Germans greeted the onset of hostilities was, to Einstein's eyes, both bewildering and deeply troubling. The intellectual and cultural figures of Germany were caught up in the patriotic fervor just as much as the general population, and many of them lent their names and their prestige to the war effort in ways that Einstein found profoundly distasteful. In October of 1914, a document appeared that became known as the Manifesto of the 93, or the Manifesto to the Civilized World, in which 93 prominent German intellectuals, scientists, and artists defended German military actions and rejected accusations of atrocities in Belgium. The signatories included Max Planck and Wilhelm Röntgen, Fritz Haber and Walther Nernst, along with artists and writers and scholars of various disciplines. The manifesto denied German responsibility for the war, denied that German troops had committed the brutalities of which they were accused, and defended the German cause in terms that struck Einstein as both dishonest and dangerous. The willingness of so many distinguished minds to place their reputations in service of what he regarded as propaganda filled him with dismay. A counter-petition was organized, calling itself the Manifesto to Europeans, which took a very different position. This document urged intellectuals to work for peace and European unity rather than lending their support to nationalism and militarism. It called upon educated Europeans to use their influence to bring about a just peace and to prevent the cultural catastrophe that the war threatened to become. The contrast with the Manifesto of the 93 could hardly have been more stark. Yet while the Patriotic Manifesto had gathered nearly 100 signatures from figures of great prominence, the Peace Manifesto attracted only 4. Einstein was one of those 4 signatories, joining the physiologist George Friedrich Nicolai, who had drafted the document, and 2 other figures whose names are less well remembered. The disparity in numbers was itself a measure of the mood in Germany at that time, when opposition to the war was deeply unpopular and when the tide of nationalist sentiment swept nearly everyone along with it. Einstein's decision to sign the Counter-Manifesto was characteristic of an independence of mind that extended beyond his scientific work into matters of politics and social conscience. He was not by nature a political activist, and his primary concerns remained with physics, but he could not bring himself to join in the general enthusiasm for a war that he regarded as a terrible mistake. His position as a Swiss citizen gave him some protection from the pressures that bore upon German nationals, but even so, his stance was not without risk, and it certainly set him apart from most of his colleagues in the Berlin scientific establishment. In the years that followed, his pacifist convictions would become more pronounced and more public, and he would eventually become a prominent voice for peace. But in 1914 he was still primarily absorbed in his scientific work, and his opposition to the war, while genuine, was expressed more through personal conviction than through active campaigning. The war disrupted scientific activity throughout Europe, though it did not bring it entirely to a halt. Many younger scientists were called into military service, and resources that might have gone to research were redirected to military purposes. Communication between scientists in different countries became difficult and sometimes impossible, as the international networks of correspondence and collaboration that had characterized pre-war science were broken apart by the conflict. Yet for Einstein, working primarily as a theorist who required paper and pencil and time to think rather than expensive laboratory equipment, the war's effects on his research were less direct than they were for experimental physicists. He continued his work on the general theory of relativity, wrestling with the mathematical difficulties that still stood between him and a satisfactory formulation of his ideas. Berlin, despite the war, remained a place where serious physics could be done, and Einstein found that his positions there gave him the freedom and the support he needed to pursue his research. The Prussian Academy provided him with a platform for presenting his work, and the colleagues he had acquired through his move to the city offered intellectual companionship of a high order, even if his disagreement with many of them over the war created a certain tension. The year 1914 thus marked a kind of beginning and a kind of ending simultaneously. It was the beginning of his Berlin years, a period that would see some of his greatest scientific achievements, and it was the ending of his first marriage and of the pre-war world in which he had come of age as a physicist. The months that followed his arrival in Berlin were filled with both personal upheaval and the larger upheaval of a continent descending into war, and through it all Einstein continued to think about gravity and geometry, about the curvature of space-time and the motion of planets, about the mathematical structures that might capture the physical reality he was trying to describe. The theory of general relativity was not yet complete, and the final breakthrough would not come until the following year, but the groundwork had been laid, and the circumstances of his life in Berlin, for all their difficulties, provided him with the conditions he needed to bring his decade of struggle to its conclusion. The city that had welcomed him in the spring of 1914 was, by the autumn of that year, a city at war, and the world that emerged from that war would be very different from the one that Einstein had known. But the laws of physics, the deep structures of space and time that he was working to uncover, remained unchanged by human conflict, and it was to these unchanging truths that he directed his attention as the war raged on around him. In the autumn of 1914, as Einstein was completing the most demanding intellectual work of his life, the world around him was descending into a catastrophe of unprecedented scale. The Great War, as it would come to be known, erupted across Europe in August of that year, and within weeks the carefully maintained networks of international scientific cooperation that had flourished for decades began to fracture along national lines. Einstein found himself in Berlin, the capital of one of the principal belligerent powers, surrounded by colleagues whose responses to the war would reveal fault lines in the scientific community that no one had anticipated, and whose choices would shape the character of European physics for years to come. The outbreak of hostilities was met in Germany with a wave of patriotic enthusiasm that swept through universities and research institutions with remarkable force. Scientists who had spent their careers corresponding with colleagues in Paris and London and Cambridge, who had attended international conferences and published in journals read across all borders, now found themselves caught up in a fervor of national feeling that seemed to demand public expressions of loyalty. In early October of 1914, a document began circulating among German intellectuals, a declaration that would become known as the Manifesto of the 93, or more formally as the Appeal to the Civilized World. This manifesto was a response to international criticism of German military conduct, particularly the destruction of the university library at Louvain in Belgium and reports of civilian casualties during the German advance through neutral territory. The manifesto declared emphatically that Germany bore no responsibility for the war, that German troops had committed no atrocities, and that German militarism was inseparable from German culture, the very culture that had produced Goethe and Beethoven and the great tradition of German learning. The signatories proclaimed that they would defend this culture to the last, and they called upon the civilized world to recognize the justice of the German cause. Among the 93 prominent Germans who attached their names to this document were some of the most distinguished scientists of the age, men whose work Einstein knew intimately and whose intellectual achievements he respected deeply. Max Planck signed the manifesto, the same Max Planck who had recognized Einstein's genius early and worked to bring him to Berlin, the founder of quantum theory and one of the most thoughtful physicists of his generation. Walther Nernst signed as well, the physical chemist whose work on thermodynamics had established fundamental principles that Einstein himself had built upon. Wilhelm Röntgen, the discoverer of X-rays and the first Nobel laureate in physics, added his name to the list. So too did Wilhelm Ostwald, the chemist who had once rejected atomistic thinking but had contributed enormously to physical chemistry. The mathematician Felix Klein signed, as did the chemist Fritz Haber, who would soon turn his considerable talents to the development of poison gas for use on the battlefield. For Einstein, who had spent his formative years escaping the nationalism he encountered in the German-speaking world, who had renounced his German citizenship as a teenager and had only reluctantly reclaimed it upon moving to Berlin, the manifesto represented everything he found troubling about the fusion of intellectual life with national pride. He could not bring himself to sign such a document, and indeed his response was to seek out those who shared his discomfort and to add his name to a very different kind of statement. A physician and physiologist named George Friedrich Nicolai had been equally disturbed by the manifesto, and he drafted a counter-declaration that he called the Manifesto to Europeans. Nicolai's document called upon intellectuals to remember their common European heritage, to recognize that the war was a catastrophe for civilization as a whole, and to work toward a future of international cooperation rather than nationalist division. The manifesto called for the creation of a League of Europeans who would resist the forces pulling the continent apart, and it appealed to the shared values of scholarship and reason that transcended national boundaries. Einstein signed this counter-manifesto readily, as did the astronomer Wilhelm Foster, who was then in his 80s and had lived long enough to remember an earlier age of European science. But the response to Nicolai's appeal was discouragingly small. Where the manifesto of the 93 had gathered nearly 100 prominent signatures with ease, the counter-manifesto attracted only 4. The patriotic fervor of the moment was simply too powerful, and most intellectuals who might have been sympathetic to its message chose to remain silent rather than risk appearing disloyal. The document was never published during the war, and it remained a private gesture of dissent rather than a public rallying point. Einstein's pacifism during these years was not merely a matter of signing documents but reflected a deeper conviction that the war represented a kind of collective madness, a failure of reason on a continental scale. He joined the New Fatherland League, a small organization that advocated for a negotiated peace and for the eventual creation of an international body to prevent future wars. This was considered suspicious activity in wartime Berlin, and Einstein's involvement brought him to the attention of the authorities, though his Swiss citizenship and his growing scientific reputation offered him some protection from the harassment that more vulnerable pacifists faced. In his letters from this period, Einstein expressed his feelings about the war with a mixture of sorrow and incomprehension. He found it difficult to understand how his colleagues, men of learning and reason, could embrace the rhetoric of nationalism so completely, could speak of the enemy in terms that denied their common humanity. He observed the war fever around him with the detachment of an outsider, which in many ways he still was, a Swiss citizen living in a German capital gone mad with patriotic enthusiasm. The war created practical difficulties for science that went beyond matters of conscience and loyalty. The networks of international communication that had sustained scientific progress for generations were suddenly disrupted. German scientists could no longer easily correspond with their colleagues in France or Britain, could no longer attend international conferences or read the latest publications from enemy nations. Journals that had circulated freely across borders now became difficult to obtain, and the exchange of ideas that had characterized European physics slowed to a trickle. For Einstein specifically, this meant that his completed theory of general relativity, published in late 1915, did not immediately reach the British physicists who would eventually play such an important role in testing and promoting it. Arthur Eddington in Cambridge, who would become one of the theory's most important advocates, did not learn of Einstein's final equations until well into 1916, when a Dutch physicist named Willem de Sitter managed to send copies of Einstein's papers through neutral channels. The war thus delayed the reception of one of the most important scientific achievements of the century, isolating Einstein intellectually even as it isolated Germany politically. And yet the war did not stop physics entirely. Some of the most remarkable work on Einstein's new theory came from a most unlikely setting, from the trenches of the Eastern Front, where a German astronomer named Karl Schwarzschild was serving as an artillery officer while the battles raged around him. Schwarzschild was not a young man pressed into service but a distinguished scientist who had volunteered at the age of 40, motivated perhaps by the same patriotic feeling that had led so many of his colleagues to sign the manifesto, or perhaps by a sense of duty that transcended his scientific calling. Schwarzschild had been the director of the Astrophysical Observatory in Potsdam, one of the leading astronomical posts in Germany, and his work on stellar atmospheres and the photographic measurement of stellar brightness had established him as one of the most capable mathematical astronomers of his time. When Einstein's final papers on general relativity appeared in November of 1915, Schwarzschild managed to obtain copies even amid the chaos of the Russian front, and he began working through the mathematics with characteristic intensity. Within weeks, Schwarzschild had accomplished something remarkable. He found the first exact solution to Einstein's field equations, describing the gravitational field outside a spherical, non-rotating mass. This solution, which would come to bear his name, showed how spacetime curved around a star or planet, and it provided the mathematical foundation for calculating phenomena like the bending of light and the precession of planetary orbits. Einstein's own calculations had relied on approximations, but Schwarzschild's solution was exact, a precise description of spacetime geometry that revealed the full mathematical structure of the theory. Schwarzschild sent his solution to Einstein in a letter dated December 22, 1915, written from the trenches somewhere in the East. Einstein received it in Berlin and presented it to the Prussian Academy in early January of 1916, expressing his admiration for the elegance of the result and his surprise that anyone had found an exact solution so quickly. It was a strange and poignant moment in the history of science, a letter arriving from the battlefield containing mathematics that would shape our understanding of the universe for a century to come. But Schwarzschild's triumph was brief and bittersweet. While serving on the Russian front, he developed a rare and painful autoimmune disease called pemphigus, which caused blistering of the skin and mucous membranes. He was evacuated from the front and returned to Germany, but the disease progressed rapidly, and Karl Schwarzschild died in May of 1916 at the age of 42. In the few months between his illness and his death, he continued to work on physics, finding a second exact solution to Einstein's equations that described the interior of a spherical mass, as if his mind could find no rest except in the contemplation of spacetime geometry. His death robbed physics of one of its most capable practitioners and served as a stark reminder of the human cost that the war was extracting from the scientific community. Schwarzschild was far from the only scientist lost to the conflict. Henry Moseley, a young British physicist whose work on X-ray spectroscopy, had revealed the deep structure of the periodic table, was killed at Gallipoli in August of 1915, shot through the head by a Turkish sniper. Moseley was only 27, and his work had been so brilliant that many believed a Nobel Prize was inevitable had he lived. His experiments had shown that each element possessed a characteristic X-ray spectrum determined by its atomic number, a discovery that brought order to the periodic table and pointed toward the nuclear structure of atoms. His death was mourned throughout the scientific world, and some later suggested that his loss alone justified changing policies to keep scientists away from the front lines in future conflicts. Across Europe, young men who might have become physicists or chemists or mathematicians were dying in their hundreds of thousands, in the mud of Flanders and the mountains of Italy and the forests of the Eastern Front. The generation that should have carried science forward was being consumed by the war, and no one could calculate the discoveries that would never be made, the insights that perished with the minds that might have conceived them. Einstein remained in Berlin throughout these years, continuing his work amid the growing hardships of wartime. As the British naval blockade tightened around Germany, food became increasingly scarce, and even academics and intellectuals found themselves struggling with shortages that would have been unthinkable before the war. Bread was rationed, then potatoes, then nearly everything else. The winter of 1916 to 1917 was particularly harsh, remembered afterward as the turnip winter because turnips became a staple when other vegetables could not be obtained. Einstein's health, never robust, suffered during this period. He experienced severe stomach problems that his doctors struggled to diagnose and treat, symptoms that may have been related to gallbladder disease or possibly to ulcers exacerbated by stress and poor nutrition. He lost weight that he could not afford to lose, and his letters from these years often mention illness and fatigue alongside reports of his scientific work. His cousin Elsa, who lived in Berlin with her 2 daughters, began caring for him during his periods of illness, cooking meals for him when food could be obtained and providing the domestic stability that his estranged wife Mileva had never quite managed. In his letters to friends abroad, Einstein described his response to the chaos around him with a characteristic mixture of honesty and self-awareness. He wrote that he quietly pursued his peaceful studies and contemplations, finding in physics a refuge from the madness of the world. This was not indifference to human suffering but rather a recognition that his particular gifts could best serve humanity through continued scientific work rather than through involvement in the political and military struggles that consumed everyone around him. He could not stop the war, could not save the young men dying in the trenches, but he could perhaps contribute something lasting to human understanding, something that would endure after the guns fell silent. The Berlin in which Einstein worked during these years was a city transformed by war. The grand avenues and impressive buildings remained, but the spirit of the place had changed utterly. Young men in uniform were everywhere, coming and going from the front, and the wounded could be seen in hospitals and convalescent homes throughout the city. Women had entered the workforce in unprecedented numbers, filling the positions left vacant by men who had been called to military service. The universities continued to function, but with depleted faculties and shrinking enrollments as students and junior professors were drafted. Einstein's position at the Prussian Academy and his role at the Kaiser Wilhelm Institute continued more or less unchanged, protected by his Swiss citizenship and by the nature of theoretical physics, which required no laboratories or materials that might be requisitioned for the war effort. He gave lectures and attended seminars and corresponded with those colleagues who remained, working on the consequences and extensions of his gravitational theory even as the world around him seemed bent on destroying everything that civilization had built. The isolation from international colleagues was perhaps the most difficult aspect of wartime for Einstein the scientist. He had always valued his connections with physicists in other countries, the exchange of ideas across borders that had characterized his career from the beginning. Now those connections were severed or attenuated, and he worked in a kind of intellectual solitude that was quite different from his earlier life. Letters to colleagues in neutral countries like the Netherlands sometimes got through, and these became precious lifelines to the broader scientific world, but communication with France and Britain was effectively impossible for the duration of the conflict. As the war ground on through 1916 and 1917, with no end in sight and casualties mounting into the millions, Einstein continued his work on general relativity. He explored the cosmological implications of his theory, asking what the universe as a whole might look like if described by his equations. He introduced the cosmological constant, a term that allowed for a static universe, because like nearly everyone at the time he assumed that the universe was eternal and unchanging on the largest scales. He corresponded with the Dutch astronomers De Sitter and Ehrenfest about these matters, grateful for the contact with minds outside Germany. The theory itself continued to develop and propagate despite the war's barriers. De Sitter in the Netherlands received Einstein's papers and wrote his own accounts of the theory for British journals, providing one of the channels through which Eddington and other British physicists learned of the new gravitational physics. Slowly, despite the conflict, the scientific community began to absorb the implications of general relativity, even as its creator continued to refine and extend the theory in his Berlin study. Einstein's pacifism never wavered during these years, though he expressed it carefully, aware that too public a stance could bring unwanted attention from the authorities. He continued to support peace organizations when he could and maintained friendships with others who shared his views, including Roman Roland, the French writer who spent the war years in Switzerland advocating for reconciliation between the warring nations. These connections kept alive Einstein's faith that reason would eventually prevail, that the war would end and the work of rebuilding international cooperation could begin. The contrast between Einstein's inner world of gravitational physics and the outer world of industrialized warfare could hardly have been more stark. In his mind, he contemplated the geometry of the cosmos, the bending of light around stars, the precession of planetary orbits, the very structure of space and time. Outside his window, a civilization tore itself apart, sending millions of young men to die in trenches and shell craters, consuming the wealth of nations in the production of ever more efficient weapons of destruction. That both of these things were happening simultaneously, in the same city, in the same years, seems almost impossible to reconcile, and yet this was Einstein's reality during the completion of his greatest work. The war would continue for 2 more years after the completion of general relativity, and its end would bring changes that no one anticipated. Germany would be defeated and transformed, the Kaiser would flee, and a new republic would struggle to establish itself amid economic chaos and political extremism. Einstein's fame would grow enormously in the post-war years, when British astronomers confirmed his predictions and made him the most celebrated scientist in the world. But all of that lay in the future, invisible from the perspective of wartime Berlin. For now, in the winters of 1915 and 1916 and 1917, Einstein worked quietly in his study, pursuing the implications of his theory, dealing with his health problems as best he could, and waiting for the madness to end. The peaceful studies and contemplations that he described to his friends were his anchor in a world gone mad, his contribution to a future that the war seemed determined to foreclose. And so the theory of general relativity, one of the supreme achievements of human thought, was brought to completion and began its early development in circumstances that could hardly have been less conducive to intellectual work, amid food shortages and isolation and the constant awareness of death on an industrial scale just a few hundred kilometers to the east and the west. In the summer of 1915, as the war continued to spread across Europe and the ordinary rhythms of academic life grew ever more difficult to maintain, Albert Einstein made a journey from Berlin to the university town of Göttingen, where he had been invited to deliver a series of lectures on his developing theory of gravitation. Göttingen was, at that time, one of the great centers of mathematical research in the world, home to scholars whose names were spoken with reverence in universities across every continent, and chief among these was David Hilbert, a mathematician of extraordinary range and influence who had spent decades shaping the very foundations of modern mathematical thought. Einstein arrived in late June, carrying with him the accumulated work of nearly a decade, the partially formed equations and physical insights that would eventually become the general theory of relativity, and over the course of 6 lectures spread across 2 weeks, he laid out his ideas before an audience that included some of the finest mathematical minds of the age. The invitation itself had come about through a combination of circumstances, as these things often do, with Felix Klein and David Hilbert both expressing interest in learning more about Einstein's gravitational theory, which had by then attracted considerable attention even in its incomplete state. Einstein was pleased to accept, for he recognized that the mathematicians at Göttingen possessed expertise that might help him overcome the difficulties he had encountered in formulating his field equations, and he was not a man too proud to seek assistance when the problems before him proved resistant to his own methods. The lectures were, by all accounts, a success in the sense that Einstein communicated the essential physical ideas of his theory with clarity and enthusiasm, explaining how he had come to believe that gravitation was not a force acting across empty space but rather a manifestation of the curvature of space-time itself, caused by the presence of matter and energy. David Hilbert listened to these lectures with intense interest, for he had long been concerned with the relationship between physics and mathematics, and he saw in Einstein's work the possibility of bringing gravitational theory into the kind of rigorous axiomatic framework that he believed should underlie all of physical science. Hilbert was 63 years old in that summer of 1915, a commanding figure in the mathematical world who had already made foundational contributions to integral equations, to the theory of algebraic number fields, to the axiomatization of geometry, and to what would later be called functional analysis. He approached problems with a characteristic combination of broad vision and technical precision, always seeking the most general and elegant formulation, and he was not content merely to understand Einstein's physical reasoning but wished to derive the gravitational field equations from first principles using the methods of the calculus of variations and the formalism of action integrals. This approach, which Hilbert pursued with considerable energy in the months following Einstein's visit, represented a distinctly mathematical path toward the same destination that Einstein was approaching through physical intuition and careful consideration of how matter and geometry must interact. The variational method begins by defining a quantity called the action, which is expressed as an integral over spacetime of some function called the Lagrangian, and the fundamental equations of the theory are then obtained by requiring that this action be stationary, meaning that small variations in the fields under consideration do not change the value of the action to first order. This is a powerful and general technique that had proven extraordinarily fruitful in classical mechanics and in electromagnetism, and Hilbert recognized that if he could identify the correct form of the gravitational action, he might be able to derive Einstein's field equations, or perhaps even more general equations, through purely mathematical reasoning. Meanwhile, Einstein had returned to Berlin, where he continued to struggle with the technical difficulties that had plagued his theory for several years. He had known since 1912 or 13 that the gravitational field should be described by a mathematical object called the metric tensor, which encodes information about distances and angles in curved spacetime, and he had known that the field equations should relate this metric tensor to the distribution of matter and energy. But finding the precise form of these equations had proven extraordinarily difficult, and Einstein had at various times pursued approaches that later turned out to be mistaken, including a set of equations published in 1913 with his friend Marcel Grossmann that failed to satisfy the principle of general covariance, which requires that the laws of physics take the same form in all coordinate systems. The autumn of 1915 brought a period of intense and concentrated work, during which Einstein finally broke through the obstacles that had held him back for so long, and this breakthrough unfolded over the course of November in a series of papers presented to the Prussian Academy of Sciences in Berlin. On the 4th of November, Einstein presented a paper in which he returned to generally covariant field equations, abandoning the restrictions he had previously accepted, and though the equations in this paper were not yet in their final form, they represented a decisive step toward the correct theory. 1 week later, on the 11th of November, he presented a second paper with revised field equations, and on the 18th of November, a third paper in which he successfully calculated the anomalous precession of the perihelion of Mercury, obtaining a result that matched astronomical observations with remarkable precision and providing powerful evidence that his theory was on the right track. It was during this same period that Einstein became aware that Hilbert was also working toward the gravitational field equations, using his variational approach, and that Hilbert was making rapid progress. The two men exchanged letters and postcards throughout November, each informing the other of their latest results, and there was an unmistakable sense of urgency in this correspondence, a feeling that both men were approaching the same summit by different routes and that the question of who would arrive first had taken on a certain importance. Einstein, who had labored over this theory for nearly a decade, who had sacrificed his health and his marriage and countless hours of sleep in pursuit of these equations, understandably felt a strong sense of ownership over the physical ideas at the heart of the theory, and he expressed concern in his letters that Hilbert might be appropriating his work, using the German word nostrifying, which means roughly to make something one's own, to claim another's discovery as belonging to one's own group or institution. On the 20th of November, Hilbert submitted a paper to the Royal Society of Sciences in Göttingen, presenting what he called the fundamental equations of physics, and this paper included a version of the gravitational field equations derived from a variational principle. 5 days later, on the 25th of November, Einstein presented his fourth and final November paper to the Prussian Academy, containing the complete and correct field equations of general relativity in their final form, the equations that describe how the curvature of spacetime is determined by the distribution of matter and energy and that have remained the foundation of gravitational physics ever since. The question of who deserves credit for these equations, and whether Hilbert had the correct equations before Einstein or arrived at them independently through his variational method, has been a subject of historical investigation and occasional controversy for more than a century. The matter is complicated by the fact that Hilbert's paper, as originally submitted on the 20th of November, underwent significant revisions before it was published in March of the following year. An examination of the surviving printer's proofs has revealed that certain crucial elements were added or modified during this revision process. In particular, some historians have argued that the explicit form of the field equations appearing in the published version of Hilbert's paper was not present in the original submission, and that Hilbert may have incorporated corrections or clarifications after learning of Einstein's final results. Others have suggested that the differences between the original and published versions are less significant than they might appear, and that Hilbert's variational approach would naturally have led to the correct equations even if the explicit form was only written out later. The surviving documentary evidence is incomplete, as some portions of Hilbert's original proofs have been lost or damaged, and scholars continue to debate the precise sequence of events and the implications for questions of priority. What seems clear, in any case, is that Einstein and Hilbert arrived at the field equations through genuinely different methods, with Einstein relying primarily on physical reasoning about how the equations must behave in limiting cases and how they must reduce to Newtonian gravity in appropriate circumstances, while Hilbert sought the most elegant mathematical formulation and derived the equations from an action principle. It also seems clear that the physical conception of the theory, the understanding of what the equations mean and how they connect to observable phenomena, was Einstein's contribution, developed over many years of sustained and often solitary effort, while Hilbert's contribution lay in showing how the same equations could be obtained from a variational principle, which provided both an alternative derivation and a framework that would prove valuable in later developments of gravitational theory. The relationship between Einstein and Hilbert, which had become strained during the tense weeks of November 1915, was eventually repaired, and the two men exchanged cordial letters in December that suggest a mutual recognition of each other's contributions and a willingness to put aside questions of priority in favor of continued scientific cooperation. Hilbert, for his part, consistently gave Einstein full credit for the physical theory of general relativity, and he is reported to have said on more than one occasion that every boy in the streets of Göttingen understands more about four-dimensional geometry than Einstein, yet Einstein did the work, by which he meant that the mathematical techniques required for general relativity were well known to professional mathematicians, but that the physical insight to see how these techniques could describe gravitation, and the determination to carry through the calculations despite years of difficulties, were Einstein's alone. The work at Göttingen continued in the years following the completion of general relativity, and it was there that some of the most important mathematical elaborations of the theory were carried out, including contributions by a mathematician whose name deserves particular mention in any account of this period. Emmy Noether had arrived at Göttingen in 1915, the same year as Einstein's lectures, having already established herself as a talented algebraist at the University of Erlangen, and she came at the invitation of Hilbert and Klein, who recognized her exceptional abilities and wished to have her assistance in working out the mathematical structure of the new gravitational theory. Noether faced significant obstacles as a woman in the German academic system of that era, including regulations that prevented her from holding an official position or receiving a regular salary for many years, and she often had to deliver lectures that were officially listed under Hilbert's name rather than her own. Despite these difficulties, Noether made contributions to general relativity and to mathematical physics more broadly that would prove to be of lasting importance, and chief among these was a theorem she proved in 1918 concerning the relationship between symmetries and conservation laws. This theorem, which has come to bear her name, establishes that for every continuous symmetry of a physical system, there exists a corresponding quantity that is conserved, meaning that it does not change over time. If the laws of physics are the same at all locations in space, then momentum is conserved, and if they are the same at all moments in time, then energy is conserved, and if they are unchanged by rotations, then angular momentum is conserved. This connection between symmetry and conservation, which Noether established with complete mathematical rigor, has become one of the foundational principles of theoretical physics, underlying not only general relativity but also quantum mechanics and the theories of fundamental particles and forces that were developed in the decades that followed. Noether's theorem also helped to clarify certain conceptual puzzles that had arisen in the context of general relativity, particularly concerning the definition and conservation of energy in a gravitational field. The general covariance of Einstein's theory, which requires that the equations take the same form in all coordinate systems, leads to subtleties in defining conserved quantities, and Noether's analysis provided a precise mathematical framework for understanding these subtleties. Her work demonstrated, among other things, that the apparent loss of energy conservation in certain formulations of general relativity is connected to the freedom to choose different coordinate systems, and that properly defined conserved quantities can be constructed by taking this freedom into account. The collaboration between mathematicians and physicists at Göttingen during this period represented a particularly fruitful example of how different approaches to the natural world can complement and strengthen one another, with the physicists bringing intuition about how nature behaves and the mathematicians providing rigorous frameworks and powerful techniques for expressing and extending these intuitions. Einstein himself, though he remained in Berlin and was never formally affiliated with Göttingen, benefited enormously from his interactions with the mathematical community there, and the theory of general relativity as we know it today bears the marks of both physical insight and mathematical elegance. As the years passed and the initial excitement of discovery gave way to the slower work of exploring the implications of the new theory, the questions of priority that had briefly troubled the relationship between Einstein and Hilbert came to seem less important than the theory itself and the new understanding of the universe that it provided. Both men continued to make significant contributions to physics and mathematics in the decades that followed, and both are remembered today as giants of 20th-century science, their work intertwined in the history of general relativity in ways that reflect the complexity of scientific discovery and the difficulty of assigning credit when brilliant minds converge on the same profound truth. Hilbert lived until 1943, continuing to work at Göttingen until the rise of National Socialism destroyed the mathematical community he had helped to build, while Einstein departed Europe in 1933 and spent his remaining years at the Institute for Advanced Study in Princeton, where he continued to seek a unified field theory that would bring together gravitation and electromagnetism within a single mathematical framework. Emmy Noether left Germany in 1933 as well, fleeing the persecution of Jewish academics, and she spent the final years of her life at Bryn Mawr College in the United States, where she continued her mathematical work until her sudden death in 1935 at the age of 53. Einstein wrote a letter to the New York Times following her death in which he described her as the most significant creative mathematical genius thus far produced since the higher education of women began, and though recognition of her contributions was slow to develop during her lifetime, she is now remembered as one of the great mathematicians of the 20th century, whose theorem connecting symmetry and conservation remains a cornerstone of theoretical physics. And so the race of November 1915, if it can properly be called a race, came to an end not with a single victor but with a shared achievement, a new understanding of gravitation and geometry that would reshape our conception of the universe and provide the foundation for countless further discoveries in the century to come. The equations that Einstein presented on the 25th of November, and that Hilbert derived through his variational methods, described a universe far stranger and more wonderful than anyone had previously imagined, a universe in which space and time are curved by the presence of matter, in which light bends around massive objects, in which time flows at different rates depending on the strength of the gravitational field, and in which the possibility exists for objects so dense that not even light can escape from their gravitational pull. These equations, written in the compact notation of tensor calculus, fit on a single line, and yet they contain within them the seeds of black holes and gravitational waves, of the expansion of the universe and the curvature of spacetime around every star and planet, and they remain today, more than a century after their discovery, our best description of the gravitational interaction and the large-scale structure of the cosmos in which we live. In the autumn of 1915, as the second year of the Great War settled into its grinding rhythm of attrition and loss, Albert Einstein found himself working in a kind of intellectual solitude that was both liberating and exhausting. Berlin had become a city of ration cards and dimmed street lamps, of wounded soldiers returning from the front and anxious families scanning casualty lists, and yet within this atmosphere of collective suffering, Einstein retreated ever more deeply into the abstract world of gravitational theory, pursuing with renewed intensity the ideas that had occupied him for nearly a decade. The breakthrough that would come in November of that year was not a sudden flash of insight appearing from nowhere, but rather the culmination of years of patient work, false starts, conceptual struggles, and the gradual refinement of mathematical and physical intuition that had been building since his first serious engagement with gravity in 1907. The story of that November is really the story of 4 papers, presented in quick succession to the Prussian Academy of Sciences over the course of just 3.5 weeks, each one representing a step closer to the final form of what we now call general relativity. Einstein had arranged to give a series of Thursday lectures to the Academy, and he used this schedule as a kind of forcing function, compelling himself to commit his evolving ideas to paper even as those ideas continued to develop and change from one week to the next. It was an unusual way to announce a major scientific theory, almost like watching a composer revise a symphony in real time before an audience, crossing out passages and rewriting them even as the orchestra prepares to play. But Einstein was driven by a sense of urgency that transcended normal academic caution, a feeling that he was finally, after so many years of struggle, approaching the solution to the great puzzle of gravitation. The first of these November papers was presented on the 4th of that month, and in it Einstein took the remarkable step of abandoning the Entwurf theory that he had developed with Marcel Grossmann and had defended for more than 2 years. This was not an easy thing to do, for the Entwurf theory represented an enormous investment of intellectual effort, and Einstein had convinced himself through various arguments that its limitations were necessary features rather than flaws. But sometime in the weeks leading up to November, Einstein had come to recognize that the Entwurf equations were fundamentally inadequate, that they could not be made compatible with the principle of general covariance that he now believed must lie at the heart of any correct theory of gravity. In the November 4th paper, he returned to the mathematical framework of Riemannian geometry and proposed a new set of field equations based on the Ricci tensor, the same mathematical object he had considered and rejected back in 1912 and 13. The equations he presented that day were not yet quite right, for they contained a restriction that limited their applicability to coordinate systems in which the determinant of the metric tensor took a particular simple form, but they represented a crucial turn away from the compromises of the Entwurf theory and toward the fully covariant formulation that would emerge by the end of the month. 1 week later, on the 11th of November, Einstein presented a second paper to the Academy, in which he modified the field equations he had proposed the previous week. The new equations were still restricted in certain ways, applying only to what Einstein called unimodular coordinates, which are coordinate systems chosen so that the square root of the negative determinant of the metric tensor equals unity. This restriction meant that the equations were not yet fully generally covariant, not yet applicable in any arbitrary coordinate system whatsoever, but Einstein believed at the time that this limitation might be physically meaningful, perhaps connected to fundamental properties of matter or to the structure of the universe as a whole. The physics of the theory was becoming clearer even as the mathematical formulation continued to evolve, and Einstein was working with a kind of feverish intensity that took a visible toll on his health and well-being. In letters from this period, he mentioned stomach pains and digestive troubles, the physical symptoms of the enormous mental strain he was placing on himself, and he described his work schedule as horribly strenuous, pushing himself to the limits of what his body and mind could sustain. The third paper, presented on the 18th of November, contained what Einstein himself regarded as the most convincing evidence that he was finally on the right track. Using his new field equations, he calculated the orbit of the planet Mercury around the Sun, paying particular attention to the phenomenon known as perihelion precession. The perihelion of a planetary orbit is the point at which the planet comes closest to the Sun, and in Newtonian gravity, if there were only one planet orbiting a perfectly spherical Sun, this point would remain fixed in space, the orbit tracing out the same ellipse over and over again for eternity. But in reality, the gravitational influence of other planets, particularly Jupiter and the other outer giants, causes the perihelion to advance slowly around the Sun, so that the orbit does not quite close on itself but rather traces out a kind of rosette pattern over millions of years. Astronomers had carefully measured this effect for Mercury, finding that its perihelion advances by about 574 arcseconds per century, and they had calculated that the gravitational influence of the other planets could account for about 531 arcseconds of this total. But that left a discrepancy of about 43 arcseconds per century, a small but stubbornly persistent anomaly that could not be explained by Newtonian gravity even when all known sources of gravitational perturbation were taken into account. This anomaly had been recognized since the 1850s, when the French astronomer Urbain Le Verrier had first pointed out the discrepancy, and various explanations had been proposed over the years, including the existence of a hypothetical planet called Vulcan orbiting closer to the Sun than Mercury, or a slight deviation from the inverse square law of Newtonian gravity, or a previously undetected arblateness in the shape of the Sun itself. None of these explanations had proved satisfactory, and the 43 arcseconds remained a small but persistent thorn in the side of classical physics, a hint that perhaps Newton's theory was not quite the last word on gravity after all. Einstein was aware of this anomaly and had long hoped that any correct theory of gravity would naturally account for it, and when he applied his new field equations to the problem of Mercury's orbit, he found that they predicted an additional perihelion precession of exactly 43 arcseconds per century, matching the observed discrepancy with remarkable precision. He later described the moment of this discovery in a letter to his friend Paul Ehrenfest, writing that he was beside myself with joyous excitement when he saw that his calculations gave exactly the right answer. For several days, he could not work, so overcome was he with the emotional impact of this result, This first clear confirmation that his long struggle toward a new theory of gravity had not been in vain. The significance of the Mercury calculation went beyond its immediate scientific content, important as that was. It showed that general relativity was not merely an abstract mathematical construction, not just a more elegant way of reformulating ideas that Newton had already captured, but a genuinely new physical theory that made predictions different from Newtonian gravity in ways that could be tested and confirmed by observation. The theory had passed its first empirical test, and passed it with flying colors, explaining an anomaly that had puzzled astronomers for more than half a century without the need for any hypothetical planets or ad hoc modifications to known physics. Einstein had always believed that a correct theory would be mathematically beautiful and conceptually coherent, but he also understood that physics ultimately answers to nature, and the Mercury result showed that nature agreed with his new equations. The final paper in this November sequence was presented on the 25th, exactly 1 week after the Mercury paper, and it contained the complete and correct field equations of general relativity in their final form. Einstein had realized that the restriction to unimodular coordinates, which he had imposed in his earlier November papers, was not necessary after all, and he had found a way to write the field equations in a form that was fully generally covariant, applicable in any coordinate system whatsoever. The equations he presented that day can be written in the compact notation of tensor calculus as a mu nu minus 1/2 g mu nu r equals kappa t mu nu, where r mu nu is the Ricci tensor, g mu nu is the metric tensor, r is the Ricci scalar obtained by contracting the Ricci tensor, t mu nu is the stress-energy tensor describing the distribution of matter and energy, and kappa is a constant related to Newton's gravitational constant. These equations, known today simply as the Einstein field equations or sometimes as the Einstein equations, express in precise mathematical form the central insight of general relativity, that the geometry of spacetime, encoded in the metric tensor and the curvature derived from it, is determined by the distribution of matter and energy, encoded in the stress-energy tensor. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. This reciprocal relationship captured in a set of equations that are at once elegant and profound. The path to these final equations required Einstein to resolve a conceptual puzzle that had troubled him for years, the problem known as the whole argument, which had convinced him back in 1913 that generally covariant field equations were physically impossible. The whole argument went something like this. Imagine a region of spacetime, a hole, that is empty of matter, and suppose we have a solution to some hypothetical generally covariant field equations that describes the gravitational field throughout spacetime, including within this hole. Because the equations are generally covariant, we can perform a coordinate transformation that changes the description of the field inside the hole while leaving everything outside the hole unchanged, and this new description will also be a valid solution to the same field equations. But if the matter distribution outside the hole uniquely determines physical reality, then it seems we have two different solutions, two different gravitational fields inside the hole, both consistent with the same matter distribution, which would mean that the field equations fail to uniquely determine the gravitational field from the sources that produce it. Einstein had found this conclusion deeply troubling, and for a time it had led him to believe that fully covariant equations must be rejected in favor of equations with more restricted covariance properties. What Einstein eventually came to understand, sometime in 1915 as he was working toward the November papers, was that the whole argument rested on a subtle misunderstanding about the nature of coordinate systems and physical reality. The two solutions related by a coordinate transformation inside the hole were not really different physical situations at all, but rather two different mathematical descriptions of the same physical situation, two different ways of labeling the same events with coordinates. The coordinates themselves have no physical meaning. They are arbitrary labels that we attach to points in spacetime for the convenience of calculation, and changing these labels through a coordinate transformation does not change anything physically observable. What matters physically is not the values of the metric tensor components at particular coordinate values, but rather the geometric relationships between events, relationships that are captured by invariant quantities that do not depend on the choice of coordinates. Once Einstein grasped this point clearly, the whole argument dissolved, and he was free to pursue fully covariant field equations without the conceptual obstacles that had blocked his path for 2 years. Throughout this intense period of work, Einstein was essentially alone in his scientific quest. His former collaborator Marcel Grossmann was in Zurich, and while they remained on friendly terms, Grossmann was not involved in the final push toward the completed theory. Einstein's marriage to Mileva had effectively ended. She had taken their 2 sons back to Zurich the previous year, and while they were not yet divorced, they were living entirely separate lives. His colleagues in Berlin were mostly occupied with war-related work or with scientific problems far removed from gravitation theory, and the international scientific community was fragmented by the conflict, with communication between scientists in warring countries becoming increasingly difficult. Einstein found the nationalism and militarism that pervaded German academic life deeply distasteful, and he was one of the few prominent intellectuals who refused to sign the infamous Manifesto of the 93, which defended German military actions in Belgium. His pacifist views isolated him further from many of his colleagues, and he spent much of his time alone with his calculations, his books, and his violin. This isolation, painful as it must have been on a personal level, may have contributed to Einstein's ability to focus so completely on his work during those crucial November weeks. Without the distractions of family life or the demands of a busy social calendar, he could devote himself entirely to the problem of gravitation, working through the night when necessary, filling page after page with tensor calculations, checking and rechecking his results against the astronomical data. The stomach pains he mentioned in his letters were almost certainly exacerbated by this punishing schedule, by irregular meals and inadequate sleep and the constant mental strain of working at the very edge of his abilities. But Einstein seems to have regarded these physical discomforts as a small price to pay for the intellectual rewards he was reaping, for the satisfaction of seeing a decade of work finally coming together into a coherent and beautiful whole. By the end of November, the essential work was done. The field equations presented on the 25th would require no further modification. They remain today, more than a century later, our best description of gravity at the classical level, having passed every experimental test to which they have been subjected with remarkable precision. There would be much more work to do in the years ahead, working out the implications of the theory, finding solutions to the field equations for various physical situations, exploring the predictions for phenomena like gravitational waves and black holes that would not be directly confirmed until much later. But the conceptual heavy lifting was complete. Einstein had achieved what he set out to do back in 1907 when he first felt the spark of insight about the equivalence of gravity and acceleration, what he had worked toward through years of struggle with the mathematics of curved spaces and the physics of gravitational fields. He had extended the principle of relativity from its special form, applicable only to observers in uniform motion, to a general form applicable to observers in any state of motion whatsoever, and in doing so he had revealed that gravity is not a force in the conventional sense but rather a manifestation of the curvature of spacetime itself. As we settle into the quiet of this narrative about events long past, about a scientist working alone in wartime Berlin more than 100 years ago, we might reflect on the strange combination of circumstances that made this achievement possible, the particular gifts of mathematical ability and physical intuition that Einstein possessed, the decade of sustained effort that allowed him to develop and refine his ideas, the isolation that freed him from distraction even as it imposed its own costs, and the stubbornness or faith or whatever we might call it that kept him working toward a goal that most of his colleagues either ignored or actively discouraged. The universe, it turned out, was more subtle and more beautiful than Newton had imagined, and it fell to Einstein to reveal something of this subtlety and beauty through his field equations, those elegant expressions that connect the geometry of spacetime to the matter and energy that fill it. And now, knowing how the story ends, we can perhaps rest more easily, trusting that the universe makes sense in ways that patient thought can uncover, that the apparent chaos of experience conceals an underlying order waiting to be discovered by those with the patience and skill to seek it out. And so we turn now to a quiet mystery that had lingered in the careful records of astronomers for more than a century, a small discrepancy in the motion of the planet Mercury that would eventually become one of the most beautiful confirmations of Einstein's new theory of gravity. This is a story of patient observation, of meticulous calculation, and of a problem so subtle that it might easily have been dismissed as mere observational error, were it not for the extraordinary precision of 19th-century astronomical science and the stubborn persistence of those who believed that nature must ultimately make sense. Mercury, that small and swift planet closest to our Sun, has been watched by human eyes since ancient times. It moves so quickly across the sky, completing its orbit in just 88 Earth days, that the Romans named it for their messenger god. Because it never strays far from the Sun as seen from Earth, it appears only briefly in the twilight hours, either just after sunset or just before dawn, and then it slips away again, lost in the solar glare. And yet, despite these difficult viewing conditions, astronomers had tracked Mercury's motion with considerable care over many centuries, building up detailed records of its positions against the background stars at various times throughout each year. By the middle of the 19th century, these accumulated observations had become precise enough to reveal something peculiar about Mercury's orbit. Like all the planets, Mercury travels around the Sun not in a perfect circle but in an ellipse, with the Sun located at one focus of that ellipse rather than at its center. This means that Mercury is sometimes closer to the Sun and sometimes farther away. The point of closest approach is called the perihelion, from the Greek words for near and sun, and it was the behavior of this perihelion point that astronomers found so troubling. According to Newtonian mechanics, if Mercury were the only planet orbiting the Sun, its elliptical orbit would remain fixed in space, with the perihelion always pointing in the same direction relative to the distant stars. But of course Mercury is not alone. The gravitational pull of the other planets, particularly the massive Jupiter and the nearby Venus, tugs gently on Mercury as it makes its rounds, causing the entire orbit to rotate slowly in space. The perihelion point advances, or precesses, around the Sun, so that if you could watch from above for many thousands of years, you would see Mercury's ellipse gradually turning like a very slow pinwheel. Newtonian gravity predicted this precession beautifully, and astronomers could calculate exactly how much the perihelion should advance each century based on the known masses and positions of all the other planets. The calculation was intricate but entirely within the capabilities of 19th-century mathematical astronomy, and when the numbers were worked out, they gave a specific prediction that could be compared with observation. And this is where the trouble began, for when astronomers measured the actual precession of Mercury's perihelion, they found that it was slightly too large. Mercury's orbit was rotating just a tiny bit faster than Newton's theory could explain. The discrepancy was noticed by the French astronomer Urbain Le Verrier, a man whose career had already been marked by one of the most spectacular triumphs in the history of celestial mechanics. In 1846, Le Verrier had analyzed subtle irregularities in the orbit of Uranus and predicted that they were caused by the gravitational influence of an unknown planet farther from the Sun. When astronomers pointed their telescopes at the location Le Verrier specified, they found Neptune within 1 degree of his predicted position. It was a stunning vindication of Newtonian gravity, demonstrating that the theory could not only explain what had been observed but could reveal the existence of worlds never before seen. So when Le Verrier turned his attention to Mercury in the late 1850s and found another anomaly, another discrepancy between theory and observation, it was only natural that he would seek a similar explanation. In 1859, he announced his careful analysis of Mercury's orbit and reported that after accounting for the gravitational effects of all the known planets, there remained an unexplained advance of the perihelion amounting to approximately 38 arcseconds per century. Later refinements would adjust this figure to about 43 arcseconds per century, but the essential mystery remained the same. Something was making Mercury's orbit precess faster than Newton's theory could account for. An arcsecond is an extraordinarily small angle, 1/3600th of a degree, and 43 arcseconds per century might seem like a negligible amount, hardly worth worrying about. But the precision of astronomical measurement was such that this tiny discrepancy was real and significant, well outside the possible range of observational error. The mystery demanded an explanation, and Le Verrier, drawing on his earlier success, proposed one that seemed entirely reasonable at the time. Perhaps there was another planet, or perhaps a ring of small bodies, orbiting even closer to the Sun than Mercury, whose gravitational influence was responsible for the extra precession. This hypothetical planet came to be called Vulcan, named for the Roman god of fire, and for several decades astronomers searched for it with considerable enthusiasm. There were even occasional reports of sightings, brief glimpses of dark spots crossing the face of the Sun that might have been the elusive inner planet making its transit. But none of these observations could be confirmed, and as telescopes improved and solar observations became more systematic, the case for Vulcan grew weaker and weaker. No planet was found, despite the most careful searches, and the mystery of Mercury's precession remained unsolved. Other explanations were proposed over the years, each attempting to save Newtonian gravity by introducing some additional factor that had not been properly accounted for. Perhaps the Sun itself was not perfectly spherical but was slightly flattened at its poles due to rotation, and this oblateness was creating an extra gravitational effect on Mercury's orbit. Careful measurements were made of the Sun's shape, and while some slight oblateness was detected, it was far too small to explain the 43 arcseconds. Perhaps there was a diffuse ring of asteroids or dust particles orbiting close to the Sun, too faint to be seen directly but massive enough in aggregate to influence Mercury's motion. Again, no evidence for such material could be found in the required quantities. The American astronomer Simon Newcomb, who was widely regarded as one of the finest mathematical astronomers of his generation, took up the problem in the 1880s and subjected it to the most rigorous analysis yet attempted. Newcomb was a meticulous calculator, patient and thorough, and he reanalyzed all the available observations of Mercury's transits across the Sun and its various planetary configurations, reducing the data with extreme care and applying the latest values for the planetary masses and distances. His 1882 calculations confirmed and refined the various result. The anomalous precession was real, amounting to 43 arcseconds per century with an uncertainty of only a few arcseconds. No adjustment of the known gravitational influences could make it go away, and no hypothetical masses in plausible locations could explain it without creating other discrepancies that would have been noticed. And so the mystery lingered, one of the few places where the magnificent Newtonian synthesis seemed to falter, a small but persistent crack in the otherwise seamless edifice of classical physics. It was not that anyone seriously doubted Newton's law of gravitation because of Mercury alone, for that law had proved itself in countless other applications and predictions. But it was curious, and it was troubling, and those who thought deeply about such matters kept it in the back of their minds as a puzzle that might someday reveal something important about the nature of gravity and space. Now we come to Einstein in November of 1915, working feverishly in Berlin to complete his general theory of relativity, racing against both his own earlier mistakes and the formidable intellect of David Hilbert in Göttingen. Einstein had struggled for nearly 3 years with his Entwurf theory, developed in collaboration with Marcel Grossmann, and during that time he had attempted to calculate the precession of Mercury's perihelion using that earlier framework. The result had been disappointing. The Entwurf theory predicted a precession of only 18 arcseconds per century, less than half of what was observed. This should have been a warning sign that something was fundamentally wrong with the theory, but Einstein had convinced himself through other arguments that the Entwurf approach was correct, and he set aside the Mercury calculation as a problem to be resolved later. It was only in the autumn of 1915, when Einstein finally abandoned the Entwurf theory and returned to the generally covariant field equations he had fleetingly considered years before, that the full power of the correct theory became apparent. On November 18, 1915, Einstein completed his calculation of Mercury's perihelion precession using the new field equations, and the result was extraordinary. The theory predicted an additional precession of precisely 43 arcseconds per century, in exact agreement with Newcomb's observed value. There were no adjustable parameters in the calculation, no free constants that could be tuned to match the data. The number emerged directly and inevitably from the mathematics of curved spacetime, and it agreed with observation to within the limits of measurement. Einstein's reaction to this result was intense and deeply personal. He later wrote to a colleague that when he saw the calculation come out correctly, he experienced heart palpitations. The mathematics of his theory had revealed something true about the universe, something that had puzzled astronomers for more than 50 years, and it had done so with no room for fudging or adjustment. This was the moment when Einstein knew, with a certainty that transcended intellectual conviction, that he was on the right track. The universe itself had confirmed his theory. It is worth pausing to consider why Mercury, of all the planets, was the ideal test case for detecting the subtle effects of general relativity on orbital motion. The new theory predicted that the curvature of spacetime near a massive body like the Sun would cause planetary orbits to precess slightly beyond what Newtonian gravity alone would indicate. But this effect is extremely small, and it falls off rapidly as you move farther from the Sun. Mercury, being the closest planet to the Sun, experiences the strongest spacetime curvature of any planet in our solar system, and therefore shows the largest relativistic precession. Furthermore, Mercury has the most elliptical orbit of all the inner planets. While Earth's orbit is very nearly circular, with an eccentricity of only about 0.017, Mercury's orbit has an eccentricity of 0.206, meaning it deviates significantly from a perfect circle. The perihelion precession is most easily detected when the orbit is noticeably elliptical, because the perihelion point is then well defined and its motion can be tracked precisely. A perfectly circular orbit has no distinct perihelion at all, since every point is equally close to and far from the central body. Mercury's pronounced ellipticity made it possible to measure the tiny relativistic effect against the much larger Newtonian precession caused by the other planets. The combination of these two factors, proximity to the Sun and orbital eccentricity, made Mercury uniquely sensitive to the predictions of general relativity. The other planets also experience relativistic precession, but in amounts far too small to have been detected with 19th-century techniques. Venus and Earth, being farther from the Sun and having more circular orbits, precess by only a few arcseconds per century due to relativistic effects. Mars does somewhat better because of its more elliptical orbit, but it is too far from the Sun for the effect to be prominent. Mercury alone carried the signature of curved spacetime in an amount large enough to notice and mysterious enough to have attracted attention long before anyone understood what it meant. Looking back, we can see that Einstein's failed calculation with the Entwurf theory should have been a decisive clue that something was wrong. If the correct value was 43 arcseconds, and the Entwurf theory gave only 18, then the Entwurf theory was clearly missing something important about the geometry of spacetime near the Sun. Einstein might have saved himself considerable time and effort if he had taken this disagreement more seriously and allowed it to guide his search for the correct field equations. But science does not always proceed along the most efficient path, and Einstein had other reasons, involving the mathematical structure of the theory and arguments about energy conservation, for believing in the Entwurf framework. It was only when those other arguments began to crumble under closer examination that he returned to the Mercury problem and found his new theory giving the correct answer. The agreement between theory and observation was not merely close, it was exact, within the precision of the measurements. This kind of precise numerical agreement, with no free parameters, is extremely rare in physics and extremely persuasive when it occurs. It meant that general relativity was not just a mathematically elegant rewriting of gravitational theory, but a genuine improvement over Newton that captured something real about how gravity works in the strong field regime near massive bodies. Newton's theory remained an excellent approximation for most purposes, but Einstein's theory went deeper, revealing structure that Newton's framework could not accommodate. The precession of Mercury's perihelion thus became one of the three classic tests of general relativity, alongside the bending of starlight by the Sun and the gravitational redshift of light. Of these three, the Mercury test was the only one that could be performed immediately, using data that had already been collected over many decades. The bending of starlight would have to wait for the solar eclipse expeditions of 1919, and the gravitational redshift would not be definitively measured until the Pound-Rebka experiment of 1960. But Mercury had already spoken, confirming Einstein's theory before the theory was even published in its final form. And so a small mystery that had puzzled astronomers since the days of Leverrier found its resolution in the curved geometry of spacetime. The extra 43 arcseconds were not caused by an unseen planet, not by solar oblateness, not by hidden rings of matter, but by the simple fact that space and time near the Sun are not what Newton had assumed them to be. Mercury, faithful messenger of the heavens, had been carrying a secret about the structure of the universe, written in the subtle precession of its orbit, waiting for someone with the right theory to read it. We have spoken now of observations and calculations, of patient astronomers measuring positions against the stars, and of Einstein experiencing heart palpitations as the numbers came together. These are quiet moments in the history of science, lacking the drama of unexpected discoveries or public controversies, but they carry their own gentle significance. The universe had placed a puzzle in plain sight, and over many decades, through the work of many careful minds, that puzzle was first recognized, then refined, and finally understood. There is a certain comfort in knowing that such understanding is possible, that the patient accumulation of precise measurements can eventually reveal deep truths about the nature of space and time and gravity. And on that thought, with Mercury still tracing its swift ellipse around the Sun, its perihelion advancing just as Einstein's equations predicted, we may let our minds settle into quietude, resting in the knowledge that the universe, however strange and curved it may be, is ultimately comprehensible to those who look carefully enough. Among the predictions that emerged from Einstein's developing theory of gravity, perhaps none captured the imagination quite so vividly as the idea that light itself might bend when passing near a massive object such as the Sun. This notion, that a ray of starlight traveling through the cosmos could be deflected from its otherwise straight path by the gravitational influence of our nearest star, became one of the central tests by which the new theory would eventually stand or fall. The story of how Einstein arrived at his prediction, how that prediction changed as his understanding deepened, and how various attempts to verify it unfolded across nearly a decade of effort, is a gentle tale of theoretical refinement and practical difficulty, of patience and persistence, and of the sometimes quiet drama that accompanies the intersection of abstract mathematics with the observable heavens. Einstein first began to consider seriously the deflection of light by gravity during the years following his 1907 insight about the equivalence principle, that foundational idea which held that the effects of gravity and the effects of acceleration were, in some fundamental sense, indistinguishable from one another. If a person stood in a closed room accelerating upward through empty space, they would feel pressed to the floor in precisely the same manner as if they were standing still in a gravitational field. This equivalence, Einstein reasoned, must extend to all physical phenomena, including the behavior of light. If a beam of light were to cross such an accelerating room horizontally, it would appear to curve downward from the perspective of someone inside, because the floor would be rising to meet it during the time the light took to traverse the space. By the equivalence principle, then, light passing through a gravitational field ought to curve as well, bending toward the massive body that produced the field. This reasoning led Einstein, by 1911, to publish a calculation of exactly how much starlight should bend when passing close to the edge of the Sun. The geometry of the situation was relatively straightforward to envision, even if the mathematics required some care. Light from a distant star, traveling toward Earth, might pass quite close to the Sun's surface before reaching us. During a total solar eclipse, when the Moon blocked the brilliant disk of the Sun and allowed the much fainter stars to become visible in the darkened sky, Astronomers could photograph the star field surrounding the eclipsed Sun and compare the apparent positions of those stars with their positions as measured when the Sun was elsewhere in the sky, months earlier or later. If the starlight were indeed bent by the Sun's gravity, the stars would appear to be shifted slightly outward from their true positions, pushed away from the Sun's center by the deflection of their light rays. Einstein's 1911 calculation yielded a deflection of approximately 0.87 arcseconds for a ray of light just grazing the limb of the Sun, that outermost visible edge of the solar disk. An arcsecond is a remarkably small angle, representing 1/3600th of a degree, or equivalently, the angle subtended by a small coin viewed from a distance of several kilometers. It is a measure that astronomers use routinely when discussing the fine details of stellar positions, though it remains far too small for the unaided human eye to perceive. The value of 0.87 arcseconds, while tiny, was nonetheless within the reach of the photographic and telescopic techniques available in the early 20th century, and Einstein expressed considerable hope that astronomers might undertake the measurements necessary to confirm or refute his prediction. It is worth pausing here to note a curious fact about this 1911 prediction. The value of 0.87 arcseconds is precisely what one would calculate using the older Newtonian theory of gravity, treating light as though it consisted of tiny particles, or corpuscles, that possessed some equivalent mass and therefore felt the gravitational attraction of the Sun just as any other material body would. This Newtonian deflection had been calculated over a century earlier by the German astronomer Johann Georg von Soldner in 1801, though his work had been largely forgotten by Einstein's time. Einstein arrived at the same numerical result through his equivalence principle reasoning, essentially capturing the same physics by a different route. At this stage, his theory of gravity remained incomplete, and the full geometric picture that would eventually characterize general relativity had not yet emerged. The deflection he predicted in 1911 arose from the curvature of time alone, from the slowing of clocks in a gravitational field that his equivalence principle implied, without yet accounting for the additional effects that would come from the curvature of space itself. Einstein was eager to see his prediction tested, and he reached out to astronomers who might be positioned to help. One such effort came in 1913, when Einstein wrote a letter to the distinguished American astronomer George Ellery Hale, who directed the Mount Wilson Observatory in California and had access to some of the finest telescopic equipment in the world. In this letter, Einstein inquired whether it might be possible to detect the deflection of starlight near the Sun without waiting for the rare circumstance of a total solar eclipse. He wondered if perhaps the brightness of the solar corona, that faint outer atmosphere of the Sun visible during eclipses, might be sufficient to allow star observations close to the Sun's edge even under ordinary conditions, or whether some other technique might circumvent the need for an eclipse entirely. Hale's reply was discouraging on this point. The scattered light from the Sun's atmosphere, he explained, was far too intense to permit the observation of stars near the solar limb except during totality, when the main disk was fully blocked. The corona itself, while faint compared to the Sun, was still brilliantly luminous compared to the background stars, and no existing method could separate the feeble starlight from the overwhelming solar glare. Einstein would have to wait for an eclipse after all. The young German astronomer Erwin Freundlich became an enthusiastic advocate for testing Einstein's prediction and undertook considerable efforts to organize an expedition for this purpose. Freundlich worked at the Royal Observatory in Berlin and had become captivated by Einstein's ideas, corresponding with him regularly and taking upon himself the task of arranging the practical details that would be necessary to observe an eclipse under favorable conditions. The total solar eclipse of August 21, 1914, would be visible from a path crossing Eastern Europe and into Russia, and Freundlich planned to lead a German expedition to the Crimean Peninsula, where the weather prospects seemed reasonably good and the duration of totality would be sufficient for careful photographic work. The preparations were extensive, involving the transportation of delicate telescopes and cameras, the arrangement of travel and accommodations, and the coordination with local authorities to secure suitable observing sites. Freundlich and his small team arrived in Crimea in the summer of 1914, setting up their equipment and preparing for the eclipse that would occur in late August. The theoretical prediction stood ready to be tested, the instruments were in place, and the astronomers waited with quiet anticipation for the moon's shadow to sweep across the landscape and reveal the stars that hid so close to the sun. But history intervened in a manner that no scientific calculation could have predicted. On the 1st of August, 1914, Germany declared war on Russia, and the great conflict that would become known as the First World War began its terrible unfolding across the European continent. The German astronomers in Russian territory were now enemy nationals, and the Russian authorities moved swiftly to detain them. Freundlich and his colleagues found themselves arrested and held as prisoners of war, their scientific equipment confiscated, their expedition brought to an abrupt and unhappy end before any observations could be made. In retrospect, this failure may have been a peculiar stroke of fortune for Einstein's reputation, though of course he did not know it at the time. Had Freundlich succeeded in measuring the deflection during that 1914 eclipse, he would have been testing the prediction of 0.87 arcseconds, the value Einstein had calculated in 1911 using only the equivalence principle and the curvature of time. As it happened, Einstein's theory was not yet complete in 1914, and that earlier prediction would prove to be incorrect by a factor of 2. The war, by preventing the measurement, inadvertently spared Einstein the embarrassment of having his incomplete theory apparently refuted before he had the chance to finish it properly. The years that followed saw Einstein laboring intensively on the mathematical formulation of his gravitational theory, struggling with the tensor calculus and the geometric concepts that would eventually yield the full field equations of general relativity. By November of 1915, as we have discussed elsewhere in this narration, Einstein had finally arrived at the complete and consistent set of equations that described gravity as the curvature of spacetime itself. And when he turned once more to the calculation of light deflection, applying the new and more sophisticated mathematics of his finished theory, he discovered that the predicted bending was twice as large as he had previously thought. The corrected value came to approximately 1.75 arcseconds for light grazing the sun's limb, exactly double the 1911 prediction and double the Newtonian result as well. The reason for this doubling is both elegant and profound, arising from the fundamental nature of general relativity's geometric description of gravity. In the earlier calculation, Einstein had accounted only for the curvature of time, for the slowing of clocks and the stretching of temporal intervals in the presence of mass. Light, traveling along its path, experienced this temporal curvature and was deflected by an amount corresponding to 0.87 arcseconds. But in the complete theory, mass curves not only time but space as well. The spatial geometry near a massive body like the Sun is subtly warped, with distances and angles behaving differently than they would in the flat, uncurved space of our everyday intuitions. When light passes through this curved spatial region, it experiences an additional deflection beyond what the temporal curvature alone would produce. As it happens, the spatial contribution to the bending is equal in magnitude to the temporal contribution, and so the total deflection is the sum of the two, yielding exactly twice the Newtonian prediction. This doubling became one of the most distinctive signatures of general relativity, a clear and measurable difference between Einstein's theory and the older Newtonian framework, or indeed between the complete general relativity and Einstein's own earlier, incomplete formulation. A measurement of the deflection could now serve not merely to confirm that light bends in a gravitational field, which even Newtonian physics might accommodate in some fashion, but to discriminate between competing theories and establish which description of gravity was the more accurate. If the observed deflection were approximately 0.87 arcseconds, it would favor the Newtonian approach or the early Einstein. If it were approximately 1.75 arcseconds, it would support the full geometrical picture of general relativity. The stakes, in terms of theoretical implications, were considerable. Not all astronomers greeted Einstein's predictions with enthusiasm or acceptance. Charles Lane Poore, a professor of celestial mechanics at Columbia University in New York, was among the more vocal skeptics, questioning both the theoretical foundations of relativity and the possibility of making the precise measurements that would be needed to test it. Poore raised objections to the manner in which Einstein's theory departed from the established Newtonian framework that had served astronomers so well for over 2 centuries, and he expressed doubts about whether the small angular deflections at issue could be reliably distinguished from the various sources of error that plagued astronomical measurements. The positions of stars on photographic plates could be affected by the optical properties of the telescope, by atmospheric refraction, by the thermal expansion of the equipment in the varying temperatures of an eclipse field, and by numerous other subtle influences that might mimic or mask the signal being sought. Poore was not alone in his caution, and a certain guardedness characterized the response of the broader astronomical community to Einstein's claims. Despite such skepticism, efforts to test the prediction continued as the war years passed and new eclipse opportunities arose. A total solar eclipse on June 8, 1918, would be visible across the United States, with the path of totality crossing through the state of Washington in the Pacific Northwest. American astronomers organized expeditions to observe this event, setting up their equipment at sites along the eclipse track and preparing to capture the star field around the darkened sun. The Lick Observatory in California dispatched a team, and hopes were reasonably high that clear skies might permit the crucial observations. But the weather, that perennial adversary of eclipse astronomers, failed to cooperate. Clouds obscured the sky at the critical moment, and the photographs that were obtained proved inadequate for extracting a reliable measurement of the deflection. The 1918 eclipse joined the growing list of missed opportunities, of expeditions mounted and preparations made, only to be thwarted by the caprice of the atmosphere. Indeed, the history of eclipse astronomy is littered with such disappointments, stretching back many decades before Einstein's prediction added new significance to these events. Eclipses are brief, lasting only minutes or sometimes merely seconds at any given location, and they occur along narrow tracks that may cross remote or inaccessible regions of the Earth's surface. Transporting heavy telescopes and delicate photographic equipment to these locations, often far from established observatories and the infrastructure they provide, posed considerable logistical challenges. And having made all such arrangements, The astronomers remained at the mercy of local weather conditions on the single day, indeed the single brief interval, when the eclipse would occur. Clouds at the wrong moment could render months of preparation entirely fruitless, and there would be no second chance until the next suitable eclipse, perhaps years in the future. Einstein, awaiting the outcome of these various expeditions with understandable interest, continued to express confidence in his theoretical prediction while acknowledging the difficulty of the measurements required to confirm it. The deflection of starlight was, to his mind, a natural and inevitable consequence of the geometric principles that underlay general relativity, a straightforward deduction from the curvature of spacetime that his field equations described. The challenge lay not in the theory but in the practice, in the demanding art of precision astronomy conducted under the unusual and often adverse conditions of a total solar eclipse. As the decade drew toward its close, with the war ending in November of 1918 and the world beginning its slow recovery from the devastation of the conflict, new eclipse opportunities appeared on the horizon. The eclipse of May 29, 1919, would offer particularly favorable circumstances for testing Einstein's prediction, with the Sun positioned against a rich field of bright stars in the Hyades cluster, providing numerous reference points for measuring any deflection. British astronomers, led by Arthur Stanley Eddington and Frank Watson Dyson, were already making plans for expeditions to observe this eclipse, and the stage was being set for what would prove to be one of the most celebrated scientific investigations of the 20th century. But that story belongs to another section of this narration, and for now we may simply note that the question of light deflection, posed by Einstein in 1911 and refined by his completed theory in 1915, remained open and awaited its empirical resolution. The prediction itself, however, stood as a testament to the remarkable reach of theoretical physics, to the capacity of mathematical reasoning to anticipate the behavior of nature in circumstances far removed from everyday experience. That a physicist working with pencil and paper in Zurich or Berlin could calculate, from first principles, the precise angle by which a ray of starlight would bend as it passed the Sun, some 93 million miles from Earth, was itself a striking achievement, whatever the outcome of the observational tests might prove to be. And the doubling of the predicted deflection between 1911 and 1915, arising from Einstein's recognition that space as well as time must curve in the presence of mass, illustrated beautifully how the deepening of theoretical understanding could lead to quantitatively different predictions, to numbers that could be checked against the world and that could therefore distinguish between competing conceptions of physical reality. So the deflection of starlight remained, through these years, a promise and a challenge, an invitation extended from theory to observation, patient and unhurried, awaiting the clear skies and steady hands that would eventually bring it to resolution. The story continues, as all such stories do, in its own time and at its own gentle pace, and we may rest content for now in the knowledge that the questions posed were good ones, carefully framed and precisely stated, and that the answers, when they came, would illuminate the nature of gravity and light and the graceful curvature of the cosmos in which we find ourselves. Karl Schwarzschild was, by the autumn of 1915, one of the most distinguished astronomers in all of Germany, and indeed in all of Europe, holding the prestigious position of director of the Astrophysical Observatory at Potsdam, which was widely regarded as one of the finest astronomical institutions in the world at that time, equipped with excellent telescopes and staffed by capable researchers who looked to Schwarzschild for guidance and inspiration in their scientific endeavors. He had come to this position through years of remarkable achievement, Having shown extraordinary mathematical talent from a very young age, publishing his first paper on the theory of celestial orbits when he was only 16 years old, and subsequently building a career that combined deep theoretical insight with practical observational skill, a combination that was relatively rare even among the most accomplished scientists of his generation. His work ranged across many areas of astronomy and physics, including the measurement of stellar brightnesses, the theory of how light travels through the atmospheres of stars, and the application of photography to astronomical observation, and in each of these areas he made contributions that were recognized and valued by his colleagues throughout the international scientific community. The observatory at Potsdam, situated just outside Berlin in the pleasant surroundings of the Prussian capital's hinterland, provided Schwarzschild with the resources and the intellectual environment he needed to pursue his varied research interests, and he had settled into a productive routine of observation, calculation, and correspondence with other scientists, enjoying the comfortable life of a senior academic in one of the world's great centers of learning. He had a wife and children, a respected position, and every reason to believe that his future would continue along the peaceful and productive path he had established, contributing to human knowledge through the patient and methodical work that characterizes the best of scientific endeavor. The nights at the observatory were long and quiet, filled with the slow turning of telescope domes and the careful recording of starlight, and the days were occupied with the equally patient work of analysis and interpretation, seeking to understand the messages carried by the light that had traveled such enormous distances to reach the waiting instruments. When the war began in August of 1914, Schwarzschild was already 40 years old, well past the age at which men were typically called upon to serve in military forces, and with his prominent scientific position, he could easily have remained at his observatory, continuing his research while younger men went off to fight in the trenches and the fields of Belgium and France and the vast expanses of the Eastern Front. Many scientists of his stature did exactly this, and no one would have thought less of him for choosing to remain at his post, contributing to the war effort, if he felt so inclined, through whatever scientific work might be deemed useful to the military authorities. But Schwarzschild made a different choice, one that reflected something deep in his character, a sense of duty or patriotism, or perhaps simply a restlessness that made it impossible for him to remain safely at home while others of his countrymen were facing danger and hardship in the service of their nation. He volunteered for military service, leaving behind his observatory, his research, his comfortable life, and his family, to join the German armed forces as a technical specialist, applying his considerable mathematical abilities to the practical problems of modern warfare. The German military, recognizing the value of having a scientist of Schwarzschild's caliber available for technical work, assigned him to duties that made use of his expertise in calculation and measurement, and he found himself working on the mathematics of artillery trajectories, computing the paths that shells would follow as they arced through the air toward distant targets, accounting for the effects of wind and air resistance and the rotation of the Earth, all of which influence where a projectile will land when fired from the enormous guns that had come to dominate the battlefields of this new kind of war. He served first in Belgium, where the German advance had stalled into the static warfare of trenches and fortifications that would characterize most of the Western Front, and then he was transferred to the Eastern Front, where the war against Russia had a somewhat different character, with more movement and maneuver across the vast distances of Eastern Europe. The conditions were difficult, the work was demanding, and the environment was entirely unlike the quiet observatory where he had spent so many productive years, but Schwarzschild applied himself to his military duties with the same conscientiousness that had marked his scientific career, performing the calculations that helped the artillery officers aim their guns with greater precision. Though one imagines that such work must have weighed upon a man whose life had been devoted to understanding the cosmos rather than to the destruction of human beings. It was during this time, while serving on the Russian front in the harsh conditions of military life, far from libraries and observatories and the comfortable surroundings conducive to concentrated thought, that Schwarzschild somehow obtained copies of the papers that Albert Einstein had presented to the Prussian Academy of Sciences during November of 1915, the papers in which Einstein had finally completed his general theory of relativity by arriving at the correct field equations that describe how matter and energy curve the fabric of spacetime. How these papers reached Schwarzschild at his military posting is not entirely clear, but the network of scientific communication, though disrupted by the war, had not been entirely severed, and important publications still found their way to interested readers even under the most unpromising circumstances. Perhaps a colleague sent them, or perhaps they arrived through some official channel, but arrive they did, and Schwarzschild, despite the demands of his military work and the discomforts of life at the front, found time to read them carefully and to think about what they meant. Einstein's field equations were, and remain, notoriously difficult to solve, being a set of 10 coupled nonlinear partial differential equations that relate the geometry of spacetime to the distribution of matter and energy within it, and Einstein himself had not been able to find exact solutions except in certain limiting cases and approximations. He had used approximation methods to derive predictions about the perihelion of Mercury and the bending of starlight, but an exact solution to the full equations for any realistic physical situation seemed like a distant goal, perhaps achievable eventually through great mathematical effort, but not something one would expect to see in the immediate future. Einstein was surely aware that others would attempt to find such solutions, but he may have expected that it would take considerable time and effort before anyone succeeded. Schwarzschild, reading the papers by lamplight or candlelight in whatever quarters he occupied on the Russian front, his mind turning over the mathematical structures that Einstein had constructed, began to think about what would happen if one considered the simplest possible case, a single spherically symmetric mass sitting alone in otherwise empty space, and asked what the geometry of spacetime would be in the region surrounding such a mass. This was, in a sense, the most natural first problem to consider, analogous to the problem of a single-point mass in Newtonian gravity, which gives rise to the simple inverse square force law that Newton had discovered more than 2 centuries earlier, and which describes with excellent accuracy the gravitational attraction between the Sun and the planets, or between any two masses that are sufficiently small and sufficiently distant from one another. Within just a few weeks of reading Einstein's papers, Schwarzschild had found an exact solution to the field equations for this spherically symmetric case, a remarkable achievement that demonstrated both his exceptional mathematical ability and the depth of his physical intuition. He wrote up his results and sent them in a letter to Einstein, dated the 22nd of December, 1915, just a month after Einstein had presented the final form of his field equations to the Prussian Academy. The letter must have made a remarkable impression upon Einstein, who had been laboring over these equations for years and who had not expected that exact solutions would be found so quickly, if at all. Here was a complete and elegant mathematical expression for the geometry of spacetime around a spherically symmetric mass, derived not in some well-equipped research institute but in the field, under wartime conditions, by a man who was supposed to be calculating artillery trajectories rather than solving the fundamental equations of gravitational physics. Einstein responded with evident surprise and admiration, writing back to Schwarzschild to acknowledge the receipt of his solution and to express his appreciation for the elegance and simplicity of the result. In his reply, Einstein remarked that he had not expected that the exact solution could be formulated so simply, a comment that reflects both his genuine surprise at Schwarzschild's achievement and his generous acknowledgement of another scientist's contribution to the theory he had worked so hard to construct. The correspondence between the two men, conducted across the divide between civilian academia and military service, between the intellectual life of Berlin and the harsh realities of the Eastern Front, represents one of the more poignant episodes in the history of physics, a reminder that scientific thought can persist even in the most unlikely and uncongenial circumstances. The solution that Schwarzschild had found describes the geometry of spacetime outside a spherically symmetric mass, and it takes a form that looks rather different from the flat spacetime of special relativity, being curved in ways that depend on the mass of the central object and on the distance from that object. At large distances from the central mass, the spacetime described by Schwarzschild's solution gradually approaches the flat geometry of empty space, just as one would expect, since the gravitational effects of even a massive body become weaker and weaker as one moves further and further away. But closer to the central mass, the curvature becomes more pronounced, and the geometry departs more and more significantly from the flat Euclidean space of our everyday intuition. One of the most striking features of Schwarzschild's solution is the appearance of a special distance from the central mass at which something rather peculiar happens to the mathematical description of the geometry. This distance, which has come to be known as the Schwarzschild radius, depends on the mass of the central object, being larger for more massive objects and smaller for less massive ones, and at this distance, certain terms in the mathematical expression for the geometry become singular, meaning that they take on infinite values, which typically indicates that something physically significant is happening. For an object like the Sun, the Schwarzschild radius works out to be about 3 kilometers, which is far smaller than the actual radius of the Sun, so the Schwarzschild radius lies deep within the interior of the star, where the vacuum solution that Schwarzschild had found does not apply. For the Earth, the Schwarzschild radius is less than a centimeter, again far smaller than the actual size of the planet. Schwarzschild himself, and Einstein, and the other physicists who studied this solution in the years following its discovery, did not fully understand the physical significance of this special radius, and indeed there was considerable confusion and disagreement about what, if anything, it meant for many decades afterward. It was only much later, in the middle of the 20th century, that physicists came to understand that the Schwarzschild radius represents the boundary of what we now call a black hole, an object so compact that its Schwarzschild radius lies outside its surface, meaning that the peculiar geometry at and within this radius is not hidden inside the object but is actually present in the external spacetime. If a star were to collapse to such a density that all its mass were contained within its Schwarzschild radius, then the surface at this radius would become what is called an event horizon, a boundary from within which nothing, not even light, can escape to the outside universe. But all of this understanding lay in the future, and in 1915 and 1916, the Schwarzschild solution was simply a beautiful piece of mathematics, an exact solution to Einstein's equations that could be used to make predictions about the behavior of test particles and light rays in the vicinity of a massive body, confirming and extending the approximate calculations that Einstein had already made. The solution showed that Einstein's theory, despite the complexity of its field equations, could yield tractable and illuminating results when applied to problems of physical interest, and it encouraged other mathematicians and physicists to seek further exact solutions for other configurations of matter and energy. Schwarzschild was not content to rest with this first solution, remarkable as it was, and in January of 1916, he sent Einstein a second paper, containing another exact solution to the field equations, this time describing the geometry of spacetime inside a spherically symmetric object of constant density, such as an idealized star composed of incompressible fluid. This interior solution complemented his earlier exterior solution, and together the two solutions provided a complete description of the geometry both inside and outside a simple model of a star, showing how the curvature of spacetime varies from the center of the star, where it is most pronounced, through the surface of the star, and out into the empty space beyond. Einstein communicated both of Schwarzschild's papers to the Prussian Academy of Sciences, where they were presented and published, ensuring that Schwarzschild's contributions would become part of the permanent record of scientific achievement. Even as he was producing this remarkable work, however, Schwarzschild's health was failing. At some point during his military service, he had contracted a rare and serious skin disease called pemphigus, an autoimmune condition in which the body's immune system attacks the skin and mucous membranes, causing painful blisters and lesions that can cover large portions of the body. In the early 20th century, before the development of modern treatments, pemphigus was often fatal, and the conditions of military life, with their lack of proper medical facilities and the general hardship of existence at the front, could only have made Schwarzschild's situation more difficult. He was eventually evacuated from the front and returned to Germany for medical treatment, but the disease proved intractable. Karl Schwarzschild died on the 11th of May, 1916, at the age of only 42, his life cut short by illness contracted during his military service, his brilliant mind silenced just as he had made some of his most profound contributions to theoretical physics. He left behind a body of work that would continue to influence astronomy and physics for generations, and a family that had to carry on without him. His death was mourned throughout the scientific community, not only in Germany but internationally, as news of his passing reached colleagues in other countries despite the barriers erected by the ongoing war. Einstein himself delivered a memorial address to the Prussian Academy of Sciences, honoring Schwarzschild's memory and acknowledging the significance of his contributions to the new theory of gravitation. In his address, Einstein spoke of Schwarzschild's exceptional combination of theoretical brilliance and practical skill, his wide-ranging interests and accomplishments, and the unfortunate circumstances that had cut short such a promising life. Einstein's words reflected genuine respect and admiration for a colleague who had, in the most difficult of circumstances, managed to extend and illuminate the theory that Einstein had spent so many years constructing. The Schwarzschild solution has become one of the foundational results in general relativity, appearing in every textbook on the subject and serving as the starting point for understanding more complex and realistic gravitational systems. Students learning general relativity for the first time typically encounter this solution early in their studies, learning to derive it and to extract from it the predictions that can be compared with observation, such as the bending of light around massive objects and the precession of orbits in strong gravitational fields. The black hole solutions that were eventually understood to follow from Schwarzschild's work have become central to modern astrophysics, with black holes now known to exist throughout the universe, at the centers of galaxies and in the remnants of massive stars, their properties described by the mathematics that Schwarzschild first worked out in the unlikely setting of the Russian front during the First World War. It is a remarkable fact of scientific history that one of the most important solutions in all of theoretical physics was found not in a well-equipped research institute but in the field, by a man serving as an artillery specialist, reading papers by lamplight and working out calculations in whatever spare moments he could find between his military duties. Schwarzschild's achievement stands as a testament to the power of mathematical insight and the persistence of the scientific spirit even in the most adverse circumstances, and his early death reminds us of the human cost of war, which claims not only the lives of ordinary soldiers but also the futures of those whose contributions to human knowledge might have been immeasurable had they been allowed to live out their natural span of years. And so we arrive now at the equations themselves, the mathematical heart of Einstein's general theory of relativity, and I want you to know that while these equations are among the most beautiful and profound ever written, we can understand their meaning, their structure, and their purpose without needing to perform any calculations at all. And in fact, the conceptual content of these equations is something that Einstein himself worked very hard to express in plain language, because he understood that the deepest truths of physics should be communicable to anyone willing to listen patiently and think carefully, and so that is what we shall do now, together, as we explore the architecture of these field equations in a spirit of calm inquiry. The field equations of general relativity are often written in a compact form that looks deceptively simple, just a short line of symbols that fits easily on a single page, and yet contained within that brevity is an entire theory of gravity, of space, of time, and of the relationship between matter and the geometry of the universe, and the equations tell us, in precise mathematical language, how the presence of matter and energy shapes the curvature of spacetime, and how that curvature in turn influences the motion of matter and energy, creating a beautiful and self-consistent dance between content and container, between stuff and the stage upon which that stuff exists, and this reciprocal relationship is perhaps the most important conceptual insight of the entire theory. Let us begin with the left-hand side of the equations, which deals with the geometry of spacetime, with curvature and shape and the way that distances and durations are measured in a universe where gravity is present, and the central object here is something called the metric tensor, which physicists denote with the symbol g followed by two small subscripts, often written as mu and nu. And this metric tensor is not a single number but rather a collection of numbers, a mathematical object that contains all the information needed to calculate distances and angles and time intervals in a particular region of spacetime, and you can think of it as a kind of field guide to the local geometry, a set of instructions that tells you how to measure things properly when you are in a curved spacetime rather than the flat spacetime of special relativity. In flat spacetime, the kind we encounter in special relativity when gravity is absent or negligible, the metric tensor takes a particularly simple form, and measuring distances follows the familiar rules we might expect. But in the presence of gravity, in the presence of massive objects that warp the fabric of spacetime, the metric tensor becomes more complicated, its components varying from place to place and from moment to moment, encoding the curvature that gravity produces, and so the metric tensor is in some sense the primary object of the theory, the thing we are trying to determine, the unknown quantity that the field equations allow us to solve for, given some particular distribution of matter and energy. The metric tensor has 10 independent components, which might seem like a lot until you realize that it must describe the geometry of a four-dimensional spacetime, with 3 dimensions of space and 1 of time, and the relationships between all of these dimensions with each other. And these 10 components are not arbitrary but are related to each other in specific ways by the requirement that the laws of physics must look the same to all observers regardless of their state of motion. and this requirement of general covariance, as it is called, places strong constraints on what forms the metric tensor can take, and this was one of the key insights that guided Einstein toward the correct equations. Now, the metric tensor tells us about geometry, but the equations also need to express how that geometry is curved, and for this purpose Einstein employed another mathematical object called the Ricci tensor, which is also denoted with two subscripts, typically the same mu and nu that appear in the metric tensor, and the Ricci tensor is derived from the metric tensor through a series of mathematical operations involving derivatives, which measure how things change from point to point, and the Ricci tensor captures essential information about the curvature of spacetime, specifically a kind of averaged curvature that tells us whether spacetime is being compressed or expanded in various directions, and this is precisely the kind of curvature information that is relevant to gravity. The Ricci tensor is itself derived from a more fundamental object called the Riemann curvature tensor, which contains complete information about the curvature of spacetime at each point, including information about tidal forces and the way that nearby objects moving along parallel paths might converge or diverge due to gravity. And the Riemann tensor has many more components than the Ricci tensor, but for the purposes of the field equations, Einstein found that the Ricci tensor, which is a kind of contraction or simplified summary of the Riemann tensor, was exactly what was needed to express the relationship between curvature and matter. There is also a quantity called the Ricci scalar, which is a single number obtained by a further contraction of the Ricci tensor, and this scalar represents a kind of total or overall curvature at each point in spacetime, and Einstein found that the correct combination of the Ricci tensor and the Ricci scalar, arranged in a particular way, was needed to ensure that the equations had the right mathematical properties. Specifically that they were consistent with the conservation of energy and momentum, and this combination appears on the left-hand side of the field equations in a form that mathematicians call the Einstein tensor, which has a beautiful property of having zero divergence, meaning that it automatically respects the conservation laws that physics requires. And so the left-hand side of Einstein's field equations contains geometric information, encoded in the Ricci tensor and the metric tensor and the Ricci scalar, all combined in just the right way to describe the curvature of spacetime, and this left-hand side is set equal to the right-hand side, which contains information about the matter and energy that is causing that curvature, and this equality, this balance between geometry on one side and matter-energy on the other, is the mathematical expression of the profound physical insight that matter and geometry are intimately connected, that they influence each other in a reciprocal fashion. The right-hand side of the equations involves something called the stress-energy tensor, which physicists denote with the symbol T followed by the same subscripts mu and nu. And this tensor is a mathematical object that contains all the information about the matter and energy present at each point in spacetime, including not just the density of mass and energy but also the flow of energy from place to place, the pressure exerted by matter and radiation, and the stresses and strains within material objects, and all of this information is relevant to gravity because in general relativity, all forms of energy and momentum contribute to the curvature of spacetime, not just mass as in Newton's theory. The stress-energy tensor has the same 10 independent components as the metric tensor, which is satisfying from a mathematical perspective because it means the equations are properly balanced, with 10 equations relating the 10 unknown components of the metric to the 10 components describing matter and energy. And this balance ensures that the system of equations is neither underdetermined nor overdetermined, and that solutions can in principle be found given appropriate boundary conditions and initial data, Though in practice finding exact solutions to Einstein's equations is notoriously difficult, and only a handful of exact solutions are known even after more than a century of study. The relationship between the two sides of the equation has been summarized in a phrase that is often attributed to the physicist John Wheeler, though the sentiment certainly goes back to Einstein himself, and the phrase goes something like this: that matter tells spacetime how to curve, and spacetime tells matter how to move, and this captures beautifully the reciprocal nature of the relationship, the way that matter and geometry influence each other in a continuous feedback loop, with the distribution of matter determining the curvature of spacetime through the field equations, and that curvature then determining how matter moves through the principle that objects follow the straightest possible paths, called geodesics, through the curved spacetime geometry. This mutual influence, this back and forth between matter and geometry, is one of the features that makes general relativity so much more complex than Newtonian gravity, where space is simply a fixed background that does not respond to the matter within it, and in Newton's theory you can calculate the gravitational field produced by some distribution of matter and then calculate how objects move in that field, treating these as separate steps. But in general relativity, the geometry and the matter are coupled together in a way that makes the equations nonlinear, meaning that the solutions do not simply add together in a straightforward way, and this nonlinearity is responsible for many of the most interesting and exotic phenomena predicted by the theory, including black holes and gravitational waves. The constant of proportionality that relates the left-hand side to the right-hand side involves Newton's gravitational constant, which appears in the theory of general relativity just as it did in Newton's original theory, ensuring that general relativity makes the same predictions as Newton's theory in the appropriate limit, and this brings us to an important point about the relationship between the two theories. Namely that Newton's gravity is contained within Einstein's gravity as a special limiting case, valid when gravitational fields are weak, when objects are moving slowly compared to the speed of light, and when pressures are low compared to energy densities, and in this limit the complicated tensor equations of general relativity reduce to the simple inverse square law of Newtonian gravity, which is reassuring because Newton's theory has been tested extensively and works beautifully for most everyday and astronomical purposes. This limiting behavior was something Einstein worked hard to verify, because any new theory of gravity had to be consistent with the enormous body of evidence supporting Newton's theory, including the beautiful agreement between Newton's predictions and the observed motions of the planets, at least for all the planets except Mercury, whose orbital precession provided one of the first confirmations of general relativity. And the fact that Einstein's equations reduce to Newton's in the appropriate limit is not accidental but is built into the structure of the theory through the careful choice of the constant of proportionality and the specific form of the equations. Now, in 1917, just 2 years after completing the field equations, Einstein made a modification to his theory that he would later come to regret, and the modification involved adding a new term to the equations, a term proportional to the metric tensor itself, with a proportionality constant that Einstein called lambda and that has come to be known as the cosmological constant, and Einstein's motivation for adding this term was cosmological, relating to his beliefs about the structure of the universe as a whole. At that time, the prevailing view among astronomers and physicists was that the universe was static, neither expanding nor contracting, simply existing in a steady state for all eternity, and this view seemed consistent with observations, which did not yet reveal the expansion of the universe that Edwin Hubble would later discover in the 1920s, and Einstein found that his original field equations did not admit solutions describing a static universe filled with matter. because the gravitational attraction of the matter would cause such a universe to collapse, and so he introduced the cosmological constant as a kind of repulsive effect that could balance the attractive effect of gravity and allow for a static cosmological solution. The cosmological constant term involves the metric tensor multiplied by a constant, and when this term is positive it acts as a kind of negative pressure or repulsive gravity, pushing things apart rather than pulling them together, and Einstein chose the value of the constant precisely to balance the attractive gravity of the matter in the universe, resulting in a static model that he found philosophically satisfying, and he published this modification in his 1917 paper on cosmological considerations. However, when Edwin Hubble discovered in 1929 that the universe is in fact expanding, with distant galaxies receding from us at speeds proportional to their distances, Einstein realized that the static universe he had tried to achieve was not only unnecessary but actually unstable, and that his original equations without the cosmological constant would have predicted an expanding or contracting universe, which would have been a remarkable theoretical prediction confirmed by observation. And Einstein reportedly referred to the introduction of the cosmological constant as his greatest blunder, though there is some historical debate about whether he actually used those exact words, but certainly he regretted the missed opportunity to have predicted the expansion of the universe. The cosmological constant has had a curious subsequent history, being discarded and then revived multiple times over the following decades, and in recent years it has returned to prominence because observations of distant supernovae suggest that the expansion of the universe is actually accelerating, which can be explained by a small positive cosmological constant, and so what Einstein considered his greatest blunder has turned out to be relevant after all, though the physical interpretation of the cosmological constant remains mysterious and is connected to deep questions about the vacuum energy of empty space and the nature of dark energy. Let us turn now to some of the mathematical properties of the field equations that give them their particular character and make them both beautiful and challenging to work with, and one important property is their nonlinearity, which we have already mentioned, and which means that if you have two solutions to the equations you cannot simply add them together to get a third solution, as you can with linear equations like those of Maxwell's electromagnetism, and this nonlinearity reflects the physical fact that gravity gravitates, that gravitational energy itself contributes to the curvature of spacetime, creating a self-interaction that makes the equations much more difficult to solve. The equations are also a system of partial differential equations, meaning they involve derivatives with respect to space and time, and they relate the curvature at each point to the matter and energy at that same point, and solving them requires specifying initial conditions on some surface and then evolving those conditions forward in time, and this initial value problem has been studied extensively by mathematicians, who have established conditions under which solutions exist and are unique, though the actual computation of solutions remains difficult except in cases with a high degree of symmetry. One of the most remarkable predictions to emerge from Einstein's field equations came very shortly after their publication, when Einstein himself showed in 1916 that the equations predict the existence of gravitational waves, which are ripples in the fabric of spacetime itself, propagating outward from accelerating masses at the speed of light, much as electromagnetic waves propagate outward from accelerating charges. And this prediction was extraordinary because it suggested that spacetime is not merely a passive backdrop but a dynamic entity that can carry energy and information across the cosmos. Einstein's analysis of gravitational waves involved linearizing the field equations, meaning he considered small perturbations to a flat spacetime background and showed that these perturbations satisfy a wave equation, with solutions representing ripples traveling at the speed of light, and he calculated the properties of these waves, including how they would stretch and squeeze space in directions perpendicular to their direction of travel, and he considered what kinds of sources might produce detectable gravitational waves, though he concluded that any waves produced by realistic astronomical sources would be far too weak to detect with the technology of his time. Interestingly, Einstein himself later had doubts about the reality of gravitational waves, and in 1936 he submitted a paper with his collaborator Nathan Rosen arguing that gravitational waves were not real physical phenomena but merely mathematical artifacts that could be transformed away by a suitable choice of coordinates, and this paper was initially rejected by Physical Review, which sent it to a referee who found an error in the analysis. And Einstein was annoyed by this unprecedented experience of having his work reviewed and initially withdrew the paper, but he later acknowledged the error and published a revised version accepting the reality of gravitational waves, though the episode shows how subtle and confusing these questions could be even for the theory's creator. The prediction of gravitational waves would not be directly confirmed until 2015. Exactly 1 century after Einstein completed his field equations, when the LIGO detectors observed gravitational waves from the merger of 2 black holes, and this observation was a spectacular confirmation of general relativity, demonstrating that space-time really does ripple and that these ripples can propagate across billions of light-years to reach detectors on Earth. And the waveform observed matched precisely the predictions of Einstein's equations, providing one of the most stringent tests of the theory ever performed. The field equations also predict the existence of black holes, regions of spacetime where the curvature becomes so extreme that nothing, not even light, can escape, and the first black hole solution was found by Karl Schwarzschild in late 1915. Just weeks after Einstein published his field equations, and Schwarzschild's solution describes the spacetime geometry outside a spherical, non-rotating mass, and it contains a curious feature, a surface at a particular radius where the metric tensor becomes singular, and this surface is what we now call the event horizon of a black hole, though the physical interpretation of this feature was not understood for decades. And Einstein himself was skeptical that such objects could actually form in nature. And so the field equations of general relativity, compact in their symbolic expression but vast in their implications, describe a universe in which matter and geometry are woven together in an intimate dance, where the presence of mass and energy curves the fabric of space-time, and that curvature guides the motion of everything within it. And contained within these equations are predictions of expanding universes and gravitational waves, of black holes and the bending of light, and even of the possible existence of a cosmological constant that might drive the acceleration of cosmic expansion, and all of this flows from the mathematical structure that Einstein labored for nearly a decade to discover, guided by physical intuition and mathematical beauty, toward a description of gravity that remains our best understanding of this most familiar and most mysterious of forces. And now we come to one of the more peculiar predictions to emerge from general relativity, a consequence that Einstein himself found so strange, so mathematically troublesome, that he would spend decades uncertain whether it was real at all, changing his mind more than once, publishing papers that contained errors, and generally displaying the kind of confusion that reminds us that even the greatest minds must feel their way through difficult terrain, making wrong turns, retracing steps, and sometimes arriving at the correct destination only after considerable wandering, which is all rather reassuring if you think about it, because it suggests that understanding comes not from instant insight but from patient, persistent effort, the kind of effort that we need not make right now, as we simply listen and let the story unfold at its own gentle pace. In 1916, Just 1 year after completing the full field equations of general relativity, Albert Einstein returned to his theory to explore one of its more subtle implications, and what he found was that the equations predicted something quite remarkable, something that no one had anticipated and that seemed almost too strange to be true, namely that the fabric of spacetime itself could ripple and vibrate, that disturbances in the gravitational field could propagate outward from their source like waves spreading across the surface of a pond, traveling through the universe at exactly the speed of light, carrying energy and information about the violent events that had created them, events like colliding stars or accelerating masses, and these ripples, these gravitational waves as he called them, represented an entirely new way of thinking about gravity, not as a static force but as a dynamic phenomenon capable of motion and change, of carrying influence from one place to another through the very geometry of space and time. To derive this prediction, Einstein employed what is called a linearized approximation, which is a mathematical technique that simplifies very complicated equations by assuming that certain quantities are small, small enough that their squares and higher powers can be ignored without significant loss of accuracy, and in this case the assumption was that the gravitational field is weak, meaning that spacetime is only slightly curved, only gently disturbed from the perfect flatness that would exist in the complete absence of matter and energy, and under these conditions the fearsome complexity of the full field equations becomes much more manageable, reducing to something that resembles the familiar wave equations of classical physics, the same kind of equations that describe how sound travels through air or how electromagnetic waves propagate through the vacuum. And what Einstein found was that small perturbations in the metric of spacetime, the mathematical object that describes how distances and times are measured at each point, would indeed travel outward at the speed of light, oscillating as they went, stretching space in one direction while compressing it in the perpendicular direction, then reversing, stretching and compressing in an alternating pattern that would continue as long as the wave persisted, growing weaker with distance from the source but never quite disappearing entirely. The speed at which these waves travel is significant because it tells us something fundamental about the nature of gravity in Einstein's theory, namely that gravitational influence cannot be transmitted instantaneously, cannot leap across the universe in no time at all as Newton's theory had seemed to suggest, but must instead propagate at a finite speed, the same speed that limits all causal influences in the universe, the speed of light, which means that if the sun were to suddenly vanish, we would not feel the gravitational consequences for approximately 8 minutes, the same 8 minutes it takes sunlight to reach us, and this finite propagation speed is essential for the internal consistency of the theory, for without it there would be paradoxes involving cause and effect, effects preceding their causes in certain reference frames, the kind of logical impossibilities that a well-constructed theory must avoid. 2 years later, in 1918, Einstein made further progress on the mathematical description of gravitational waves by deriving what is now called the quadrupole formula, which describes how much gravitational radiation is emitted by a system of moving masses, and this formula tells us something important and rather sobering about gravitational waves, namely that they are extraordinarily weak, far weaker than the electromagnetic waves that we use every day for communication and sensing and countless other purposes, and the reason for this weakness is connected to a fundamental difference between gravity and electromagnetism, a difference in what kinds of radiation are possible, for in electromagnetism the simplest and strongest type of radiation is dipole radiation, which can be produced by a single oscillating charge. But in gravity the analogous dipole radiation is forbidden by the conservation of momentum, which ensures that the center of mass of an isolated system cannot oscillate, And so the simplest gravitational radiation that is allowed is quadrupole radiation, which requires not just one moving mass but a system of masses whose distribution has a time-varying shape, whose overall configuration is changing in a more complex way, and this quadrupole radiation is inherently much weaker than dipole radiation would be. The quadrupole formula that Einstein derived allows us to calculate, at least approximately, how much energy a gravitational wave carries, and when we apply this formula to real astronomical systems, we find that the numbers are humbling in their smallness. For even a binary star system consisting of two massive stars orbiting each other at considerable speed produces gravitational waves that carry away energy at an almost negligibly slow rate. So slow that such a system might orbit for millions or billions of years before radiating away a significant fraction of its orbital energy, and for systems here on Earth, for any apparatus we might construct in a laboratory, the gravitational waves produced are so feeble as to be completely undetectable, a mere whisper against the background noise of the universe. Which is one of the reasons that detecting gravitational waves from distant astronomical sources would prove to be such a monumental challenge, a challenge that would not be met for nearly a century. But before we speak of detection, we must acknowledge that the very existence of gravitational waves remained a matter of considerable doubt and confusion for many decades, and Einstein himself was not immune to this confusion. Indeed, he was perhaps the most notable example of it, for he struggled with the question of whether gravitational waves were real physical phenomena that could carry energy from one place to another, or whether they were merely mathematical artifacts, coordinate effects that could be transformed away by a clever choice of reference frame. And this question troubled him deeply because general relativity is fundamentally a theory about the geometry of spacetime. And in such a theory it can be surprisingly difficult to distinguish between genuine physical effects and mere changes in the way we describe things, between real waves and what might be called pseudowaves that appear or disappear depending on how we set up our coordinates. This confusion reached its most dramatic expression in 1936, some 20 years after the original prediction, when Einstein, now living in Princeton, New Jersey, collaborated with a younger physicist named Nathan Rosen on a paper that claimed to prove that gravitational waves do not exist after all, that what had appeared to be waves were in fact singular solutions to the field equations, solutions that became mathematically ill-behaved, infinite in some sense, and therefore unphysical. And Einstein was so confident in this conclusion that he submitted the paper to the Physical Review, the leading American physics journal, expecting it to be published without much fuss. But what happened next was something that Einstein had not anticipated and did not appreciate, for the Physical Review employed a system of peer review, sending submitted papers to experts in the field for evaluation before deciding whether to publish them. And the anonymous referee who reviewed Einstein's paper found what appeared to be a serious error in the mathematical reasoning. The referee who evaluated this paper was Howard Percy Robertson, an American mathematician and physicist who understood general relativity very well, and he identified a flaw in Einstein and Rosen's argument, a point at which their reasoning had gone astray, leading them to an incorrect conclusion. And the journal returned the paper to Einstein with the referee's comments, asking him to address the concerns before publication could proceed. But Einstein, who was unaccustomed to having his work scrutinized in this way, was offended by the process, so offended that he withdrew the paper from the Physical Review entirely and sent it instead to a less prominent journal that did not employ peer review. But here the story takes an interesting turn, for during this time Einstein was also discussing the matter with Leopold Infeld, another physicist working at Princeton, and through a series of conversations and independent analysis, Einstein came to realize that the referee had been correct after all, that there was indeed an error in the paper, and that gravitational waves did exist, though perhaps not in quite the form he and Rosen had originally imagined, and so the published version of the paper was substantially different from the rejected version, reaching essentially the opposite conclusion, which is a remarkable example of science working as it should, with errors being caught and corrected, even when those errors are made by the most famous scientist in the world. Around the same time, Arthur Eddington, the British astrophysicist who had done so much to promote and explain general relativity, expressed his own skepticism about gravitational waves in his characteristically witty manner, suggesting that the waves predicted by the theory might travel at the speed of thought rather than the speed of light, meaning that they might be nothing more than mathematical constructs with no physical reality, artifacts of our imagination rather than genuine features of the universe, and this quip captured a real concern that many physicists shared, a worry that the coordinate freedom of general relativity made it difficult or impossible to identify gravitational waves as truly physical phenomena, as things that could be detected by instruments and shown to carry energy from one place to another. The correspondence between Einstein and his old friend Max Born during this period reveals the depth of confusion that persisted even among the greatest physicists of the age, with Born writing to Einstein to inquire about the reality of gravitational waves and Einstein responding with explanations that sometimes seemed to settle the question and sometimes seemed to leave it more uncertain than before, and this uncertainty was not a failure on Einstein's part, not a sign of diminished powers, but rather a reflection of the genuine difficulty of the problem. For general relativity is a subtle theory in which the distinction between real physical effects and coordinate artifacts requires careful thought, and it took many decades for the physics community to develop the conceptual tools and the mathematical techniques needed to answer the question definitively, to prove beyond doubt that gravitational waves are real, that they do carry energy, and that they can in principle be detected. The question of detection brings us to the 1960s and the pioneering work of Joseph Weber, an American physicist at the University of Maryland who devoted much of his career to the search for gravitational waves, designing and building the first instruments intended to sense their passage, and these instruments were called resonant bars, massive cylinders of aluminum that Weber isolated from external disturbances as carefully as he could. The idea being that a passing gravitational wave would cause the bar to vibrate slightly at its natural resonant frequency, and this vibration could be detected by sensitive strain gauges attached to the surface, amplified and recorded, and compared with similar signals from other bars at distant locations, because a genuine gravitational wave from a cosmic source would affect bars everywhere on Earth nearly simultaneously, while local disturbances would affect only individual bars. Weber built several of these resonant bars and operated them for years, patiently collecting data and searching for the telltale coincident signals that would indicate the passage of a gravitational wave, and in 1969 he announced that he had detected such signals, that gravitational waves were streaming past the Earth on a regular basis from sources at the center of our galaxy, and this announcement generated tremendous excitement in the physics community, for it seemed that the century-old prediction had finally been confirmed, but subsequent attempts by other research groups to replicate Weber's results were unsuccessful. Other bars were built and operated with even greater sensitivity, and they failed to see the signals that Weber had claimed to detect, and the consensus gradually emerged that Weber had been mistaken, that what he had seen was not gravitational waves but some other phenomenon, perhaps subtle correlations in noise that had mimicked the expected signal, and so the search continued, the gravitational waves remaining elusive, hidden behind the enormous technical challenges of detecting something so weak. The weakness of gravitational waves is worth contemplating for a moment, for it is truly extreme, and to understand why requires us to think about the numbers involved, the vast distances that astronomical gravitational waves must travel and the tiny stretching and squeezing of space that they produce when they arrive, for even the most violent events in the universe, the collision and merger of two black holes for instance, produce waves that by the time they reach Earth have amplitudes measured in parts in 10 to the power of 21 or 22, which means that a distance of 1 kilometer would be stretched or compressed by an amount roughly 1,000 times smaller than the diameter of a proton, and detecting such a minuscule change against the background of seismic vibrations and thermal fluctuations and quantum noise is a challenge that borders on the impossible, or so it seemed for many decades. The solution to this challenge came in the form of laser interferometry, a technique that uses the interference of light beams to measure distances with extraordinary precision, and beginning in the 1970s, physicists began to develop plans for gravitational wave detectors based on this principle, detectors consisting of two long perpendicular arms along which laser light would travel, bouncing back and forth between mirrors at the ends, and when a gravitational wave passed through, it would stretch one arm while compressing the other, changing the relative lengths and causing the light beams to interfere differently when they were recombined, and this change in interference could be measured with incredible sensitivity that improved as the arms were made longer and the lasers more powerful and the mirrors more perfectly reflective, and after decades of development and refinement, of solving countless technical problems and pushing technology to its limits, this approach finally succeeded. On the 14th of September, 2015, the two detectors of the Laser Interferometer Gravitational Wave Observatory, known as LIGO, located in Louisiana and Washington State in the United States, detected a gravitational wave for the first time, a wave that had been produced by the merger of two black holes more than 1 billion light-years away, two objects each with a mass approximately 30 times that of our Sun, spiraling toward each other and finally colliding in a cataclysm that released more energy in gravitational waves than all the stars in the observable universe were emitting in light at that moment. And yet this tremendous release of energy, after traveling for over 1 billion years across the expanding universe, arrived at Earth as a ripple so small that it stretched the 4-kilometer arms of the detectors by less than 1,000th of the width of a proton, and LIGO detected it, confirming at last the prediction that Einstein had made nearly 100 years earlier, proving that gravitational waves are real, that spacetime can ripple and vibrate, that the universe has a voice we had never before heard. This detection was not the end of anything but rather the beginning, the opening of a new window onto the cosmos, for in the years since 2015 there have been many more detections, gravitational waves from merging black holes and merging neutron stars and systems containing both, and each detection teaches us something new about the universe, about the populations of compact objects that exist in galaxies, about the violent processes that bring them together, about the nature of gravity itself in the extreme conditions where spacetime is most strongly curved, and all of this flows from those equations that Einstein wrote down in 1915 and 1916, from his patient working out of the consequences of his beautiful theory, even when those consequences seemed strange, even when he himself doubted them, even when decades passed without any experimental confirmation. And so we may rest now with the knowledge that the universe vibrates gently around us at every moment, that ripples in spacetime are passing through this very room as we speak, most of them far too weak to detect, remnants of cosmic events that happened long ago and far away, and there is something soothing in this thought, something peaceful in knowing that the fabric of space and time is not rigid but flexible, that it can carry waves like a vast and patient ocean, an ocean on which we float without even noticing its motion, drifting quietly toward sleep. And so we come now to a quieter sort of territory, one that concerns itself not with equations or experiments but with the deeper currents of thought that moved beneath Einstein's scientific work like slow water beneath ice. And we may take our time here, for these philosophical influences shaped his thinking in ways that are sometimes overlooked when we focus only on the mathematics, and yet without them, without the particular cast of mind that Einstein brought to his physics, the theory of general relativity might never have emerged at all, or might have emerged quite differently, in someone else's hands, at some other time. The figure who looms largest in this philosophical landscape is Ernst Mach, an Austrian physicist and philosopher who was born in 1838 and who spent much of his career examining the foundations of mechanics with a critical eye that spared nothing, not even Newton himself. And Mach's great work, published in 1883 and titled The Science of Mechanics, offered a historical and critical examination of the principles underlying classical physics, tracing their development from the earliest times and questioning assumptions that had gone unexamined for generations. And it was this book, read by Einstein during his student years, that left an impression so deep that its influence can be traced throughout the development of relativity theory, both special and general. Mach's critique of Newtonian physics centered on what he saw as metaphysical concepts smuggled into what purported to be an empirical science, and chief among these was Newton's notion of absolute space, that invisible, unchanging stage upon which all physical events were supposed to unfold, independent of any material content. And Newton had defended this concept with his famous bucket experiment, in which he imagined a bucket of water suspended by a twisted rope, and as the rope unwinds, the bucket begins to spin, and at first the water remains flat while the bucket rotates relative to it, but gradually the water begins to spin as well, and its surface becomes concave, curving upward at the edges, and Newton argued that this curvature must be caused by the water's rotation relative to absolute space, since at the moment when both bucket and water rotate together, there is no relative motion between them, and yet the surface remains curved. Mach found this argument unconvincing, and he proposed instead that what Newton attributed to absolute space might better be understood as an effect of the water's relation to the totality of matter in the universe, the distant stars and galaxies, or rather, as Mach would have known them, the fixed stars, for galaxies beyond our own had not yet been recognized as such, and in Mach's view, when we say that an object rotates or accelerates, we mean that it rotates or accelerates relative to the average distribution of matter in the cosmos, and if that distant matter were somehow removed, or rearranged, then the local effects we attribute to inertia might change or disappear entirely, and this idea, that inertia is not a property arising from some absolute space but is instead determined by the gravitational influence of all the matter in the universe, would later come to be known as Mach's principle, though it was Einstein himself who gave it that name. The young Einstein, working as a patent clerk in Bern and pondering the foundations of physics in his spare hours, found in Mach's writings a model for how one might approach fundamental questions, stripping away assumptions that had accumulated over centuries and asking what could actually be established on empirical grounds. And this critical attitude, this willingness to question even the most venerable authorities, became a hallmark of Einstein's own approach, and he later wrote that Mach's science of mechanics had a profound influence on him, shaking his dogmatic faith in mechanics as the final basis of all physical thinking, and opening his eyes to the possibility that concepts which seemed self-evident might in fact be conventions or approximations rather than absolute truths. Einstein's reverence for Mach was not merely intellectual but also personal, and he sought to establish contact with the older physicist, initiating a correspondence that continued intermittently over several years, and in 1913, Einstein traveled to Vienna to meet Mach in person, visiting him at his home, where the elderly philosopher, now in his 70s and partially paralyzed from a stroke, received him warmly, and the two discussed physics and philosophy, and Einstein presented his developing ideas about gravitation, hoping to show Mach how the general theory of relativity would incorporate Machian principles by treating the metric properties of spacetime as determined by the distribution of matter and energy, rather than as fixed features of an absolute background, and by all accounts the meeting went well, with Mach expressing interest in and approval of Einstein's direction. But the story takes a melancholy turn, for after Mach's death in 1916, there appeared a preface he had written for a book on optics, in which he disavowed the theory of relativity in surprisingly strong terms, rejecting both the special and general theories, and calling himself out from the company of those who promoted what he termed dogmatic relativity, and this rejection came as a painful surprise to Einstein, who had believed he was carrying forward Mach's program, and scholars have debated ever since whether this preface truly represented Mach's considered views or whether it might have been written during a period of mental decline, or perhaps even altered by his son, who held conservative views on physics. But regardless of the explanation, Einstein had to come to terms with the fact that his philosophical mentor had not endorsed the work that Einstein himself saw as a vindication of Machian thinking. And we should note that Mach's principle, as Einstein understood and named it, remains a subtle and somewhat elusive concept, for while Einstein originally hoped that general relativity would fully incorporate it, making the inertial properties of matter entirely dependent on the cosmic distribution of mass, the situation turned out to be more complicated, and the equations of general relativity permit solutions in which spacetime has definite geometric properties even in the absence of matter, which seems to contradict the Machian program, and Einstein struggled with this throughout his life, sometimes believing he had found a way to save Mach's principle within general relativity, and other times acknowledging that the connection was not as complete as he had hoped. And this remains an area of active research and philosophical discussion to this day, though we need not resolve it here, for our purpose is merely to note the influence and the aspiration. Beyond Mach, Einstein's philosophical development was shaped by a broader reading in the history of thought, and we may mention several figures whose ideas left their marks on his mind, beginning with the Scottish philosopher David Hume, whose treatise of human nature Einstein read during his Bern years, and Hume's radical empiricism, his insistence that all knowledge must ultimately derive from sense impressions, and his famous critique of causation as a matter of custom and habit rather than logical necessity, resonated with Einstein's own developing views about the relationship between theory and experience, and Einstein later credited Hume, along with Mach, with helping him break free from the concept of absolute time that had prevented others from recognizing the need for special relativity. Immanuel Kant also figured in Einstein's education, as he did in the education of most German-speaking intellectuals of that era, and while Einstein ultimately rejected Kant's doctrine that certain concepts, such as Euclidean geometry and absolute time, were synthetic a priori truths, necessary features of any possible experience, he engaged seriously with Kantian philosophy, and his rejection of it was informed and deliberate, based on the conviction that what Kant had taken to be necessary features of human cognition were in fact contingent assumptions that could be revised in light of new physical discoveries, and the development of non-Euclidean geometries in the 19th century, and their eventual application in general relativity, served as Einstein's most powerful demonstration that Kant had been wrong about the apodictic certainty of Euclidean space. The French mathematician and physicist Henri Poincaré also influenced Einstein's thinking, though the exact nature and extent of this influence has been much debated by historians, and Poincaré had written extensively on the philosophy of science, emphasizing the conventional element in physical theories, the way that certain choices, such as the choice of a particular geometry to describe space, are not forced upon us by experience but are made by us for reasons of convenience or simplicity. And this conventionalist perspective can be seen in some of Einstein's own discussions of the foundations of physics, particularly in his willingness to consider alternative geometric frameworks, though Einstein balanced this with a stronger commitment to physical realism than Poincaré typically expressed. And we should also mention Baruch Spinoza, the 17th-century Dutch philosopher, whose influence on Einstein was less direct but perhaps more personal, for Einstein expressed throughout his life an admiration for Spinoza's pantheistic vision of nature, the idea that God and nature are two names for the same infinite substance, and that everything that exists follows necessarily from this substance according to eternal laws. And while this is not a technical philosophical doctrine that shaped Einstein's physics in any specific way, it colored his broader worldview, his sense of the universe as orderly and comprehensible, governed by laws that human reason could aspire to discover, and it informed his famous remark that he believed in Spinoza's God, who reveals himself in the lawful harmony of all that exists, but not in a God who concerns himself with the fates and actions of individual human beings. Einstein's 1905 paper on special relativity, with its revolutionary treatment of simultaneity, offers a clear example of philosophical thinking in action, for the key insight that allowed Einstein to develop the theory was his recognition that the concept of simultaneity, which seems so natural and intuitive, actually requires an operational definition, a specification of how we would determine in practice whether two distant events happen at the same time. And when Einstein examined this question carefully, he found that the determination depends on the synchronization of clocks using light signals, and that observers in relative motion would arrive at different conclusions about which events are simultaneous, and this operationalist approach, asking what a concept means in terms of the measurements and procedures by which we apply it, reflects the influence of Mach and the broader empiricist tradition, though Einstein would later move away from strict operationalism toward a more realist philosophy. In the years following the completion of general relativity, Einstein's views on the philosophy of science underwent a gradual but significant shift, moving away from the positivist and empiricist tendencies of his earlier work and toward a form of realism that emphasized the independent existence of physical reality and the goal of science as describing that reality, not merely organizing our experiences. And this shift became particularly evident in his debates over quantum mechanics, where Einstein found himself arguing against the Copenhagen interpretation and its denial of definite values to unmeasured quantities, and he invoked philosophical principles, such as the idea that the moon exists whether or not anyone is looking at it, that sounded quite different from the Machian critiques of his youth. The logical positivists of the Vienna Circle, a group of philosophers and scientists who met regularly in Vienna during the 1920s and 1930s, claimed Einstein as one of their inspirations, seeing in his 1905 analysis of simultaneity a model for their own project of eliminating metaphysics from science by clarifying the meaning of concepts through their empirical content, and they celebrated Einstein as a philosophical ally. But Einstein himself was uncomfortable with this embrace, and he distanced himself from their more extreme claims, particularly their verificationist theory of meaning, which held that a statement is meaningful only if it can be verified by experience, and Einstein insisted that there was more to physics than the organization of observations, that the goal of the physicist is to grasp something of the objective reality underlying phenomena, even if our concepts always remain imperfect approximations. This tension between empiricism and realism runs through Einstein's philosophical writings, and he never fully resolved it to his own satisfaction, acknowledging on the one hand that our concepts must make contact with experience to have any content, and insisting on the other hand that science aims at something beyond mere description, at a picture of the world as it really is, and this philosophical position, which some have called critical realism, allowed Einstein to maintain both the Machian skepticism toward unobservable absolutes and the conviction that physics reveals genuine features of nature, though the balance between these two commitments shifted over the course of his career. And so we see that the development of general relativity was not merely a technical achievement but a philosophical one as well, reflecting Einstein's deep engagement with questions about the nature of space, time, matter, and the aims of physical theory, and Mach's influence is visible in the very formulation of the problem, the attempt to eliminate absolute space by making geometry depend on the distribution of matter, while the broader philosophical tradition, from Hume to Kant to Poincare, provided Einstein with conceptual tools and critical perspectives that enabled him to question assumptions others took for granted, and even as Einstein later moved toward a more realist philosophy, the Machian spirit of critique and reconstruction remained part of his intellectual heritage, a reminder that the greatest advances in physics often require not just new mathematics but new ways of thinking about what physics is and what it hopes to achieve. The story of Mach and Einstein also reminds us that intellectual debts are complicated things, that one can be profoundly influenced by a thinker without agreeing with everything that thinker said, and that the relationship between philosophy and physics is not one of simple derivation but of mutual illumination and sometimes creative misunderstanding, for Einstein took from Mach what he needed, a critical attitude and a particular way of framing questions, and built with these materials something that went beyond anything Mach himself had envisioned or, in the end, was willing to accept. And this is perhaps the way of all intellectual inheritance, that we honor our teachers not by repeating their conclusions but by carrying forward their spirit of inquiry into territories they could not have foreseen. When Albert Einstein published his complete theory of general relativity in November of 1915, the world was consumed by the terrible machinery of the Great War, and the scientific community itself had fractured along national lines, with German and British and French researchers largely unable to communicate with one another, their journals and letters interrupted by the hostilities that had engulfed the continent and beyond. The theory appeared in the Proceedings of the Prussian Academy of Sciences, written in German, and it might have languished there for years, unread by researchers in Allied nations, had it not been for a series of fortunate circumstances and the determined efforts of a few individuals who believed that science ought to transcend the boundaries of warring states. The initial reception among those German scientists who could access and understand the work was one of cautious admiration mixed with considerable perplexity, for the mathematics involved were formidable indeed, requiring facility with tensor calculus and differential geometry that few physicists of the era possessed, and the conceptual framework demanded a wholesale reimagining of space, time, and gravitation that ran counter to centuries of Newtonian thinking that had served so well for so long. In the Netherlands, which had maintained its neutrality throughout the conflict, the great physicist Hendrik Lorentz received copies of Einstein's papers and studied them with keen interest, for Lorentz had long been a supporter of Einstein's work and maintained a warm correspondence with him despite the difficulties of wartime communication. Lorentz was among the first to fully grasp the significance of what Einstein had achieved, and he worked to disseminate the theory to other neutral countries and, where possible, to colleagues in Allied nations who might be receptive to examining the work of a German-speaking scientist during such fraught times. The theory predicted several phenomena that differed from Newtonian gravity, including the precise amount by which Mercury's orbit precessed, which Einstein had already shown matched observations beautifully, and the degree to which light rays passing near a massive body like the Sun would be bent from their otherwise straight paths through the curved geometry of spacetime. It was this latter prediction, the bending of starlight, that offered the most promising avenue for experimental verification, though testing it would require observing stars whose light passed close to the Sun, something only possible during a total solar eclipse when the Moon blocked the overwhelming brightness of the solar disk and allowed faint background stars to become visible. Arthur Stanley Eddington was a British astronomer and physicist working at Cambridge, a man of Quaker faith and pacifist conviction who had faced considerable difficulty during the war years due to his conscientious objection to military service. He had avoided imprisonment partly through the intervention of the Astronomer Royal, Frank Watson Dyson, who argued that Eddington's scientific expertise was too valuable to waste and that plans were already underway for an important astronomical expedition that required his participation. Eddington had learned of Einstein's general relativity theory through a copy of the papers sent by the Dutch physicist Willem de Sitter, and he had become fascinated by both the mathematical elegance and the physical implications of the work. He was perhaps uniquely positioned among British scientists to appreciate the theory, for he possessed the necessary mathematical sophistication, the astronomical expertise to understand the observational challenges involved in testing it, and a temperament inclined toward embracing revolutionary ideas rather than defending established orthodoxy. Eddington spent considerable effort during 1916, 1917, and 1918 mastering the theory and explaining it to his British colleagues, writing a detailed report for the Physical Society that helped familiarize English-speaking scientists with concepts that might otherwise have remained inaccessible to them for the duration of the war and beyond. The solar eclipse of May 29, 1919, presented an exceptional opportunity for testing Einstein's prediction about the bending of starlight, for on that date the Sun would pass directly in front of an unusually rich field of bright stars known as the Hyades cluster, providing numerous reference points against which any deflection could be measured with reasonable precision. Dyson, in his capacity as Astronomer Royal, organized a joint expedition funded by the British government, which was a remarkable commitment of resources given that the war had only ended 6 months earlier and the nation was exhausted both economically and spiritually from 4 years of devastating conflict. The expedition divided into 2 teams to maximize the chances of obtaining usable observations despite the unpredictable nature of weather, with one group traveling to the town of Sobral in the Ceará province of northeastern Brazil, and the other, led by Eddington himself along with Edwin Cottingham, journeying to the small island of Principe off the western coast of Africa, in the Gulf of Guinea, which was then a Portuguese colonial possession. The preparations were extensive and meticulous, involving the transport of delicate telescopic equipment across thousands of miles of ocean, the establishment of temporary observing stations in remote locations with limited infrastructure, and the coordination of precise timing to ensure that the critical observations would be made during the few precious minutes of totality when the solar corona would be visible and the background stars could be photographed. The expedition to Principe faced considerable difficulties, for the island's climate proved less cooperative than had been hoped, and on the morning of the eclipse, clouds obscured much of the sky, threatening to render the entire voyage futile. Eddington and his colleague waited anxiously as the moon's shadow swept across the landscape, and they managed to obtain several photographic plates during brief intervals when the clouds thinned sufficiently to allow starlight through, though the images were far from ideal and would require careful analysis to extract any meaningful measurements. The Sobral expedition fared somewhat better in terms of weather, with clearer skies permitting more numerous exposures, though they encountered technical difficulties of their own, including problems with one of their telescopes, an astrographic lens that produced images that were later deemed unreliable due to changes in focus caused by temperature variations during the eclipse. The expedition members returned to England with their precious photographic plates, and the painstaking work of measurement and analysis began, a process that would occupy several months as the positions of stars in the eclipse photographs were compared meticulously with reference photographs of the same starfield taken when the sun was elsewhere in the sky. The analysis of the photographic plates was a delicate and demanding task, requiring the careful measurement of stellar positions to fractions of an arcsecond, accounting for various sources of systematic error, and comparing the results with the predictions of different theories. Newtonian physics, when extended to include the effects of gravity on light, which was not part of Newton's original theory but could be derived by treating light as if it consisted of particles with some effective mass, predicted that starlight grazing the sun would be deflected by approximately 0.87 arcseconds. Einstein's general relativity, by contrast, predicted exactly twice this value, approximately 1.75 arcseconds, because in Einstein's theory both the curvature of time and the curvature of space contribute to the bending, whereas a naive Newtonian calculation only captures what might be thought of as the temporal component. The difference between these predictions, though small in absolute terms, was large enough in principle to be distinguished by careful measurements, and it was precisely this distinction that the eclipse expeditions aimed to establish. The plates from Principe, despite their compromised quality due to cloud interference, yielded results that appeared consistent with Einstein's prediction, and the better plates from Sobral, obtained using an alternative 4-inch telescope after the main astrographic instrument proved problematic, also showed deflections in good agreement with the general relativistic value. On the 6th of November, 1919, a joint meeting of the Royal Society and the Royal Astronomical Society convened in London at Burlington House to hear the official announcement of the expedition's results. The room was filled with the most distinguished scientists in Britain, gathered to learn whether the measurements supported or refuted the theory of a German physicist, an occasion freighted with both scientific and political significance in a nation still raw from the wounds of war. The Astronomer Royal, Frank Dyson, presented the findings of the two expeditions, detailing the measurements and their uncertainties, and concluded that the observations were consistent with Einstein's predicted value of 1.75 arcseconds and inconsistent with both the Newtonian prediction of 0.87 arcseconds and the null hypothesis of no deflection at all. Joseph John Thomson, the president of the Royal Society, who had himself won the Nobel Prize for his discovery of the electron, rose to address the assembled company, and he declared that this is the most important result in connection with gravitation since Newton. The weight of his words settled over the audience, for Thomson was not given to hyperbole, and his endorsement signaled to the scientific establishment that general relativity was to be taken with the utmost seriousness. The philosopher Alfred North Whitehead, who was present at the meeting, later described the atmosphere as one of tense anticipation and eventual recognition that they were witnessing a moment that would be remembered in the history of science, a turning point comparable to the great intellectual achievements of the past. The news spread quickly from Burlington House to the offices of newspapers throughout London and thence to the wider world, and within days Albert Einstein had been transformed from a physicist known primarily within academic circles to an international celebrity whose name and face became recognizable to ordinary people who had never studied science and never would. The Times of London ran a headline proclaiming a revolution in science, new theory of the universe, Newtonian ideas overthrown, and similar headlines appeared in newspapers across Europe, America, and beyond, each attempting to convey to general readers the significance of findings that most journalists themselves barely understood. There was something in the public imagination that responded powerfully to the idea of a lone genius overturning centuries of established thinking, of space and time being revealed as stranger and more malleable than common sense suggested, of light itself bending under the influence of gravity as it passed near the sun. Einstein received letters from admirers, requests for interviews, invitations to lecture, and inquiries from all manner of curious correspondents, and he found himself suddenly burdened with a fame that he had never sought and that would accompany him for the rest of his life, making him perhaps the first scientist to achieve the kind of worldwide recognition previously reserved for political leaders, military figures, and entertainers. The results of the Eclipse expedition were not, however, accepted without controversy, and in the years and decades that followed, various critics raised questions about the methodology and interpretation of the measurements. Eddington in particular came under scrutiny for his role in analyzing the data, with some suggesting that his prior commitment to Einstein's theory had influenced his judgment in ways that compromised the objectivity of the conclusions. The most pointed criticism concerned the treatment of the Sobral astrograph plates, which had yielded measurements closer to the Newtonian prediction than to Einstein's value, and which Eddington and Dyson had decided to exclude from the final analysis on the grounds that the instrument had suffered from a defect in focus that rendered its measurements unreliable. Critics argued that this decision appeared suspiciously convenient, that the problematic plates were rejected precisely because they gave the wrong answer, while plates of comparable or perhaps even lesser quality were retained because they supported the desired conclusion. Eddington's defenders countered that the decision to exclude the astrograph data was based on legitimate technical concerns that had been documented before the final results were known, and that subsequent analyses using more sophisticated statistical techniques have generally vindicated the original conclusions, but the controversy has never entirely subsided, and it remains a subject of discussion among historians of science interested in the sociology of knowledge and the ways in which theoretical commitments can shape the interpretation of experimental evidence. There was also a political dimension to the reception of the eclipse results that added layers of complexity to what might otherwise have been a straightforward scientific announcement. The confirmation of general relativity represented British scientists validating the work of a German physicist at a time when anti-German sentiment remained intense throughout Britain and the Allied nations, when memories of the war dead were painfully fresh, and when many people struggled to separate the realm of pure science from the national identities of those who practiced it. Some saw the Eclipse expedition and its favorable conclusions as a noble gesture of reconciliation, a demonstration that the international community of science could transcend the hatreds and divisions of war and recognize truth regardless of its national origin. Others were more cynical, noting that Einstein himself was hardly a typical representative of German nationalism, for he had been a Swiss citizen for much of his career, had signed a counter-manifesto opposing German militarism early in the war, and was Jewish at a time when anti-Semitic currents were already stirring in Germany, though they would not reach their terrible culmination for another decade and more. Eddington's Quaker pacifism made him particularly sympathetic to the cause of international scientific cooperation and to the idea of reaching across the chasm of wartime enmity, and it is possible that his personal convictions influenced not only his willingness to champion Einstein's theory but also his interpretation of ambiguous data, though such speculation ventures into psychological territory that is difficult to assess with confidence at this historical remove. Einstein himself learned of the eclipse results through a telegram from Hendrik Lorentz, who communicated the news as soon as it became available, and his reaction was characteristically philosophical rather than triumphant. When a student asked him how he would have felt if the observations had contradicted his theory rather than confirming it, Einstein reportedly responded that then I would feel sorry for the dear Lord, because the theory is correct. This remark captured something essential about Einstein's approach to physics, his deep conviction that the universe was fundamentally rational and comprehensible, that nature's laws possessed a mathematical beauty and logical consistency that could be discerned through careful thought, and that empirical tests served not so much to determine whether a well-constructed theory was true but rather to reveal whether the theorist had succeeded in grasping the underlying reality. It was an attitude that served Einstein well in developing general relativity, sustaining him through years of difficult work when empirical guidance was scarce and mathematical obstacles seemed insurmountable, though some historians have suggested that this same confidence in theoretical intuition over experimental evidence may have contributed to his later difficulties in accepting quantum mechanics and to his growing isolation from the mainstream of 20th-century physics in his final decades. The Nobel Prize in Physics for 1921, which was actually awarded in 1922 due to the committee's decision to defer the previous year's prize, went to Albert Einstein, but not for the theory of relativity that had made him famous throughout the world. Instead, the Nobel citation honored his work on the photoelectric effect, specifically his explanation of how light falling on a metal surface could eject electrons with energies that depended on the light's frequency rather than its intensity, an explanation that required treating light as consisting of discrete quanta of energy rather than continuous waves. This earlier work, published in 1905 during Einstein's miraculous year at the Patent Office in Bern, had been instrumental in the development of quantum theory and was undeniably deserving of recognition, but many observers noted that the committee's choice seemed designed to avoid endorsing relativity, whether special or general, which remained controversial among some physicists and which involved theoretical claims that the conservative Swedish academicians may have considered insufficiently established by experimental evidence. The politics of the Nobel Prize are always somewhat opaque, and various explanations have been offered for the committee's decision, including the influence of particular members who were skeptical of relativity, concern about the philosophical implications of a theory that seemed to make time and space relative rather than absolute, and simple caution in the face of revolutionary claims that overturned centuries of established physics. Whatever the reasons, the award for the photoelectric effect rather than relativity remains one of the more curious episodes in the history of scientific honors, though it should be said that Einstein's quantum work was itself profoundly important and might well have merited recognition even if he had never developed his theories of relativity at all. In the years following the 1919 eclipse, additional tests of general relativity were conducted, and the theory gradually won acceptance among the majority of physicists, though pockets of resistance remained for decades, particularly among those who found the conceptual framework philosophically troubling or who questioned the adequacy of the experimental evidence. The gravitational redshift predicted by general relativity, whereby light climbing out of a gravitational field loses energy and shifts toward longer wavelengths, proved difficult to measure with the technology of the early 20th century, and definitive confirmation would await the development of precision atomic clocks and the Pound-Rebka experiment of 1959. The precession of Mercury's perihelion remained the most precisely confirmed prediction of the theory for many years, though as observational techniques improved, measurements of light bending during subsequent eclipses provided increasingly accurate confirmations of Einstein's predicted value. The theory's prediction of gravitational time dilation, whereby clocks run slower in stronger gravitational fields, would eventually find practical application in the global positioning system, whose satellites must account for relativistic effects to maintain their accuracy, but such technological vindications lay far in the future, unimaginable to the scientists gathered at Burlington House on that November evening in 1919, who knew only that they had witnessed something remarkable, a moment when human understanding of the cosmos had shifted in ways whose full implications would take generations to unfold, and who dispersed into the London night carrying with them the knowledge that space and time were not what Newton had supposed, that gravity was geometry, and that a quiet man with unruly hair working in Berlin had seen further into the nature of reality than anyone since Isaac Newton himself.